The night is a heavy velvet curtain drawn softly across the window of the world. It is a time for stillness, a time when the frantic motion of the day settles into a quiet rhythm, like dust motes drifting slowly in a shaft of moonlight. Take a moment before we begin to find your own stillness. Let your shoulders drop away from your ears. Unclench your jaw. Let the muscles of your face soften, smoothing out the worries of the waking hours. Feel the weight of your body sinking into the mattress, supported, held, safe. Tonight, we are going to take a journey. We are not traveling outward to the distant stars, though we will find them along the way. We are traveling inward. We are going down, past the skin of the world, past the cells of life, past the molecules that make up the air you breathe. We are drifting down into the basement of reality, into the quiet, shimmering world of the quantum. Chapter 1: The Grain of the Universe. It is a strange place, a place where the rules of the everyday world dissolve like mist in the morning sun. But do not worry. You do not need to solve equations here. You do not need to memorize facts. You only need to drift, to watch, to listen to the hum of the universe at its most fundamental level. Imagine, if you will, a stream of water. Visualize it pouring from a pitcher, crystal clear, catching the light. It looks smooth, doesn't it? A single, continuous sheet of liquid, bending and flowing without a break. For centuries, this is how we thought the universe was built: smooth, continuous, unbroken. We believed that energy flowed like that water, a seamless river. We believed that if you zoomed in closer and closer still, you would just see more smoothness. We thought nature was painted with a wide brush in long, sweeping strokes. But in the year 1900, a man named Max Planck looked closer. He was looking at something very simple: heat. Imagine a blacksmith's forge. Picture a piece of iron thrust into the heart of the fire. At first, it is dark. Then, as it warms, it glows a dull, deep red, then bright orange, then a blinding yellow, and finally, if it gets hot enough, a piercing blue-white. Planck tried to explain this beautiful gradient of color using the old rules, the rules of the smooth river. But the math failed him. The equations said that the iron should glow with an infinite brightness, a catastrophe of energy that would consume everything. But the iron didn't destroy the world. It just glowed, calm and steady. So Planck made a guess that would shatter the mirror of classical physics forever. He imagined that energy did not flow like a smooth stream. Instead, he imagined it falling like rain. Visualize that stream of water again, but now look closer. So close that the smooth sheet breaks apart into billions of tiny, individual droplets. Planck realized that energy comes in packets, tiny, indivisible chunks. He called them quanta. This was the birth of the grainy universe. It means that reality is not a slope. It is a staircase. You cannot stand between the steps. You must be on one step or the next. The universe counts. It deals in whole numbers. It pays in coins, not in fluid value. Deep down, beneath the smoothness of your skin, beneath the solid wood of your floor, The universe is pixelated. There is a smallest possible thing, a smallest possible action. Planck discovered a number, a tiny, impossibly small number, that describes the size of these pixels. We call it Planck's constant. It is the grain size of existence. It is the resolution of reality. If this number were large, if the grain was the size of a marble or an apple, the world would be a chaotic, flickering nightmare. You would see the world jump and stutter like a broken film reel. But the grain is small, so small that 10 billion trillion of them could fit inside a single atom. And because it is so small, the world appears smooth to us. The staircase looks like a ramp. The rain looks like a river. But tonight, as you drift toward sleep, remember the truth. The smoothness is an illusion. We are floating in a sea of tiny, glittering droplets of energy. Let yourself sink deeper into this idea. The air in your room feels still, but it is not empty. It is filled with these tiny packets of energy, flickering, vibrating, dancing. The heat of your body is a gentle radiation of these quanta, leaving you like slow breaths, warming the sheets. This discovery changed everything. It was the first key to a door that had been locked since the dawn of time. And when scientists opened that door, they did not find a dark, empty room. They found a wonderland. As we step through that door together, the first thing we notice is the light. Light has always been a mystery. For thousands of years, we argued over it. Isaac Newton, the father of gravity, imagined light as a stream of tiny bullets, corpuscles, flying through space. He saw light as particles, solid, distinct. But others looked at how light bends around a corner, or how it ripples like a pond when you toss in a stone, and they said, no, light is a wave. And for a long time, the wave theory won. We could prove it. If you shine a light through two narrow slits cut into a screen, the light spreads out on the other side. The waves overlap. Where two crests meet, they get brighter. Where a crest meets a trough, they cancel out into darkness. It creates a pattern of stripes, a zebra crossing of light and shadow. Only waves do that. Bullets don't ripple. So we settled it. Light was a wave. The universe was an ocean of electromagnetic vibrations. But then came Albert Einstein. He looked back at Planck's discovery that energy comes in packets, and he asked a simple, dangerous question. What if light itself is grainy? Imagine standing on a beach on a sunny day. You feel the warmth of the sun on your skin. It feels like a continuous blanket of heat. But Einstein said that light arrives not as a continuous wave, but as a rain of particles. He called them photons. Each photon is a tiny packet of light, a droplet of sun. When you see a red light, you're being touched by photons with lower energy, lazy and slow. When you see a blue light, you are being struck by energetic photons, vibrating quickly. This was proven by the photoelectric effect. Imagine a sheet of smooth, cold metal. If you shine a light on it, you can knock electrons loose from the surface, like pebbles being kicked off a cliff. If light were just a wave, a very bright, intense red light should be like a massive tidal wave. It should have enough power to wash the electrons away. But it doesn't. You can shine the brightest red spotlight in the world on that metal, and the electrons won't budge. But turn on a dim, faint blue light, barely a whisper of illumination, and the electrons fly off instantly. Why? Because the red photons, no matter how many of them there are too weak individually. They are like ping pong balls thrown at a boulder. But the blue photons are like heavy rocks. Even one of them carries enough punch to knock an electron free. So, light is a particle. The debate was over. Or was it? This is where the dream begins to bend. This is where the logic of the day gives way to the magic of the night. Because nature refused to choose. When we ask light, "Are you a wave?" it behaves like a wave. It ripples, it bends, it interferes. When we ask light, "Are you a particle?" it behaves like a particle. It strikes, it counts, it punches. It is both, and it is neither. It is a shapeshifter, a phantom. Imagine a shape suspended in the air. If you shine a light on it from the front, it casts a shadow of a circle on the wall. If you shine a light from the side, it casts a shadow of a square. Is the object a circle, or is it a square? It is a cylinder. It is something more complex, something richer, which can only be understood by looking at its shadows. Light is like that. We cannot see its true face. We can only see the shadows it casts in our experiments. Sometimes it casts the shadow of a wave, sometimes the shadow of a particle. But its true nature, its quantum nature, is something beyond our language. Drift with this image. You are floating in deep space. A single photon, a solitary spark of creation, is traveling toward you from a distant star. It has traveled for 1 billion years. For all that time, as it crossed the void, it was a wave. It was spread out. It wasn't in one place, it was in many places, expanding like a ripple on a dark pond, exploring every path through the cosmos. But the moment it hits your retina, the moment you see the star, that wave collapses. Instantly, it shrinks from being light years wide down to a single microscopic point. It becomes a particle. It delivers its tiny kiss of energy to your eye, and your brain says, "Star." For 1 billion years, it was a ghost. For one final moment, it became real. This is the dual nature of reality. Everything you touch, everything you see, has this double life. The phone in your hand, the blanket over your legs, even the atoms of your own body. They are all shimmering between being solid things and being waves of possibility. You are not just a solid object lying in a bed. You are a symphony of waves, vibrating, resonating, interacting with the fields of the universe. And this brings us to the edge of the atom. For a long time, we thought of atoms like miniature solar systems. We learned this in school, didn't we? A hard, dense nucleus in the center, like a sun, and tiny electrons whizzing around it like planets in neat circular orbits. It is a comforting image, orderly, predictable, clockwork. But the quantum world is not a clock. If you could shrink down, smaller than a cell, smaller than a strand of DNA, down to the level of an atom, you would not see little planets orbiting a sun. You would see a cloud. The electron is not a ball. It is a mood. It is a mist. It is a vibration. Because of its wave nature, the electron is not in one place. It is smeared out around the nucleus. It surrounds the center like a fog. It is everywhere in its orbit at once. If you try to touch it, if you try to measure it, it will suddenly snap into a single position. "Here I am," it seems to say. But the moment you look away, it dissolves back into the cloud. It returns to the wave. It creates a shell of probability, a protective haze that gives the atom its size. Think about this. The nucleus of an atom is tiny. If the atom were the size of a football stadium, the nucleus would be a marble on the center line. The electrons would be tiny gnats buzzing in the highest seats of the stands. Everything in between, the field, the rows of seats, the air, is empty space. You are made of atoms, which means you are made almost entirely of empty space. So why do you feel solid? Why doesn't your hand pass through the table? Why doesn't the bed collapse beneath you? It is because of that electron cloud, that ghostly quantum fog. When your hand touches the table, the clouds of your electrons push against the clouds of the table's electrons. They repel each other, not because they are touching, but because the waves are interacting. You have never truly touched anything in your life. You are floating, always, on a cushion of quantum forces, hovering nanometers away from everything you encounter. You are levitating. The solidity of the world is a mirage created by the rapid motion of these waves. Like a fan spinning so fast it looks like a solid disk. If the fan stopped, you could put your hand through it. But the quantum fan never stops. It spins forever. So rest now on your cushion of fields. Feel the support of the bed, knowing that it is a dialogue between the atoms of the mattress and the atoms of your body. A silent agreement to hold you up. A promise kept by the laws of physics. The universe is grainy, yes, it is built of steps and packets. But out of those jagged pieces, it weaves a blanket of incredible smoothness. It takes the chaos of the quantum and spins it into the calm of the classical. We have only just stepped across the threshold. We have seen that light is a dual spirit and that matter is a misty cloud. But there are deeper mysteries waiting in the dark. Questions of how a thing can be in two places at once. Questions of how two hearts can be connected across the galaxy. Questions of uncertainty and the power of merely looking. The library of the universe is vast, and the lights are dim. We have plenty of time to explore the aisles. But for now, let the concept of the grainy, pixelated universe fade. Let the waves of probability wash over you. You are safe in the uncertainty. You are a wave, resting on a wave, drifting in the great, dark ocean of the night. Chapter 2, The Library of Possibilities. We are drifting deeper now. Behind us lies the familiar world of solid things, the tables, the chairs, the steady ground beneath our feet. We have left the shore of the certainty we know and pushed off into the deeper waters of the quantum ocean. The air here is different. It is thick with potential. In the previous chapter, we saw that matter is not a collection of hard marbles, but a haze of clouds. We learned that the universe is pixelated, grainy, and shimmering with waves. But tonight, the mystery deepens. We are going to explore a concept that defies every instinct you have ever had. It is the idea that a thing can be two different things at the exact same time. It is the idea that the universe does not choose a path until it absolutely has to. This is the realm of superposition. To understand this, let us return to a simple, quiet room in your mind. Imagine a wooden table. The grain of the wood is smooth, polished by time. In the center of the table, there is a coin. It is an old coin, heavy and bronze. Reach out in your mind and pick it up. Feel the cool metal against your thumb. It is solid, it is real. Now, give it a spin. Flick it with your finger and watch it dance across the wood. Round and round it goes, humming a low, metallic song. Look at the spinning coin. Is it heads or is it tails? While it is spinning, it is a blur. It is a sphere of motion. In our everyday world, we say it is either heads or tails. I just don't know which one yet. We believe the coin has a secret. We believe that if we had a high-speed camera, we could freeze time and see exactly which face is up at any given microsecond. But in the quantum world, the coin is doing something magical. While it is spinning in that quantum state, it is not hiding a secret. It is not either heads or tails. It is fully, genuinely both. It is a ghost occupying two states at once. It is a mixture, a blend, a superposition of all its possibilities. The head's reality and the tail's reality are overlapping, singing in harmony like two notes in a chord. This is how the particles of your universe behave when you are not watching them. An electron does not spin clockwise or counterclockwise. It spins both ways. An atom does not sit on the left side of a box or the right. It sits in both corners simultaneously, filling the space with its potential. It is a beautiful, if unsettling, thought. It means that until a choice is made, the universe is limitless. It keeps its options open. It refuses to be pinned down. There is a famous story about this, a parable of modern physics told by a man named Erwin Schrödinger in 1935. It is a story about a cat. Now, do not worry, this is not a sad story. It is a story about a box that contains a mystery. Imagine a steel box. The walls are thick and soundproof. There are no windows, no way to peek inside. Schrödinger asked us to imagine placing a cat inside this box, along with a tiny, fragile device, a device controlled by a single atom. If the atom decays, a random quantum event, a mechanism trips and the cat falls asleep forever. If the atom does not decay, the cat remains awake and happy. The box is sealed. Time passes. Now, stand outside the box. What is the state of the cat? Common sense tells us the cat is either awake or it is not, one or the other. It is a binary world. But quantum mechanics tells us something stranger. It says that because the atom is in a superposition, because the atom is both decayed and not decayed at the same time, the cat, which is linked to the atom, shares its fate. Until you open the lid, the cat is not alive, it is not dead. It is suspended. It is a blur. It is a wave of possibility involving both a living cat and a dead one, coexisting in the dark. The universe has not decided. This thought experiment was meant to show how absurd the quantum rules seem when we apply them to living, breathing things. But the math insists it is true. Inside the unobserved dark, reality is a cloud of maybe. Only when you step forward, only when you lift the lid and look inside, does the spell break. This is called the collapse. The wave function, that mathematical description of all the possibilities, snaps shut. The blur resolves into sharpness. The coin stops spinning and lands flat. The cat is revealed as one thing or the other. This suggests something profound about you, about the observer. You are not just watching the universe, you are sculpting it. By looking, by measuring, by interacting, you are forcing the cosmos to make up its mind. You are the artist who turns the chaotic clay of potential into the statue of reality. Without you, the story has no ending. Let's drift away from the box now. Leave the cat in peace. Let's float down into the microscopic world to see what this magic looks like in practice. Imagine you are standing at the edge of a dense, dark forest. You need to get to the other side. There are two paths winding through the trees. One goes left, around a grove of ancient oaks. The other goes right, past a murmuring brook. You are a traveler. You are a solid thing. You must choose, left or right. But if you were an electron, you would not choose. You would become a mist. You would drift forward, and your ghostly form would split. You would flow down the left path and the right path at the same time. You would brush against the oak trees and ripple the water of the brook simultaneously. You would explore the entire forest at once. And when the paths merged again on the other side, the you that went left and the you that went right would meet. They would overlap. They would interfere with each other. Like ripples from two stones thrown into a pond, the waves of your journey would cross. Where the crests meet, they would rise higher. Where a crest meets a trough, they would vanish. This is how nature finds its way. It does not walk a straight line. It explores every possible history, every possible route, all in the same breath. This phenomenon is happening right now, outside your window. Think of a green leaf on a tree. It is soaking up the sunlight, turning it into energy. Inside that leaf, there is a tiny packet of energy trying to find its way to the reaction center, the factory where food is made. It needs to get there fast, before the energy fades. The path is crowded and complex, a maze of molecules. If the energy had to bump around blindly like a ball in a pinball machine, it would get lost. The plant would die. But it doesn't. Recent discoveries suggest that the energy moves like a quantum wave. It enters a state of superposition. It takes all the paths through the maze at once. It flows like water filling a mold, instantly finding the most efficient route, the path of least resistance. This phenomenon is happening right now, outside your window. Think of a green leaf on a tree. It is soaking up the sunlight, turning it into energy. Inside that leaf, there is a tiny packet of energy trying to find its way to the reaction center, the factory where food is made. It needs to get there fast, before the energy fades. The path is crowded and complex, a maze of molecules. If the energy had to bump around blindly like a ball in a pinball machine, it would get lost. The plant would die. But it doesn't. Recent discoveries suggest that the energy moves like a quantum wave. It enters a state of superposition. It takes all the paths through the maze at once. It flows like water filling a mold, instantly finding the most efficient route, the path of least resistance. Every plant you see, every blade of grass, is quietly performing a quantum miracle. They are harnessing the power of being in two places at once to capture the sun. Life itself is built on this ghostly ability to explore the library of possibilities without ever opening a single door. This power, the power of superposition, is what scientists are now trying to harness in our machines. We call them quantum computers. It sounds cold, technical, but think of them as multiverse explorers. An ordinary computer thinks in switches, on or off, yes or no, 1 or 0, 1 or 0. It reads a book one word at a time, page by page. It is fast, but it is linear. A quantum computer thinks in qubits. A qubit is like that spinning coin. It is 0 and 1 together. It is a switch that is both on and off. If you link enough of these qubits together, you create a machine that doesn't just read the book one page at a time. It reads the entire library in a single glance. It can hold a million different answers in its mind simultaneously, floating in a vast, cold superposition. And then, with a delicate pulse of energy, we ask it a question. The waves of all those answers interfere. The wrong answers cancel each other out, fading into silence. The right answer amplifies, rising like a rogue wave from the ocean. It is a new way of thinking, a way of thinking that mimics the universe itself. But there is a fragility to this magic. Superposition is like a soap bubble. It is beautiful, iridescent, reflecting the entire world on its surface, but it is incredibly delicate. It requires silence, it requires cold, it requires isolation. If a stray molecule of air hits the bubble, if a warm photon of light touches it, the bubble pops, the superposition collapses, the magic vanishes, and the system becomes ordinary again. The coin falls, the cat wakes up. This is why we don't see ghosts in our daily lives. You and I are too big, we are too warm, we are too noisy. We are constantly bumping into the air, into the ground, into light. We are constantly being measured by the environment around us. The universe is always looking at us, always touching us, forcing us to be just here and nowhere else. We are living in the collapsed wreckage of the quantum world. The solid furniture, the walls of your room, the beating of your heart. These are the leftovers. These are the choices the universe made. But underneath it all, in the quiet gaps between the atoms, the dream still lives. Deep down, the particles that make you are still trying to spin both ways. They are still trying to be everywhere. So, as you lie here in the dark, imagine that you can reclaim a little of that quantum freedom. The day is done. The choices of the last 24 hours have been made. They are solid. They are history. But tomorrow? Tomorrow is a superposition. Now, imagine you try the opposite. You want to capture the speed. You want to see the motion. So you slow the shutter speed down. You leave the lens open for a long, deep breath. Click. Clack. Now look at the photo. You see a beautiful blur, a streak of color rushing through the trees. You can see the speed, you can feel the momentum in the smear of the image. But look closely. Where is the runner? You cannot say. They are a streak. They are not at this tree or that tree. They are a smear across the entire path. You have captured the motion, but you have lost the position. This is the trade-off. This is the bargain we make with nature. In 1927, a German physicist named Werner Heisenberg realized that the universe works exactly like that camera. He discovered that there are pairs of qualities in the universe that are linked, like two ends of a seesaw. The most famous pair is position, where you are, and momentum, where you are going. Heisenberg realized that you cannot know both of these things about a particle at the same time with perfect precision. The more you pin down the particle's location, zooming in, tightening your focus, trapping it in a corner, the wilder its momentum becomes. It begins to vibrate, it begins to shake. The more you try to hold it still, the more it struggles to move. And if you try to measure its momentum, if you try to gauge the rhythm of its movement, its position spreads out like a drop of ink in water. It becomes a cloud. This is not because our rulers are too clumsy. It is not because our eyes are too weak. It is because the particle is a wave. Think of a wave in the ocean. Ask yourself, where exactly is the wave? Is it at the crest? Is it in the trough? Is it at the start of the swell or the end? A wave is not a point. A wave is a long, undulating shape. It needs space to exist. It needs a spread to be a wave. If you try to squeeze a wave into a single, tiny point, it stops being a wave. It disappears. So, for an electron to have a wavelength, which gives it its energy, its momentum, it must be spread out. It must be fuzzy. If it were perfectly sharp, perfectly located, it would have no wavelength. It would have no energy. It would cease to be part of the quantum dance. This fuzziness is beautiful. It means that at the bottom of everything, reality is soft. The atoms in your body are not hard, grinding gears. They are soft, overlapping clouds. This leads us to one of the most comforting truths in all of physics. Have you ever wondered why atoms don't collapse? Remember the picture of the atom? The nucleus in the center, positively charged, and the electron on the outside, negatively charged. Opposites attract, we know this. The electron wants to fall into the nucleus. It is pulled by a powerful electric force, like a magnet snapping to a fridge. According to the old rules, the electron should spiral inward, crashing into the center in a flash of light. The atom should implode. The universe should shrink into a dense, dead speck. But it doesn't. The atom is vast. The atom is empty. The atom stands strong. Why? Because of uncertainty. Imagine the electron trying to fall into the nucleus. It gets closer and closer. The space it occupies gets smaller and smaller. But remember the rule. The more you pin down the position, the wilder the momentum becomes. As the electron is squeezed into the tiny space near the nucleus, its position becomes too precise. The uncertainty principle kicks in. The electron begins to panic. Its momentum skyrockets. It starts to buzz and vibrate with frantic energy. It creates a quantum pressure, a resistance. The electron refuses to be trapped in the center, because to be trapped would mean having a precise location, and nature forbids that. So the electron pushes back. It finds a balance point, hovering just far enough away to keep its freedom, but close enough to feel the attraction. That balance point is the size of the atom. That balance point is the reason you exist, the reason the floor holds you up, the reason your hand doesn't pass through the cup, the reason matter takes up space. It is all because of this frantic, claustrophobic resistance of the electron. It is the refusal of the universe to be pinned down that gives matter its bulk. You are made of puffiness. You are made of resistance to precision. It is a strange irony. The solidity of the world comes from the fact that its building blocks refuse to sit still. Let this idea settle in your mind like a soft fog. In a world that demands so much accuracy from you, deadlines, schedules, exact words, exact change, the deepest part of you is free from that pressure. Deep down, your atoms are allowed to be blurry. They are allowed to be unsure. They exist in a state of roughly here and moving roughly that way. There is a peace in this lack of focus. It is like listening to music. Think of a beautiful, low note played on a cello. To hear the pitch, to know that it is a C, you need to listen for a moment. You need to hear the vibration, the oscillation of the sound wave. You need time. If you tried to shorten that note to a tiny fraction of a second, snap, you wouldn't hear the pitch anymore. You would just hear a click, a pop. To know the music, you must accept that it takes up time. You cannot freeze the symphony and still hear the song. The universe is a song. It is a vibration, and like a song, it cannot be frozen. It must flow. It must be allowed to blur from one moment to the next. This uncertainty extends even to the empty air. We think of a vacuum as empty space, nothingness, silence. But because of the uncertainty principle, we can never say that a patch of space has zero energy, because zero is a very precise number. Zero means we know exactly what the energy is, and nature hates precision. So even in the deepest, darkest void of space, the energy is never truly zero. It fluctuates, it jitters. Tiny sparks of energy borrow themselves from the future, appear for a microsecond, and vanish again. The vacuum is seething. It is a frothing sea of virtual particles popping in and out of existence, obeying the laws of the fuzziness. Empty space is alive. It is humming. Listen to the silence of your room. It is not dead silence. It is a pregnant silence, a silence full of potential. The air around you is shimmering with these tiny, invisible loans of energy. The fabric of space-time is trembling gently, like the surface of a drum that has just been struck. So do not be afraid of the blur. When your thoughts begin to drift, when the sharp edges of the day begin to soften into the nonsense of dreams, you are not losing control. You are simply aligning with the fundamental nature of things. You are becoming more like an electron. You are spreading out. You are trading your position for momentum. You are letting go of where you are so you can drift to where you are going. Drift into the mist. The fog is safe. The fog is the foundation. In the blur, there is stability. In the uncertainty, there is room to breathe. And as we float here in this soft, indeterminate cloud, we begin to sense a connection. We realize that if particles are waves, and waves can spread out, what happens when two waves meet? What happens when two particles interact and then separate? Do they ever truly say goodbye? Or does the wave connect them forever, across the miles, across the years? We are about to discover that in the quantum world, there is no such thing as separation. We are about to explore the invisible threads that bind the universe together. Chapter 4: The Invisible Thread. We are drifting deeper into the dream of the universe. We have seen the grainy rain of energy. We have walked the forking paths of superposition. We have rested in the soft fog of uncertainty. But now we come to a place of profound comfort, a place that answers the oldest human fear, the fear of being alone. In the classical world, the world of sun and stone, distance is a real thing. If you are in this room and a friend is on the other side of the world, you are separate. To touch them, you must travel. To speak to them, you must send a signal, a sound, a radio wave, a letter. That signal must cross the miles, fighting against the wind and the time. There is a gap between you, a silence. But in the quantum world, distance is not a wall. It is not even a barrier. In the quantum world, it is possible for two things to be so deeply connected that they share the same heartbeat no matter how far apart they are. This is the mystery of entanglement. Imagine two particles, two tiny sparks of light born at the exact same moment from the exact same burst of energy. They are twins. They are not just similar, they are part of the same whole. As they fly apart, moving away from their birthplace, they begin to spin. But they do not spin randomly. They spin in a perfect, silent duet. If one spins up, the other spins down. If one spins left, the other spins right. They are balanced. They are a zero-sum equation of motion. Now, imagine we separate them. We keep one particle here in the palm of your hand. We send the other particle on a long, lonely journey. We put it on a spaceship and send it past the moon, past the rings of Saturn, out into the deep, cold void of interstellar space. It travels for 1,000,000 years until it reaches the edge of the galaxy. They are separated by an ocean of darkness so vast that light itself would take 100,000 years to cross it. Surely they have forgotten each other. Surely the link is broken. But then you look at the particle in your hand. You measure it. You force it to choose a state. Let's say you find it spinning up. At that exact instant, not a second later, not a millisecond later, but instantly, the particle on the other side of the galaxy snaps into the state of spinning down. It doesn't matter that there was no time for a signal to travel between them. It doesn't matter that the speed of light is the speed limit of the universe. The other particle knew. It felt the touch of your measurement across the void. It responded as if there was no space between them at all. Albert Einstein, the great master of space and time, found this deeply unsettling. He believed in a universe where things happened for a reason, where influence traveled locally, step by step. He looked at this quantum connection and famously called it spooky action at a distance. He thought it was a mistake. He thought there must be some hidden instruction, some secret note tucked inside the particles' pockets telling them what to do. But he was wrong. Decades of experiments, from basement labs to satellites orbiting the Earth, have proven it. The spooky action is real. The universe allows for a connection that transcends space. Think about what this truly means. It means that space, the distance that seems so real to us, the miles that separate us from the ones we love, might be an illusion. Or at least it is not the whole story. Underneath the fabric of space, there is a sublayer, a basement level of reality where things are stitched together. Entangled particles are not two separate objects sending messages back and forth. They are a single object that just happens to be in two places. Imagine a long red thread. Now imagine passing that thread through a piece of paper so that only the two ends poke through two holes. From the surface of the paper, it looks like two separate red dots, two independent things. But if you look underneath the paper, you see the thread connecting them. You see that they are one. Entanglement is the thread beneath the paper of the universe. This phenomenon is happening everywhere. It is not just a trick performed in a lab. It is the glue of the cosmos. Every time two atoms interact, every time they collide or bounce or share energy, they become entangled. They leave a little piece of themselves with the other. They walk away carrying a ghostly memory of that meeting. Think of the air in your room. The molecules are constantly crashing into each other, billions of times a second. With every crash, they are knitting an invisible web of entanglement. The air is not just a gas, it is a tapestry. The light from the lamp entangled with the walls, the heat from your skin entangled with the sheets. And consider the beginning. Go back in your mind. Back before the earth, before the sun, before the stars. Go back to the Big Bang. In that first, unimaginable moment, everything that exists, every ounce of matter, every drop of energy was crushed together into a single tiny point. Everything touched, everything was one. Then the explosion, the expansion, the great scattering. The universe blew apart, flinging matter outward to form the galaxies, the nebulas, the planets. But if everything was entangled at the start, does that mean everything is still entangled now? Are the atoms in your right hand entangled with the atoms in a star burning in the Andromeda galaxy? Is the breath in your lungs entangled with the dust on the surface of Mars? Is the universe just one giant, shimmering, entangled thing, pretending to be many pieces? It is a thought that borders on the spiritual, yet it is grounded in the cold, hard math of quantum mechanics. It suggests that isolation is impossible. You cannot cut yourself off from the universe. You are woven into it. When you look up at the night sky, you are not looking at a foreign place. You are looking at a part of yourself that has drifted away. There is a gentleness to this idea. It means that no matter how lonely the night feels, you are tethered. You are connected to the ground beneath you, to the air around you, and to the cosmic history that made you. We are now learning to use this spooky connection. We are building the future with it. Scientists are creating quantum internets. Imagine sending a message that cannot be intercepted because it doesn't travel through the air. It travels through the entangled link. Imagine teleportation, not beaming a person like in the movies, but beaming information, taking the delicate quantum state of an atom here and instantly recreating it there, across the world, using the bridge of entanglement. We have already done this. We have teleported the state of a photon from the ground to a satellite in orbit. We have sent a quantum whisper into space, and the satellite heard it. We are learning to pluck the strings of the invisible web. But tonight, let us simply marvel at the web itself. Close your eyes and visualize the space around you. Usually, we see empty space as a void, a gap, a nothingness that separates things. Try to see it differently now. See the space as a connector. See the invisible lines of light stretching from every atom to every other atom. A billion silken threads crossing the room. Threads connecting you to the window. Threads connecting the window to the tree outside. Threads connecting the tree to the moon. The universe is not a collection of lonely islands. It is a single, vast organism. It is a nervous system of light and gravity. When one part shivers, the whole web trembles. Feel that connection. You don't have to do anything to maintain it. You don't have to send a signal. You don't have to call out. It is built into your atoms. It is your birthright as a child of the Big Bang. You are entangled with the stars. And just as particles have a property that links them, they also have a property that defines them, a property that acts like a tiny internal compass. It is a spinning motion that isn't really spinning, a dance that happens without moving. We call it spin. As we drift further along these invisible threads, let us turn our attention to the tiny dancers that make up the world and the pirouettes they perform in the dark. Chapter 5: The Silent Pirouette. We are traveling inward again. We have floated through the web of entanglement, tracing the invisible threads that hold the stars together. Now we follow one of those threads down, shrinking smaller and smaller until we are face to face with a single electron. It is floating in the void, and if we look closely, we sense a motion. It is not moving across space, it is moving within itself. There is a feeling of rotation, a sense of a twist, a silent, eternal pirouette. We call this spin. But the word is a whisper of a lie. When you hear spin, you imagine a child's top whirring on a floor. You imagine the Earth turning on its axis, bringing the sunrise. You imagine a physical ball of matter rotating in space. But the electron is not a ball. It is a point. It has no surface. It has no equator to spin around. If an electron were truly spinning like a top, its edges would have to move faster than the speed of light just to generate the magnetic field we measure, and that is forbidden. So, what is it doing? It is carrying a secret form of momentum. It is carrying a permanent, built-in arrow of direction. Imagine a compass. A compass doesn't need to spin around to point north. It just has a direction. It possesses an orientation. Every particle in your body, every proton in every atom carries this tiny, invisible compass needle. This discovery began with a beam of silver. In 1922, two physicists named Otto Stern and Walther Gerlach performed an experiment that looked like magic. Visualize a dark laboratory. In the center, a small oven heats a nugget of silver until it evaporates. A thin stream of silver atoms, a ghostly metallic steam, drifts out into the vacuum. The scientists sent this stream of silver through the jaws of a powerful magnet. In the classical world, the magnets inside the atoms should have been pointing in every random direction. Some up, some down, some tilted left, some tilted right. If that were true, the magnet would have smeared the silver beam into a messy, vertical blur on the detector screen. But that is not what happened. When the silver hit the screen, it didn't smear. It split. The beam divided into two crisp, clean lines. One group of atoms went up. The other group went down. Nothing went in the middle. It was as if the universe forced the atoms to choose. Are you spinning up or are you spinning down? There is no sideways in the quantum world. There is no diagonal. Spin is quantized. It is all or nothing. Imagine a ballerina spinning in the dark. In our world, she can spin at any speed. She can slow down, she can speed up. In the quantum world, she can only spin at one precise speed, and she can only spin clockwise or counterclockwise, up or down. And stranger still, she never stops. An electron cannot stop spinning. To stop spinning would be to stop existing. The spin is not something it does, it is what it is. This tiny, ceaseless motion is the source of all magnetism. Why does a magnet stick to your refrigerator? It is not magic. It is the collective dance of billions of electrons. In a piece of iron, the electrons align their spins. They agree to dance in the same direction. Their tiny, invisible arrows all point the same way, and their microscopic magnetic fields add up layer by layer until they create a force strong enough to hold a photo against gravity. When you hold a magnet in your hand, you are holding a macroscopic quantum object. You are feeling the combined weight of a trillion quantum spins. But spin has an even stranger quality, a quality that bends the geometry of the world. If you take a rock and turn it around 360 degrees, a full circle, it returns to where it started. It looks the same. But if you take an electron and turn it 360 degrees, it does not return to its original state. It comes back changed. It comes back with a mathematical minus sign. It is facing the opposite way in the logic of the universe. To get the electron back to normal, you have to turn it another 360 degrees. It takes a rotation of 720 degrees, 2 full circles, to bring a particle of matter back to its beginning. It creates a double cover of reality. It means the electron sees a larger world than we do. It tracks a path that winds twice around the axis of existence. Drift with this image. Imagine walking down a spiral staircase. You walk a full circle, 360 degrees, you are facing the same direction, but you are on a different floor. You are not back where you started. You have to walk another full circle to find your original place. Matter follows this spiral logic. This intrinsic twist helps us categorize the entire universe. Everything you see is divided into two great families, based entirely on their spin. There are the fermions, the particles of matter. They have half-integer spin, 1/2. They are the dancers who need 2 turns to reset. And there are the bosons, the particles of force. They have integer spin, 0, 1, 2. They are simpler. They look the same after 1 turn. These numbers sound dry, but they define the texture of reality. Spin is what makes matter solid. Spin is what makes light flow. Spin is the reason you cannot walk through a wall. And we can listen to this spin. In hospitals around the world, there are giant white machines, MRI scanners, that are essentially giant ears listening to the spin of the atoms in your body. Your body is mostly water. Water is full of hydrogen, and hydrogen nuclei are tiny spinning magnets. When you lie in the scanner, a strong magnetic field lines up all those tiny spins, like soldiers standing at attention. Then, a pulse of radio waves knocks them over. As they spiral back up to their standing position, they sing. They emit a tiny radio signal. The machine hears this song. It maps where the water is. It draws a picture of your brain, your heart, your knees, based entirely on the rhythm of quantum spin. So, as you lie in bed now, feel the quiet rhythm of your own body. You are a galaxy of tiny spinning tops. Billions upon billions of protons and electrons twirling in the dark, never stopping, never slowing down. They are generating a faint magnetic field that surrounds you like a cloak. You are magnetic. You are rhythmic. You are built of motion. The bed you sleep on is solid because of spin. The gravity that holds you is a conversation with spin. The light of the morning will be a wave of spin. Let yourself become a part of that rotation, not a dizzying spin, but a slow, cosmic turning, like the rotation of the Earth, steady, reliable, ancient. The universe is not static. It is a grand, silent clockwork of aligned arrows pointing the way toward sleep. Chapter 6: The Stones and the Light. We have watched the dancers spin. Now we must look at how they dance together. In the great ballroom of the universe, there are 2 kinds of personalities, 2 distinct ways of being. There are the fermions and there are the bosons. Think of them as the stones and the light. They behave differently. They follow different rules. And the difference between them is what makes the world interesting. It is what makes the world possible. Let us start with the fermions. These are the electrons, the protons, the neutrons. These are the particles that make up stuff. They make up the atoms of your body, the wood of the chair, the rock of the mountain. And they have a very specific personality trait. They are the ultimate introverts. They are the loners of the quantum world. There is a rule they must follow, a law written by a physicist named Wolfgang Pauli. It is called the Pauli exclusion principle. It sounds strict, doesn't it? Exclusion. The rule is simple. No 2 fermions can occupy the same state at the same time. They cannot be in the same place, doing the same thing, with the same spin. They need their space. Imagine a theater. The fermions are the audience, and the rule of the theater is that only one person can sit in each seat. If an electron takes the front row, seat A, no other electron can sit there. The next electron must take seat B, then seat C. When the front row is full, the next electrons must go to the second row, then the third. They stack up. They build outward. This simple refusal to share a seat is the reason matter has volume. Why is an atom big? Why isn't it just a tiny speck? Because the electrons refuse to crash into the lowest energy level together. They stack up in layers, creating shells. They puff the atom out like layers of an onion. This is why you can touch things. Press your hand against the mattress. You feel resistance. You feel a surface. That feeling is the Pauli exclusion principle in action. The electrons in your hand and the electrons in the mattress are fermions. They are governed by the law of no trespassing. They refuse to occupy the same space, so they push back. That pressure, that degeneracy pressure, is what you interpret as solidity. It is the force of quantum stubbornness. If fermions were allowed to share space, you would fall right through the bed. The bed would collapse into a speck of dust. The Earth would shrink to the size of a city. The entire structure of the world, the architecture of everything solid, is built on the politeness of fermions. You sit there, so I will sit here. But then there are the bosons. These are the particles of force. The photon, light, the gluon, the graviton. Bosons are the opposite of fermions. They are the extroverts. They are the joiners. They do not obey the exclusion principle. They love to share. Imagine the theater again. But this time, the audience is made of bosons, made of light. One photon sits in the front row, seat A. The next photon comes in. It doesn't look for an empty seat. It sits right on top of the first one. The third photon sits on top of the second. A million, a billion, a trillion photons can all occupy the exact same seat at the exact same time in perfect harmony. When they do this, they do not stack up. They merge. They amplify each other. They become a single giant wave. This is how a laser works. A laser is a choir of bosons singing the exact same note at the exact same time in the exact same place. It is a beam of perfectly coordinated light cutting through the darkness because the particles are willing to be one. Drift between these two feelings, the feeling of the stone, fermion, the feeling of being solid, of having boundaries, of saying, I am here and you are there. This is your body. This is the ground. This is safety. And the feeling of the light, the feeling of merging, of flow, of passing through, of saying, we are one. This is the heat of the sun. This is the Wi-Fi signal in the air. This is the force that holds the atoms together. The universe is a dance between these two tribes. The fermions build the stage. They create the walls, the actors, the props. They create the separation that allows individual things to exist. The bosons weave the story. They carry the messages between the actors. They fly back and forth, carrying electromagnetism, carrying gravity, carrying the strong force that binds the nucleus. Without fermions, there would be no structure, just a soup of light. Without bosons, there would be no interaction. The universe would be a dark, silent collection of dust that never touched, never saw, never felt. But together, they make a symphony. Think of a white dwarf star, a dying sun. It is collapsing under gravity. It wants to shrink to nothing. But the electrons inside it, the fermions, shout no. They refuse to be squeezed into the same state. They push back with their exclusion pressure. They hold up the weight of a star just by refusing to share their seats. A star is saved by the stubbornness of its parts. And think of a superconductor, a wire with zero resistance. In the bitter cold, the electrons, which are normally fermions, do something clever. They pair up, 2 by 2. And when they pair up, they pretend to be bosons. They lose their individuality. They join the choir. They flow through the wire without bumping into anything. A perfect, frictionless stream of current. Matter acting like light. Stones acting like water. The lines blur in the cold and the dark. But for now, resting in the warmth, appreciate the difference. Feel the solidity of the fermions supporting your back. Feel the warmth of the bosons, the infrared light radiating from your skin. You are a vessel of both. You are structure, and you are flow. You are a boundary, and you are a bridge. As we move deeper into the night, we will see what happens when we strip away the matter and look at what remains. We will look at the spaces between the fermions, the empty air, the vacuum, and we will find that it is not empty at all. We are about to enter the fields. Chapter 7: The Ocean of Everywhere. We are floating now. Let the idea of solid ground fade completely. In the previous chapters, we talked about particles, electrons, photons, quarks, as if they were tiny objects, as if they were minuscule specks of dust or drops of light. But that is not the whole truth. That is only how they appear when they break the surface. Beneath the surface, there are no particles. There are only fields. Imagine you are submerged in a vast, endless ocean. The water stretches out in every direction, up, down, left, right, past the horizon, past the stars. The water is calm. It is still. But every now and then, a little ripple forms. A crest of water rises up, travels for a while, and then settles back down. If you were looking at the ocean from far away, you might point at that ripple and say, "Look, there is a thing. There is an object moving across the water." But you know the truth. The ripple is not a separate object. You cannot take the ripple out of the ocean and put it in your pocket. The ripple is the ocean, just behaving differently for a moment. This is the deepest secret of modern physics. The universe is filled with these invisible oceans. We call them quantum fields. They are everywhere. Right now, in the room where you sleep, the air is filled with them. They pass through the walls, through the bed, through your body. There is an electron field. It is a fluid that fills the entire universe. Every single electron in your body, the trillions of them spinning in your cells, is just a tiny ripple in that one vast field. They are not separate things. They are just local vibrations of the same universal sheet. When an electron moves from your hand to the sheet, it is just a ripple transferring from one part of the ocean to another. There is a photon field, the electromagnetic field. Every beam of light, every radio wave, every color you see is a wave in that field. There is a quark field, a gluon field, a Higgs field. The universe is a layer cake of these fields, all overlapping, all occupying the same space, ghosting through one another. This is a beautiful thought. It means that connection is the default state of reality. We often feel isolated. We feel like separate entities, cut off from the world by the boundary of our skin. But in the language of fields, separation is an illusion. You are made of the same stuff as the stars, not just metaphorically, literally. The ripple that is you and the ripple that is the sun are made of the exact water. Think of a guitar string. The string runs the length of the instrument. It is one object, but you can pluck it in many places. You can make a low note vibrate at one end and a high note vibrate at the other. The notes sound different. They are in different places, but they are excitations of the same string. Particles are the notes. The universe is the instrument. This explains why every electron is exactly the same. Have you ever wondered why every electron in the universe has the exact same charge, the exact same mass, the exact same spin? Why aren't there fat electrons and thin electrons? Why aren't there slightly faster or slower ones? It is because they are all cast from the same mold. They are all identical ripples in the same field. There is only one electron field. We are all just sharing it. Rest in this feeling of unity. The emptiness of space is not empty. It is a fullness. It is a presence. It is a thick, rich medium that connects everything to everything else. You are not floating in a void. You are floating in a substance. You are held by the fabric of reality. And these fields are not silent. They talk to each other. When an electron ripple moves through the electron field, it disturbs the photon field nearby. It creates a splash. That splash is what we call light. When you rub your hands together to warm them, you are creating a disturbance in the fields, transferring energy from the motion of your skin into the warmth of the air. You are a conductor of the cosmic orchestra. So let your breathing align with this idea. Inhale and imagine drawing energy from the vast field around you. Exhale and imagine your breath rippling out, changing the field forever. You are continuous with the cosmos. There is no edge where you end and the universe begins. Chapter 8: The Humming Void. We are sinking deeper into the ocean now. We have realized that the universe is made of fields. But what happens when the ocean is calm? What happens in the deepest, darkest vacuum of space where there are no stars, no atoms, no light? Is it truly quiet? Is it truly empty? The answer, whispered by the mathematics of the quantum, is no. Nothing is never truly nothing. Remember the uncertainty principle? The rule that says we cannot know the energy and the time of a system with perfect precision? Because of this rule, a field can never sit perfectly still. If a field were perfectly flat, zero energy, zero motion, we would know its state too precisely. Nature forbids this. So the field must jitter. It must tremble. Even in the absolute zero of the void, the fields are bubbling. Imagine a pot of water just before it boils. The surface is not yet churning, but it is not still. It is shivering. Tiny bubbles form at the bottom and vanish before they can rise. The vacuum of space is like that. It is a seething froth of virtual particles. These are ghost particles. They borrow energy from the bank of the universe, exist for a fraction of a nanosecond, and then pay the energy back and vanish. Matter and antimatter popping into existence, snap, and annihilating each other, crackle, in the blink of an eye. Every cubic centimeter of empty space in your room is alive with this activity. It is a cosmic hum, a background static of creation and destruction. We call this zero-point energy. It is the minimum amount of energy the universe can have. It is the floor, but the floor is vibrating. It sounds like a fantasy, doesn't it? Something scientists invented to make the math work. But we can prove it is real. We can feel the push of the ghosts. There is an experiment called the Casimir effect. Imagine taking two metal plates, perfectly flat, perfectly polished. You place them in a vacuum, very, very close together, thinner than a sheet of paper. There is nothing between them. No air, no light, nothing. They should hang there, still and silent. But they don't. They move. They are pushed together. Why? Because the nothing outside the plates is stronger than the nothing inside the plates. Outside, the ocean of virtual particles is wild and stormy. There are waves of all sizes crashing against the metal. Inside, the narrow gap, the big waves don't fit. Only the tiny ripples can exist there. The ocean is calmer. So the pressure from the outside storm pushes the plates together. The vacuum itself, the empty space, has a physical force. It has a weight. This is the heartbeat of the void. It is a comforting thought for the night. It means that silence is not an absence. Silence is a presence. When you close your eyes and the world goes dark, you are not alone. You are surrounded by a living stillness. The air is humming a lullaby of energy that has been playing since the beginning of time. It explains why black holes aren't truly black. Stephen Hawking realized that this bubbling vacuum interacts with the edge of a black hole. Occasionally, a pair of ghost particles pops up right on the cliff edge. One falls in, the other escapes. To us, it looks like the black hole is glowing. It is radiating heat. The vacuum is stealing energy from the monster bit by bit until the black hole evaporates into the night. So wrap yourself in the blanket of the humming void. It is not cold, it is vibrant. It is the soil from which everything grows. Before the Big Bang, there was likely just this, a fluctuating field, trembling in the dark. And from a random spark in that trembling, the entire universe unfolded. You are a child of the vacuum's restlessness. Chapter 9. The Ghost in the Wall. We have floated in the ocean. We have listened to the hum. Now we are going to try something impossible. We are going to walk through a wall. In the world of the day, barriers are absolute. If you throw a tennis ball at a brick wall, it bounces back. Every time. If you roll a marble up a hill and it doesn't have enough speed to reach the top, it rolls back down. Physics is strict. If you don't have the energy to overcome an obstacle, you stop. But in the quantum dream, obstacles are suggestions. Barriers are misty. This is the phenomenon of quantum tunneling. Remember that you are not a solid object. You are a wave. Imagine a wave crashing against a breakwater. Most of the water bounces back, but some of the water seeps through the cracks. Some of the wave extends to the other side. Particles behave the same way. When an electron approaches a barrier, an energy wall that it shouldn't be able to cross, it doesn't just hit it and stop. Its wave function, that cloud of probability, smacks into the wall. Most of the cloud bounces back, but a tiny, ghostly tail of the cloud leaks through the barrier. It extends to the other side. And because the electron is a wave of probability, if there is a piece of the wave on the other side, there is a chance, a small, real chance, that the electron will suddenly find itself there. It doesn't climb over the wall, it doesn't dig under it, it doesn't break a hole. It simply vanishes from one side and appears on the other. It slips through the fabric of reality like a ghost passing through a closed door. It sounds rare, a magic trick, but it is happening constantly. In fact, you owe your life to it. Look at the sun, or imagine it burning in the sky. How does the sun shine? It shines by smashing hydrogen atoms together to make helium, fusion. But protons are positively charged. They hate each other. They repel. To fuse, they have to get incredibly close. But the sun, believe it or not, is not hot enough to push them that close. According to classical physics, the protons should bounce off each other. The sun should not ignite. It should be a cold, dark ball of gas. So why is it burning? Tunneling. As the protons rush toward each other, they hit the wall of repulsion. They don't have enough energy to cross it. But every now and then, once in a trillion collisions, a proton decides to cheat. It borrows the magic of the quantum. It tunnels through the repulsion barrier and lands right inside the other proton. Snap! Fusion happens. Light is born. Every ray of sunlight that has ever warmed your face, every photon that feeds the plants that feed you, is a result of a quantum particle walking through a wall. The sun is a giant quantum tunneling machine. The daylight is a ghost story. We use this magic here on Earth, too. We have built microscopes, scanning, tunneling microscopes that use a tiny metal tip, sharp as a single atom. We hover the tip just above a surface. We don't touch it, but we bring it close enough that electrons can tunnel across the gap. They jump from the surface to the tip, creating a tiny current. By measuring this current, we can feel the shape of individual atoms. We can map the bumps and valleys of the molecular world, reading the braille of the universe. And think of the enzymes in your body. Right now, in your cells, chemical reactions are happening that keep you alive. Some scientists believe that protons are tunneling their way through molecules to make these reactions faster. Your biology is using quantum shortcuts. So, as you lie in bed surrounded by walls, think of the freedom of the tunnel. Think of how the universe is not a series of closed doors. It is permeable. When the odds are low, when the barrier seems too high, nature has a way of slipping through. It doesn't force its way, it doesn't fight, it waits. It spreads out its possibilities, and it simply arrives on the other side. There is a lesson in this for the weary mind. Sometimes we face barriers in life, problems that seem too big, mountains we cannot climb. The quantum way is not to crash against them. The quantum way is to relax, to spread out your awareness, to realize that a part of you is already on the other side, to trust that, in time, you will find yourself there. We are almost at the end of our structural journey. We have seen the particles, the waves, the fields, and the ghosts. But there is one final state we must explore. A state of cold, a state of perfection, a state where the chaos of the universe finally stops and everything moves as one. Chapter 10. The Symphony of Cold. We are traveling to the coldest place in the universe, colder than the dark side of the moon, colder than the empty voids between the galaxies. We are traveling to a laboratory on Earth where scientists have learned to slow time down by freezing it. In our everyday world, heat is noise. Heat is the jiggling of atoms. The hotter something is, the faster its particles vibrate, bounce, and collide. It is a chaotic dance, a crowded room full of people bumping into one another. But as we lower the temperature, the dance slows. The noise fades. The atoms begin to calm down. We drop past the freezing point of water, past the freezing point of air, down, down, toward the absolute floor of existence, absolute zero. At this temperature, the motion of the world almost stops. And when things get this quiet, the quantum spirits come out to play. We witnessed earlier how bosons, the particles of light, love to occupy the same state. But atoms are usually individualists. They keep their distance. However, if you cool certain atoms down enough, to a billionth of a degree above absolute zero, something miraculous happens. They lose their identity. They stop being this atom and that atom. Their wave functions, those clouds of probability, begin to expand. They grow larger and larger as they slow down. Eventually, the clouds overlap. They merge. Suddenly, a million separate atoms snap into a single state. They become one giant, shimmering superatom. We call this a Bose-Einstein condensate. Imagine a choir. Before the conductor arrives, everyone is talking, coughing, tuning their instruments. It is a mess of sound. That is a normal gas. Then the conductor raises a baton. Silence falls. And then everyone sings the exact same note at the exact same pitch at the exact moment. The sound is pure. It is perfect. It is one voice coming from 100 throats. That is the condensate. It is a state of matter where the quantum world becomes big enough to see. If you looked at a droplet of this condensate, you wouldn't see a speck of dust. You would see a single quantum wave, rippling and interfering with itself. And this leads to one of the most magical substances in existence, superfluid. Imagine a cup of coffee. If you stir it, it swirls. Eventually, friction against the cup slows it down and it stops. Now, imagine a cup of superfluid helium. You stir it, it swirls, and it never stops. Ever. A billion years could pass, and that vortex would still be spinning exactly as fast as the day you started it. Because in this state, friction has vanished. The atoms are moving in such perfect unison that they don't rub against each other. They flow like ghosts passing through a wall. It gets stranger. If you leave a cup of superfluid sitting on a table, the liquid will not stay in the cup. It will climb the walls. A thin film of atoms, driven by quantum curiosity, will creep up the side of the glass, go over the rim, and drip down the outside until the cup is empty. It is a liquid that defies gravity. It is a liquid that flows uphill. This is what happens when the chaos of the world is stripped away. We tend to think of nature as messy, but deep down, nature craves order. The superfluid is the universe's dream of perfection, a flow without effort, a motion without loss. As you lie here, stillness settling over you, imagine your own thoughts becoming like that superfluid. The friction of the day is gone. The resistance is gone. Your thoughts are no longer bouncing around like hot atoms. They are cooling. They are merging. They are becoming a single, smooth stream, flowing effortlessly toward the ocean of sleep. You are climbing out of the container of the waking world, spilling gently over the edge into the dark. Chapter 11. The Forever Flow. We remain in the cold, but now we turn our gaze to a wire, a simple thread of metal. In the waking world, sending electricity through a wire is a struggle. Electrons try to move, but they crash into the atoms of the metal. They get scattered. They generate heat. This is called resistance. It is the tax we pay for energy. Every time you turn on a lamp, some energy is lost to the heat of the struggle. But in the deep quantum cold, a truce is called. In certain materials, when the temperature drops, the electrons, those lonely, antisocial fermions, do something unexpected. They find partners. They form pairs, called Cooper pairs. It is a delicate romance. They are not touching. They are often thousands of atoms apart, but they are linked. They move together, and when they pair up, they stop acting like fermions. They start acting like bosons. They join the choir. Suddenly, the resistance vanishes. The electrons stop crashing into the metal. They glide through the lattice like a phantom train floating above the tracks. This is superconductivity. Imagine a ring of this wire. If you start a current flowing in it, that current will flow forever. You could unplug the battery, walk away, come back in 1,000 years, and the electricity would still be circling undiminished. It is a perpetual motion machine, permitted by the laws of quantum mechanics. This is the forever flow. It is the closest thing to eternity we can build. And this state has a shield. A superconductor does not just carry electricity perfectly, it rejects magnetism. If you place a magnet above a superconductor, it will not touch the surface. It will hover. It will levitate in mid-air, locked in place by invisible quantum hands. This is called the Meissner effect. It is a quiet insistence on purity. The superconductor says, "I am a perfect state, and I will not allow the magnetic field to disturb me." We use this magic today. Inside the giant MRI machines in hospitals, there are coils of superconducting wire, bathed in liquid helium, carrying massive currents without a whisper of heat. They create the magnetic fields that see inside your body. The image of your brain, your heart, your bones. It is made possible by the forever flow. There is a peace in this concept. We spend so much of our lives fighting resistance, fighting traffic, fighting deadlines, fighting our own worries. But nature shows us that there is a state where the struggle ends. There is a path of moving that requires no force. There is a path where the energy you give is never lost. Let yourself find that path now. Imagine the nerves in your body relaxing. The signals from your brain to your muscles are slowing down, smoothing out. There is no resistance in your body, no tension in your shoulders. You are a superconductor of calm. The peace flows through you, looping round and round, protecting you from the noise of the outside world. You are hovering, levitating in the safe, cold silence of the quantum night. Chapter 12. The Quantum Morning. We have been far. We have been down to the grain of the universe. We have spun with the electrons. We have floated in the fields. We have frozen in the deep cold. But now the journey circles back. We must rise from the basement. We must drift back up, layer by layer, toward the surface. As we ascend, the atoms begin to wake up. The superfluids evaporate into gas. The Bose-Einstein condensates break apart into individuals again. The superconductors warm up, and the resistance returns. The ghosts of tunneling settle back into solid walls. The fog of uncertainty sharpens into the furniture of your room. You are back, but you are different, because now you know what lies beneath. When you wake up tomorrow and the sunlight hits your face, you will know that it is not just warmth. It is a rain of photons, born from quantum tunneling in the heart of the sun, flying as waves across the void and collapsing into particles the moment they touch your skin. When you pick up your phone to check the time, you will know it is not just a machine. It is a sculpture of quantum mechanics. The transistors inside are guiding electrons through quantum tunnels. The GPS is listening to atomic clocks that tick to the rhythm of energy steps. The screen is glowing with the quantized light of LEDs. You are holding the strangeness of the universe in your hand. When you look in the mirror, you will see a being made of stardust and fields. You will know that the atoms of your body are vast cathedrals of empty space, held strong by the exclusion of fermions. You will know that you are entangled with the air you breathe and the ground you walk on. You will know that deep down, in the quiet hum of yourselves, you are vibrating with the same energy that birthed the stars. The world of the day looks solid, it looks separate, it looks simple, but you know the secret. You know that underneath the mask of the classical world, the dream continues. The particles are still spinning, the waves are still flowing, the web is still connected. The magic didn't go away just because you woke up. It is weaving the reality of your life moment by moment. So, sleep well, traveler. You do not need to understand the math. You do not need to solve the equations. You are the equation. You are the solution. You are the wave that has decided for a brief, beautiful moment to be a person. Drift now. The fields are holding you. The spin is rocking you. The vacuum is humming its lullaby. And the universe is watching over you, entangled and whole. Good night.
Hello, and welcome back to the Midnight Scientists. Tonight, the journey we begin is a slow, gentle descent into a curious and often misunderstood part of ourselves. We are going to explore the vast and quiet landscape of a single mind, not in its busy waking hours, but in the soft unraveling of the day, as the world begins to turn down its volume. We are here to talk about a paradox, a kindness, a subtle art that is as fundamental to being human as breathing itself. We are going to explore the quiet grace of forgetting. Chapter 1: The Quiet Unraveling. Imagine, if you will, a single moment, a quiet, mundane moment that happened just this morning. Perhaps it was the feel of a warm mug in your hands, or the way a curtain filtered the morning light, or the fleeting scent of rain on a distant street. Where is that memory now? Has it already begun to fade? Was it ever even truly captured at all? Most of us think of forgetting as a failure, a flaw in the system, an embarrassing lapse in our perfect digital-like brain. But what if it's not? What if the ability to forget is not a bug, but a beautiful, essential feature, a form of self-preservation, a way for the mind to sift through a torrent of information, keeping only the gold and letting the river of irrelevant data flow gently past? In our waking lives, we are constantly bombarded. We are walking through a world of sensory chaos. The thousands of faces we pass, the number plates on the cars, the precise tone of a voice in a crowded room, the exact placement of your keys on a different day than today. If our brains kept every single one of those moments, every single one of those irrelevant facts, where would there be room for new ideas? Where would there be space for a new feeling? We would be collectors of chaos, weighed down by an infinite archive of unpolished trivia. Instead, our minds are more like gentle gardeners, And in this great garden of consciousness, every memory is a seed. Some seeds grow into great, sprawling trees reaching for the sky. These are the powerful moments, the joyous occasions, the life-altering conversations that remain with you for a lifetime. But many others are just small, fleeting things, the weeds that pop up and then disappear. And your mind, with a quiet, patient wisdom, prunes the garden. It keeps the strong branches, the beautiful blossoms, and lets the weeds return to the soil. So as we begin to drift, imagine this nightly pruning, the silent work that your mind does as you relax and breathe. It is not just resting, it is tending to the garden, deciding what to water and what to release back into the dark. It is a necessary ebb and flow, a soft dance between holding on and letting go, a dance that keeps us from being buried by our own pasts. And with that thought, let us settle in. Perhaps let the day's worries drift from your mind. Just as the brain lets go of what no longer serves it, we too can release the thoughts that no longer help us. Take a slow, deep breath and let the story begin. We will start at the very beginning with a simple, foundational question. What is a memory, truly? Chapter 2, The Architect of Whispers. Visualize a single luminous star in the deep, velvety blackness of the night. It is a lonely light, shimmering with a fragile energy. Now imagine that next to it, another star flickers into being, and another. Soon, thousands of stars populate the void, not in a perfect pattern, but in a vast, sprawling, ever-shifting cloud of light. This is not a picture of the cosmos. This is an image of your mind. The 86 billion neurons inside your skull are not a neat filing cabinet, but a living, breathing constellation. And a memory, at its very core, is not a file, but a connection. It is the electrical whisper that passes between two of these starlit cells, the brief, shimmering dance of chemical messengers across a tiny, invisible gap. This is the truth of remembrance, not a solid record, but an ever-changing network, a web woven from electricity and time. Let us begin with the quiet mechanics of this celestial city. Every experience you have, from the simplest act of seeing a face to the complexity of a late-night thought, is translated into a pattern of activity. Your neurons fire in response to a stimulus, sending a tiny electrical signal down a long, slender arm called an axon. At the end of that arm is a synapse, a small junction where the message must leap across a void, like two hands almost touching. And to make that leap, the message transforms. The electrical signal triggers the release of microscopic chemical messengers known as neurotransmitters. These gentle purriers float across the synapse, finding a home on the next neuron and continuing the chain of communication. It is a marvel of biological engineering, a world of microscopic conversations happening in the quiet, dark spaces of your mind. But the real magic lies not in the message itself, but in the path it takes. The first time a signal travels this route, it's like a brand new trail through a dense, quiet forest. The way is overgrown, the passage slow, but every time that same pattern of neurons fires together, every time you revisit that face or remember that smell or recall that feeling, the path gets a little clearer, a little wider, a little smoother. This is the principle of synaptic plasticity. The very connections that hold your memories are not fixed. They are living, adaptable, and wonderfully pliable. The more something is repeated, the more emotionally charged it is, the more likely the neurons are to strengthen their bond. Scientists have a simple, elegant phrase for this: neurons that fire together, wire together. It is the brain's poetic way of saying that practice doesn't just make perfect, it makes permanent. It's how the trail becomes a path, and the path over time becomes a highway. This subtle architecture is the foundation of your inner world. Everything from the taste of your morning coffee to the name of your childhood best friend exists because of these microscopic connections. Your mind, in this way, is not a simple container. It is an artist, a sculptor, constantly molding and reshaping itself in the gentle flow of experience. And as we continue to drift, we might wonder about these ever-changing memories. If they are so fluid, so alive, where do they live? Do they exist in different spaces? Drift with me now as we explore the different layers of this magnificent system. Chapter 3: The Library of Now and Then. Imagine that your mind is a grand, ancient library, but one that is not quiet or still. This library is a constant hum of activity, filled not with dusty books, but with living, breathing scrolls of light and sound. And within this library, there are many different rooms, each with its own rhythm and its own purpose. The first room you enter is the most ephemeral. It is known as the sensory memory. This is not a library at all, but a momentary photograph, a brief whisper that lasts for mere fractions of a second. If you've ever looked at a bright light and then, closing your eyes, still seen its afterglow for a moment, that is this room at work. It is the fleeting echo of perception, the ghost of a sensation that your brain captures before deciding if it is even worth keeping. Most of the echoes here vanish as quickly as they appear. Next, you walk into a smaller, more active space. This is the room of short-term memory. Think of it as a mental sticky note, a small notepad where information can be held for a few seconds or a minute at most. This is where you might hold a phone number you've just heard or a grocery item you've just been asked to remember. This room is not designed for long stays. It is a temporary holding area, a brief but valiant guardian of fleeting information before it either slips away or is invited into a deeper part of the library. It is always active, always in motion, and its purpose is simply to keep the present moment intact, just long enough for you to act. And a quiet sibling to short-term memory lives right next to it. This is working memory. If short-term memory is a mental sticky note, then working memory is your brain's kitchen counter. It's the place where you juggle information, where you do mental math, or follow a set of directions. It's not just about holding on to a piece of information, it's about manipulating it, sorting it, and using it to solve a small, momentary problem. It is a small, cluttered, and constantly used space. It is where you think, and as soon as the problem is solved, it clears itself out, making space for the next thing. Now we drift toward the heart of the library. This is the deep, silent archive of your life. This is long-term memory. It is a place of incredible vastness and surprising durability. Here you will find everything from the memory of a childhood birthday party to the name of your fifth-grade teacher. This archive is not a vault. It is a living, breathing system that evolves with you. It is a collection of stories, a series of lessons, a tapestry of moments that define the narrative of who you are. Long-term memory is so immense, it is often softly divided. There's the part that stores facts, like knowing that Paris is the capital of France. This is semantic memory. And then there's the part that stores your personal history, like remembering the very first time you saw the Eiffel Tower in person. This is episodic memory. One is knowledge, the other is experience. And finally, tucked away in the shadows of this grand archive are the memories that you possess without even realizing it. The knowledge of how to ride a bicycle, how to tie your shoes, how to brush your teeth. These are implicit memories. and they do not require conscious thought. They are woven into your muscles and your habits, living in deep, silent neural circuits that operate on their own below the surface of your awareness. They are the quiet magic that allows you to simply do. In a way, your mind is a beautiful contradiction. A momentary flash, a fleeting thought, a vast, unending archive, and an unconscious flow of habit. All of it is held together by the same delicate, dynamic dance of electricity and chemistry. As we drift and ponder this great library, we might begin to wonder, what makes some books last forever while others vanish into dust?
Chapter 4. The Painter with a Shaky Hand. Drift with me now into a quiet truth. Your memories are not perfect photographs. They are not pristine recordings sealed in a glass jar. They are more like paintings, constantly being touched up, recolored, and reshaped by an artist. And sometimes this artist has a slightly shaky hand. We like to believe that when we remember, we are simply pulling a pristine file from the archives and putting it back. But the truth is far more wonderfully messy. The act of remembering is, in itself, an act of creation. Every time you bring a memory to mind, you don't just recall it, you rebuild it. And in that moment of reconstruction, it becomes malleable. It is open to subtle change. Scientists have a name for this process: reconsolidation. It's the idea that a memory, once retrieved, must be saved again to be stored. It's like opening a digital document, making a few small edits, and then hitting save. Sometimes you might add a detail from a conversation you had 5 minutes ago. You might subtly shift the emotional tone based on your current mood. You might even, without realizing it, add a detail that never happened at all. Think of it like this. You tell a story about a summer long ago. The first time you tell it, the details are a bit fuzzy, but each time you recount the tale, you refine it. You polish the best parts, you add a punchline here, a poignant moment there. The story gets better with each telling. Your memory works in the same way. It is a story retold and reshaped each time you revisit it. The version of the memory you have today is not the memory of the original event. It is the last version you remembered. This is why, in gentle ways, our memories can be so wonderfully unreliable. That time you were certain your best friend wore a yellow shirt to a party, it might have been green all along. The feeling that a moment lasted a lifetime, when in fact it was only a few minutes, your emotions simply painted it in a different light. The brain, in its quiet wisdom, is not a camera, it is a painter. It creates a version of reality that feels solid and true, even though it is constantly being changed. This process is not random, of course. It is guided by an intricate orchestra of brain regions working in concert to shape and store your experience. In the quiet depth of your mind, there is a small, curled creature with a charm of its own. It is the hippocampus. Named after the Greek word for hippocampus, this little organ acts like a librarian, helping to organize and transfer memories from the short-term holding area to the long-term archive. It does not store memories itself, but it is essential for the creation of new ones. Damage to this small structure, as we have seen in certain cases, can make it nearly impossible to form lasting memories. Then there is the prefrontal cortex, the logical, quiet part of your mind that helps with organization and retrieval. Think of it as the executive assistant of memory, calmly sorting through the information. And nearby is the amygdala, an almond-shaped cluster of neurons that is a great emotional storyteller. The amygdala adds color and emotional charge to your experiences.
It is why memories stamped with strong emotions of fear or joy or sorrow often linger with a kind of powerful, almost unsettling vividness. They have been sealed with a kind of emotional ink. And finally, behind the scenes are the cerebellum and basal ganglia, the quiet keepers of your habits. They hold the memories of how to walk, how to whistle a tune, how to tie your shoes. They are the quiet masters of motion, living in the depths of your mind, doing their important work without a thought from you. So when you consider what a memory is, it is not one single thing. It is a symphony of systems constantly tuning and retuning themselves. From the flash of a firefly on a summer night to the melody of a song from your childhood, your memories are a patchwork of sensations, emotions, and stories, all stitched together by electricity and time. It is humbling, isn't it? The brain does all of this, mostly without your awareness. It is constructing a version of reality that feels solid, even though it is constantly, gently, wonderfully changing. Now, as we feel the quiet pull toward deeper relaxation, let us turn our attention to the great mystery that haunts us all, the quiet and curious nature of forgetting itself.
Chapter 5. The Gentle Filter of the Mind. We often think of forgetting as something that happens to us, a slip, a blank moment, an unintentional vanishing of once important information. But what if forgetting isn't a passive failure at all? What if it is a purposeful, active, and necessary process, a gentle filter that keeps the mind from becoming a chaotic, overflowing mess? Imagine your brain as a great ancient forest. In this forest, every thought, every memory, every tiny piece of information is a new branch growing on a tree. Early in life, and especially in your youth, the forest is a tangle of wild growth. The branches are dense and thick with possibility. Your brain creates a massive number of connections, most of which are temporary, exploratory, and not particularly useful. This wild overgrowth is what makes early learning so fascinating, but also so inefficient. But as you grow and experience the world, your brain begins a process of quiet, patient editing. It begins to prune. This process is called synaptic pruning. It's the mind's way of trimming back the less used branches to strengthen the ones that matter most. If a neural pathway isn't used regularly, the brain decides it's not worth keeping. The connection weakens, and the information quietly fades. It is an elegant system. By getting rid of the noise, the signal becomes clearer. This pruning is what makes your brain more efficient as you age. It helps you focus and respond more quickly to the things you truly need to know. It's the difference between trying to run through a dense jungle and walking down a clear, well-trodden path. But pruning isn't the only mechanism at play. There's also a process that adds to the gentle fade. For a long time, scientists believed that the adult brain stopped producing new neurons entirely. But that idea has been quietly overturned. We now know that in certain regions of the brain, like the hippocampus, new neurons can and do form, even in adulthood. This process is known as neurogenesis. And here's the curious part. Some researchers believe that the birth of these new neurons may contribute to forgetting. When new neurons integrate into an existing circuit, they can sometimes disrupt older pathways. Think of it as a subtle remodeling of a room. You might add beautiful new furniture, but in the process, you may have to move or discard what was already there. The brain is always adapting, and sometimes adaptation requires letting go of old information. Then there is decay theory, one of the oldest and simplest explanations for forgetting.
It's the idea that memories fade over time simply because they aren't accessed. Like a path in the woods that gets overgrown with weeds, a memory that isn't revisited becomes harder to reach. The brain isn't actively deleting anything, the connections just weaken with disuse. Out of use, out of mind. And on the more purposeful side of things, there are the quiet housekeepers of the mind, tiny cells called glial cells that act like the brain's sanitation crew. A specific type, known as microglia, roams around, detecting and helping to dismantle unnecessary synaptic connections. When they find something no longer useful, they help break it down and remove it. This process of cleanup is especially important during sleep, as the brain goes through the day's experiences and decides what's worth keeping and what can be quietly swept away. So in many ways, forgetting is a form of exquisite artistry. It is an intentional, purposeful process that serves a vital purpose. It keeps your mind from being overwhelmed. It allows you to live in the present. It protects you from carrying around every password you've ever used, every minor embarrassment from third grade, or the detailed history of what you had for lunch 6 weeks ago. It is your brain's quiet wisdom. It is the pause between notes that gives the music its rhythm. It is the background blur that helps the subject come into focus. Drift with me now and let us explore a fascinating piece of this puzzle. A pattern of forgetting so predictable, a man decided he could measure it. Chapter 6. The Forgetting Curve and the Power of Spaced Repetition. There is a certain moment we all experienced. You meet someone new, shake hands, smile politely, and hear their name, say Mike or Sarah. You nod, repeat it once in your head, and then, less than 30 seconds later, it is gone. You can remember the smile, the shirt, perhaps even their oddly firm handshake, but the name is lost to the breeze. This is not a personal failing. You are not uniquely forgetful. In fact, you are gloriously, beautifully average in your forgetting. And that is exactly what a man named Hermann Ebbinghaus figured out over 140 years ago. Hermann Ebbinghaus was a German psychologist with a rather ambitious goal: to measure forgetting. He was tired of philosophical speculation. He wanted numbers, data. He wanted something he could point to and say, "Here, this is how quickly a memory fades." With admirable, if slightly masochistic dedication, he became a one-man memory laboratory. Using himself as the sole test subject, he began memorizing long lists of nonsense syllables, things like Baz, Zid, and Guk, words with no inherent meaning and therefore no emotional hooks to cling to. He would study a list, test himself after a delay, and record how much he could still recall. He repeated this process hundreds of times across different intervals for months on end. What he discovered was quietly revolutionary. Forgetting does not happen at a constant rate. Instead, it drops off sharply soon after learning, and then the rate of forgetting slows down and levels out. This pattern became known as the forgetting curve. In simple terms, we forget a lot very quickly, and then the rate of memory loss tapers off. Let's bring this to life with a gentle, hypothetical example. Say you learn 10 new vocabulary words in a foreign language today. According to Ebbinghaus's findings, within 20 minutes, you might forget almost half of them. After an hour, you might be down to just 4. By the end of the day, maybe 2 remain, if you are lucky. This steep initial drop is your brain's way of testing what really matters. If you don't return to the information, your brain assumes it's not important. And honestly, it is a pretty smart system. You are exposed to an overwhelming amount of new input each day. Holding on to everything would be like trying to carry every single item from a grocery store in your arms without bags. Eventually, something has to drop. But here's where the story gets hopeful. Ebbinghaus also discovered a wonderful counterintuitive truth. Review helps. If you revisit the information before it vanishes entirely, the curve resets. And each time you relearn it, your memory holds on to it a little longer. This is the principle of spaced repetition. It's the idea that you can revisit information at increasing intervals can dramatically strengthen your long-term retention. Spaced repetition is like watering a plant at just the right moment before it wilts. Do it too soon, and you are wasting effort. Wait too long, and you have lost the memory entirely. But hit that sweet spot just as your memory begins to fade, and you revive the knowledge and reinforce the connection. This is the science behind countless study methods, from language apps to old-fashioned flashcards. They are all built on this simple, elegant idea that you can work with your forgetting rather than against it. Understanding the forgetting curve can be oddly comforting. It reminds us that forgetting is not a sign of failure. It is an expected, predictable, and necessary part of how the mind works. Your memory is doing what it is supposed to do, protecting you from information overload, adapting to what matters most, and giving you a chance to learn smarter rather than harder. And the best part is that this knowledge gives you a quiet power. You can build rituals of review. You can give your brain the gentle nudge it needs to strengthen connections at just the right time. So if you forget something small, just remind yourself that it's not you. It's Ebbinghaus. He'd be proud. As we continue to drift, let us consider another source of forgetting. Not a simple fading, but a kind of cosmic traffic jam in the mind. Chapter 7. The Problem of Too Much Noise. Imagine your brain as a vast, chaotic library. Not the quiet kind with polished wooden desks, but the sort where new books are constantly being added, removed, shuffled around, and occasionally 2 books with identical covers get placed right next to each other. In this library, memories are the books. And as you try to place a new book on a shelf, the one next to it might slide over and push it out. Or worse, you reach for a familiar title, but it's been quietly replaced by something similar but entirely wrong. This is the nature of interference. It's not that your brain is forgetting information entirely, it's that other similar memories are elbowing their way into the spotlight and hogging the attention. Interference is one of the most common and frustrating causes of forgetting. It's what happens when memories compete for space and access. And just like 2 people trying to talk at the same time, things can get muddled. There are 2 main types of interference, each with its own particular style of chaos: proactive and retroactive. Let's start with proactive interference. This is when old information interferes with your ability to learn or recall something new. Imagine you've had the same phone number for 10 years. You finally get a new one, and for the next few weeks, every time someone asks, you instinctively blurt out the old digits. That's proactive interference in action. Your brain is so well trained on the old number that it automatically serves it up, even when it's no longer accurate. The neural pathway for the old number is a well-trodden, smooth highway that your brain is used to driving down. The new number, by contrast, is still a gravel road, half-built and riddled with potholes. So when it comes time to recall, your brain takes the faster, easier route, even if it's wrong. On the other side, we have retroactive interference. This is when new information interferes with your ability to remember old information. Let's say you just changed your email password. A few days go by, and suddenly you can't, for the life of you, remember the previous one. You used it for years, typed it hundreds of times, but now that it's been replaced, it's vanished into the mist. That's retroactive interference. The new memory has overwritten or at least obscured the old one. This happens because your brain is constantly updating and reorganizing. It wants to stay current. But in doing so, it sometimes places newer memories on top of older ones, like saving digital files with the same name. The original might still be there, buried in the depths of your mind, but accessing it becomes more difficult. Both types of interference are more likely to occur when the memories in question are similar. Learning Spanish after years of studying Italian? Expect some cross-linguistic confusion. Meeting a new colleague named Mark when your old coworker was also named Mark? Prepare to say the wrong last name at least once. It's not that you're careless, it's just that your memory system is trying to manage overlap with limited shelf space. The good news is that interference isn't inevitable. Your brain naturally uses, and you can consciously adopt, strategies to reduce its effects. One of the most effective is context separation. If you study similar subjects in different environments or at different times of day, your brain is more likely to keep them distinct. Even small differences in setting can help reduce confusion. Sleep also plays a key role. During rest, your brain not only consolidates memories, but also helps untangle overlapping information. If you're feeling overwhelmed by new learning, one of the best things you can do, ironically, is nothing at all. Just close your eyes and let your brain do its behind-the-scenes organizing. Interference is a sign of a working, learning, and adapting brain. The very act of forming new memories means you're creating the potential for conflict. That's not a flaw. It's a side effect of being a constantly evolving human. Your brain doesn't store memories in neat, isolated folders. It weaves them into a rich, overlapping, and wonderfully complex network. Sometimes the threads get tangled, but overall, it's a system designed to adapt and respond to the patterns of your life. So if you forget your new PIN and accidentally punch in the old one at the ATM, just smile and blame it on interference. Your brain has good intentions. It's just a little crowded up there. Chapter 8: The Silent Gatekeeper. Imagine walking into a room and realizing for the 5th time this week that you've completely forgotten why you went in. You stand there, baffled, gazing at a light switch as if it might hold the answer. Eventually, you wander back out, slightly annoyed and not the least bit surprised. It's not a memory failure, it's an attention failure. Memory begins with attention. It is the brain's first gatekeeper, the quiet bouncer at the club of consciousness, deciding which experiences get past the velvet rope and which get turned away at the door. Without attention, memory doesn't stand a chance. At any given moment, your senses are flooded with data. The subtle hum of a refrigerator, the faint scent of laundry detergent, the temperature of the air on your skin. It's all being registered, but you're not aware of most of it. And more importantly, you won't remember most of it. That's because your brain is highly selective. It filters out the majority of incoming information and allows only a fraction to pass into your conscious awareness. And from there, an even smaller portion makes it into memory. This is where attention comes in. Attention is the mechanism that tells your brain, this is important, store this. Without that signal, the information fades, often before it even gets properly encoded. You simply can't remember what you never really noticed in the first place. Take, for example, the common phenomenon of daydreaming while reading. You sit down with a book, turn the pages diligently, and after several paragraphs realize you have absolutely no idea what you just read. The words went in, but your attention was elsewhere. Perhaps you were thinking about dinner or an awkward conversation from earlier. Whatever the case, your focus drifted and the content never made it into memory. This isn't just a reading issue. It happens during conversations, movies, and commutes. Whole sections of life can disappear simply because your mind was somewhere else. Then there's multitasking, the arch nemesis of good memory. We like to think we're great at juggling tasks, texting while cooking, scrolling while watching television, answering emails during meetings. But this science says otherwise. Multitasking is largely a myth. What we're actually doing is rapid task switching, moving attention back and forth between activities. And every time we switch, there's a cost. That cost comes in the form of reduced encoding. When your attention is divided, each task receives less cognitive bandwidth. You're more likely to make errors and more likely to forget details. Multitasking doesn't just reduce performance in the moment, it creates weaker memories for everything involved. Interestingly, not all distractions come from the outside world. Internal distractions, your own thoughts, feelings, and mental to-do lists, can be just as disruptive. You might be sitting in a quiet room trying to concentrate on a task and find your mind spinning off into unrelated directions. This is sometimes called mind wandering, and while it can be creatively useful, it's a surefire way to reduce memory formation. What's especially fascinating is that attention and memory are deeply intertwined in the brain. The prefrontal cortex, responsible for higher-order thinking and focus, works closely with the hippocampus, the memory maker. When you pay close attention to something, these regions coordinate, enhancing the chances that the experience will be encoded and stored for future retrieval. But when attention is thin, scattered, or constantly shifting, the hippocampus doesn't get a strong enough signal. The result? Fragile memories that are prone to fading or never form at all. There's a gentle truth worth embracing here. You don't have to remember everything. Part of attention's job is to prioritize. You can't focus on every detail of every moment, and your brain doesn't want you to. What it offers instead is a curated version of reality, an edited highlight reel based on what you attend to. So the next time you forget why you walked into the kitchen, don't worry. It's not that your memory failed, it's that your attention was doing a bit of creative pruning. And maybe, just maybe, that trip into the other room was never really about getting something at all. Maybe it was your brain's way of saying, hey, let's go stretch our legs and forget something together. Drift with me now as we ponder what a life of perfect, flawless memory might be like, and why that might not be the gift we imagine it to be.
Chapter 9. The Burden of Total Recall. It is a tempting fantasy, isn't it, to have a perfect memory, to never forget a name, a birthday, a face, or a single detail of your life. Every conversation intact, every pleasant afternoon cataloged and polished like a museum exhibit. No lost keys, no forgotten appointments, no mystery bruises with unknown origins. Just a pristine, searchable archive of everything you've ever seen, done, or felt. And yet, in reality, such a memory might be more of a burden than a blessing. We are told by popular culture that forgetting is a kind of failure, a defect to be overcome. But the truth is, forgetting is not only normal, it is essential. A perfectly functioning memory, well, it might drive you quietly bonkers. There is, in fact, a rare condition that gets close to this idea of perfect memory. It's called hyperthymesia, or highly superior autobiographical memory. Individuals with hyperthymesia can recall nearly every day of their lives in astonishing detail. Ask them what happened on a random Tuesday in October 2 decades ago, and they'll tell you the weather, the clothes they wore, what they ate for lunch, and maybe even what song was playing on the radio. It's not something they have to study or rehearse. The memories are simply there, vivid and immediate. At first, this sounds incredible. Who wouldn't want such a talent? But for many people with hyperthymesia, it's far from a superpower. It can be overwhelming. Memories intrude uninvited, vividly, and relentlessly. Some describe it as being constantly pulled into the past, unable to let go of old wounds or embarrassing moments. If someone hurt your feelings in high school, you may feel that sting just as sharply today as you did then. The memory doesn't fade or soften. It stays bright, clear, and loud.
and this highlights a crucial point. Forgetting is not just something we tolerate, it is something we need. It is the mind's way of making peace with the past, of turning down the volume on moments that no longer serve us. Without it, we would carry every mistake, every awkward pause, every painful conversation like emotional luggage we can never put down. Your memory is not designed to be perfect. It is designed to be useful. Your brain doesn't aim for a flawless historical record. It aims to help you survive, adapt, and focus on what matters most. That means emphasizing patterns, not details, themes, not transcripts. Take, for example, your daily commute. You probably don't remember every car you passed or every pedestrian who crossed the street. What you do remember are the things that stood out: the sudden honk, the coffee spill, the squirrel that nearly got flattened but miraculously survived. That's your memory doing its job. It filters the mundane and highlights the meaningful. Without this selectiveness, we'd be overwhelmed by information. Our brains would be cluttered with irrelevant details, making it harder to spot important patterns or make decisions. Even creativity benefits from forgetting. Some of the most original ideas emerge not from perfect recollection, but from misremembering, from merging concepts in new ways, from filling in forgotten gaps with fresh imagination. If you remembered every source, every quote, every influence exactly, you might never synthesize them into something new. Forgetting creates space for invention. So, the next time you forget where you parked, or why you opened the fridge, or the name of that actor in the movie with the boat and the dramatic music, try not to be too hard on yourself. Your brain is not broken. It's just doing what it was built to do, remembering what matters most and letting the rest gently fade. Now, as we drift deeper, let us explore the most profound and sometimes sorrowful aspect of forgetting: the role it plays in grief and emotional healing. Chapter 10: The Mercy of a Fading Heartbeat. Grief is one of the most universal human experiences, yet also one of the most uniquely personal. It can arrive as a quiet ache or as a tidal wave that knocks the wind from your lungs. It may feel like something is missing or like everything is too present. Time slows, words feel heavy, and memories, especially those tied to someone you've lost, take on a kind of unbearable clarity. In the midst of that intensity, forgetting might seem like a betrayal. The thought of a face softening, a voice becoming harder to hear, or a little quirk slipping away can feel like losing the person all over again. But here is the quiet truth: forgetting, at least in part, is also what allows us to keep going. It's not betrayal. It's the brain's version of mercy. When someone we love is gone, the memories attached to them become emotionally charged. The brain holds on tightly. The amygdala, already an expert in flagging emotionally significant events, keeps these memories vivid, especially the painful ones. The hippocampus, responsible for storing and retrieving these moments, becomes flooded with cues, songs, photos, places that bring those memories rushing back. In the early stages of grief, this is intense. A single scent or phrase can bring tears in an instant. The memory is sharp, alive, and unrelenting. That's because the loss is still recent, not just in time, but in emotional space. Your brain hasn't yet learned how to carry it. It hasn't found the right container. Over time, something gradual begins to happen. The pain, while still present, starts to lose its jagged edge. The memories become less intrusive. They're still there, but they no longer punch quite so hard. This isn't forgetting in the sense of losing. It's forgetting in the sense of softening. The brain is learning how to hold on differently. This process is partly emotional, but also deeply neurological. The brain is constantly reshaping its networks in response to experience. it adapts. The fading of emotional memories is the neurobiology of resilience. It's not about erasing pain. It's about gradually reducing the emotional voltage of a memory. The charge goes down, even if the memory remains intact. That's why you might eventually be able to talk about someone you've lost without crying, or even with a smile. It's not that you have forgotten them, it's that your brain has done what it does best. It has adapted for survival. Interestingly, grief isn't only about emotional pain. It involves working memory too. In deep grief, working memory often falters. People report feeling foggy, disoriented, or forgetful. They lose track of time. They reread paragraphs without absorbing a word. It's not a failure. It's a reflection of how much energy the brain is investing in emotional processing. Like a computer running too many programs at once, the system slows down. But eventually, the capacity returns. And when it does, the memories remain, but they no longer crowd out the present. They no longer demand center stage. That's a gift in itself. The ability to remember someone without becoming undone every time you do. None of this means forgetting is easy. There can be a fear attached to it. The fear of losing a connection, of dishonoring the memory, of moving on too far, too fast. But letting go isn't the same as letting someone disappear. You can carry a memory differently and still carry it fully. In fact, many people find that forgetting certain details allows them to hold on to the essence of a person more clearly. The broad strokes remain: the laughter, the kindness, the love. The specifics, exact dates, exact outfits, exact conversations, fade gently into the background, but what mattered most shines brighter. The ability to forget in grief allows life to expand again. It makes room for new memories, for joy to return without guilt, for laughter to coexist with loss. And that perhaps is the most generous thing the brain offers. Not erasure, but equilibrium. The gift of forgetting in grief is not that it makes us love less, it's that it lets us continue to love while living. It allows us to speak of the person we miss without collapsing, to carry them forward not as a wound, but as part of the story. And in that way, forgetting becomes something quiet and noble. Not a flaw, not a betrayal, but a gentle release, a softening of sharp edges, a grace note in the melody of remembrance. Drift with me now and let us consider how this quiet act of forgetting can also be a profound source of creativity and innovation.
Chapter 11. The Space for Invention. Creativity is often painted as the realm of memory's opposite. As if to be imaginative, one must leave knowledge behind and frolic freely in the fields of nonsense. But in truth, creativity and memory are deeply entangled. Memory provides the ingredients: images, experiences, associations. Creativity is what happens when you mix them in new ways. And in that mixing process, forgetting plays a surprisingly vital role. To imagine something new, the brain needs room. Room to reshape old ideas, to connect distant dots, to wander down unfamiliar paths without tripping over every single thing it already knows. If memory held on to every fact and framework with an equally strong grip, your thinking would be rigid. There would be no room for reimagining the familiar or bending the rules. You'd be stuck inside a mental box, inspecting its corners rather than questioning its shape. This is where forgetting comes in, not as a flaw, but as a creative tool. By loosening the hold on fixed memories and automatic associations, the brain creates space for insight. It makes it possible to see with fresh eyes, to solve problems in unconventional ways, to stumble into the unexpected. Consider the phenomenon known as functional fixedness. It's a mental bias where people struggle to see objects being used for anything other than their intended purpose. If you need to prop open a door and all you have is a book,
Your ability to do so depends on whether you can momentarily forget that the book's primary function is to be read. If you're too tied to that purpose, too anchored in memory, you might not see it as a doorstop at all. This is one reason why young children are often so wildly creative. Their memories are less cluttered with conventions. They haven't yet learned all the correct uses for things. Give a child a spoon, and they might stir with it, wear it as a hat, use it as a catapult, or declare it a royal scepter. Their imagination isn't hemmed in by too much prior knowledge. And while we can't unlearn what we know, we can allow some of it to blur at the edges, to forget just enough to see things differently. This is the heart of divergent thinking, the ability to generate multiple solutions to a single problem. Divergent thinking depends not just on what you remember, but on how flexibly you can manipulate those memories. Can you set aside what's typical? Can you mix ideas from unrelated domains? Can you forget the expected in favor of the unusual? There's research to support this. Studies have shown that individuals who demonstrate greater creative thinking often show a reduction in activation in certain memory-related brain areas during problem solving. This doesn't mean their memories are poor, far from it. It means their brains are less constrained by past patterns and more open to novelty. One especially interesting idea in this space is called cognitive disinhibition. It's the tendency to let more information into consciousness, including things most people might filter out. People high in creative achievement often show greater cognitive disinhibition. Their brains are less rigid in screening out irrelevant thoughts or associations, which can lead to surprising and original ideas. There's also the matter of incubation, that curious process where stepping away from a problem can lead to insight. You've probably experienced it. You wrestle with the task, get nowhere, take a walk or sleep on it, and suddenly the solution appears. It's not magic. It's the brain letting go of rigid pathways. During rest or distraction, your mind may forget the stuck frame you were using and allow alternative routes to surface. Letting go, quite literally, makes room for creativity. Even dreams, those surreal nighttime narratives, may be a playground for creativity fueled by forgetting. During REM sleep, the brain accesses memories and concepts, but it does so with reduced logic and less filtering. This is why dreams are often bizarre, but occasionally insightful. Your brain is making connections it might never allow during waking life because the usual rules, the usual memories, are just out of reach. Great works of art, scientific breakthroughs, clever inventions, they often come from people who've managed to forget something important. Forget what's been tried. Forget what's considered impossible. Forget how things are supposed to be done. These are acts of productive forgetting, letting go of the obvious to make room for the original. Of course, memory still plays an essential role. Creativity builds on experience. But the magic happens in how you rearrange what you know, in the gaps, in the fuzziness, in the moments when the mind lets go of one thing just long enough to reach for another. So the next time your mind feels blank or a bit jumbled, maybe don't rush to fill it with facts. Let it float. Let it rest. Let it forget. You might be clearing just enough space for a new idea to land. Creativity isn't just about brilliance or talent. It's about freedom. And sometimes freedom begins with forgetting what you were told was true and imagining what else might be possible. Now, as our journey nears an end, let us consider what happens when the delicate balance of remembering and forgetting is disrupted. What can we learn from those for whom memory has become a source of profound confusion and loss? Chapter 12. The Fragile Tapestry of Self. Memory is usually so seamless, so automatic, that we rarely notice it at all.
It follows us around, filling in the blanks, reminding us where we left our shoes, nudging us with déjà vu, carrying the scent of childhood through a bakery door. It's only when memory falters, when it bends, warps, or breaks, that we truly begin to understand how miraculous and delicate it really is. Memory disorders pull back the curtain on this quiet marvel. They show us what happens when the systems of remembering and forgetting stop playing nicely. They reveal just how much of our identity, our continuity, and even our reality depends on memory behaving itself. One of the most widely known memory disorders is Alzheimer's disease. It's a neurodegenerative condition that slowly, relentlessly erodes memory and cognitive function. In its early stages, it often presents as mild forgetfulness, losing track of dates, misplacing objects, repeating questions. But over time, it moves into deeper territory, forgetting names, faces, and even the threads of one's own story. The brain physically changes, with the buildup of amyloid plaques and tau tangles disrupting the connections between neurons and eventually killing them. What's especially striking about Alzheimer's is how it peels memory back in reverse. Recent memories vanish first, what you had for breakfast, the conversation you just had, while older memories often stay intact for longer. It's like watching the chapters of a book disappear, starting from the end. In many cases, long past events are recalled with eerie clarity, while the present dissolves in real time. A person might vividly recount a school dance from 60 years ago while forgetting where they are or why they're holding a spoon. This reversal provides a window into how memory is stored. It suggests that newer memories are more fragile, more dependent on the hippocampus, while older memories, having been consolidated and distributed across the cortex, are more durable, at least for a while. Then there's amnesia, a condition that often comes with a cloud of cinematic drama, but is in reality varied and complex. Amnesia isn't one disease, but a symptom that can result from head injury, stroke, or psychological trauma. It comes in different flavors. Anterograde amnesia is the inability to form new memories after an event. This is what famously affected a man known in the medical literature as HM after undergoing brain surgery to treat epilepsy. HM lost the ability to store new, long-term memories. He could hold a conversation, but a few minutes later, it was gone. Yet he could still learn new motor skills, like tracing shapes in a mirror, even though he had no memory of practicing. This told researchers that procedural memory, how to do things, is handled by different systems than declarative memory, knowing facts and events. Retrograde amnesia, on the other hand, is the loss of memories formed before an event. People may forget years of their lives or even their entire identity. Often, the more recent the memory, the more likely it is to be lost. What these memory disorders show us again and again is that memory isn't a single system. It's a collection of overlapping networks and processes. You can lose one type of memory and retain another. You can remember how to play the piano, but forget that you ever owned one. You can recognize a face, but forget a name, or vice versa. They also remind us how little we still understand. Despite decades of research, we're still unraveling the basic mechanisms of memory storage and retrieval. We don't know exactly why some memories vanish while others persist. We can't fully explain why one traumatic event is forgotten and another is etched in perfect detail. We do know that memory is deeply tied to identity. When memory breaks down,
It's not just information that's lost. It's context, continuity, the story of who we are. And yet, even when memory fails, the essence of a person often remains. There's something more than memory that holds us together. Something quieter, perhaps, but no less real. These disorders challenge the idea that memory is about truth. The mind doesn't record life like a camera. It edits, distorts, forgets, and sometimes imagines. Even in health, memory is fluid. It bends with emotion. It shifts with time. What matters is not perfect recall, but meaning. So if you ever forget where you left your phone or struggle to recall the name, take comfort in this. Your memory system is doing something far more complex than simply storing data. It's building a narrative, shaping your identity, balancing emotion, and keeping you grounded in time. And even when it stumbles, it still holds remarkable power. For to remember is human, but to forget, in all its strange and surprising ways, might just be as important. Drift with me now, one last time, as we summarize the quiet wisdom of forgetting and bring our journey to a gentle close.
Chapter 13. The Grace of an Empty Hand. We often think of forgetting as something broken, an embarrassing lapse, a failure of attention, a sign that the brain isn't doing its job. But what if it's the opposite? What if forgetting is not only natural, but vital to a healthy, functioning mind? The more we learn about memory, the clearer it becomes. A forgetful brain is not a flawed brain. It's a beautifully efficient, ever-adapting system doing exactly what it was designed to do. Forgetfulness, in many cases, is not about loss. It's about letting go. It's the brain saying, you probably don't need this anymore, and quietly removing clutter to keep things running smoothly. If you remembered every detail of every moment, your mind would be a chaotic mess, a noisy warehouse full of unfiled receipts, ancient grocery lists, and every glance, whisper, and pebble you've ever encountered. Not very useful. Instead, the brain forgets strategically. And in doing so, it protects you, focuses your attention, and creates space for the new. At its core, forgetting is a form of filtration. Throughout the day, your senses take in far more information than your conscious mind can handle. Colors, movements, words, smells, sounds, all flowing in at once. Your brain has to filter what matters from what doesn't. If you notice everything, you remember nothing in particular. Forgetting helps streamline perception and sharpen focus. It lets you zoom in. Forgetting also supports decision-making. Imagine walking into a supermarket and remembering every brand of cereal you've ever seen, every advertisement you've ever heard, and every breakfast you've ever eaten. You'd be paralyzed in the breakfast aisle. Forgetting helps you prioritize. It removes the noise so the signal stands out. This is especially clear when you consider working memory, the short-term system that allows you to hold and manipulate information in real time. It's your mental workspace, and it's limited. You can only juggle so many ideas at once. Forgetting the irrelevant ones keeps the space clear for what you're actually trying to do. And it goes deeper. Forgetting protects your emotional well-being. When painful memories soften with time, it's not weakness, it's survival. The sting of a breakup or the embarrassment of a mistake eventually subsides. It's not that you've forgotten the event entirely, it's that your brain has dialed down its emotional volume, allowing you to live in the present. This doesn't just happen by accident. Research shows that certain neural pathways actively support forgetting. Proteins like RAC1 are involved in weakening synaptic connections, those little bridges between neurons that help store memories. The brain builds them up when it learns something new, but it also knows when to tear them down. Synaptic pruning, the process of trimming unused or outdated connections, happens throughout life. Like a sculptor removing excess clay, your brain refines itself by subtraction. This selective forgetting isn't about losing memories.
It's about optimizing them. The strongest memories tend to be those that are meaningful, emotional, or frequently revisited. The rest, they're archived or gently released. Think of a library. You don't need every book ever written on the front desk. You need the ones relevant to today. The rest are in storage, or replaced, or recycled. Not gone, just not cluttering your workspace. And here's something else. Forgetting helps creativity. If your brain held onto every fixed rule and familiar solution, it would struggle to think outside the box. By letting go of rigid associations, you create room for fresh combinations, original insights, and imaginative leaps. It's forgetting that loosens the mental grid and allows for new connections to form. Even everyday forgetfulness, the kind that makes you wonder where you put your glasses, which are often on your head, has a practical explanation. These lapses often occur when attention is split. The brain, efficient onto a fault, doesn't encode information unless it's flagged as important. If you're thinking about dinner plans while absent-mindedly placing your keys on the counter, your brain simply doesn't register the moment. It's not broken, it's prioritizing. There's even evidence that forgetting helps maintain a coherent sense of self. If you remembered every contradictory thought, every passing impulse, every shift in mood, your sense of identity might become fractured. Forgetting helps you weave a story about who you are. Not a perfect story, but a meaningful one. And yes, there are times when forgetting hurts, when names slip, when facts blur, when something you wanted to remember fades too quickly. But those moments are the exception, not the rule. Most of the time, forgetting is not the absence of memory. It's the refinement of memory. It's worth embracing this idea, especially in a world where we're constantly trying to remember more. Apps, alerts, calendars, reminders, we're outsourcing memory as fast as we can. And while these tools are helpful, they also suggest that remembering everything is ideal. But nature doesn't agree. The brain, in all its quiet wisdom, forgets on purpose. So the next time you blank on a detail, don't be too hard on yourself. Chances are your brain is just making room for something more useful, or clearing out emotional static, or nudging you to stay in the present instead of getting lost in the past. There's beauty in a forgetful mind. It's focused, it's adaptable, it knows what to keep and what to let go. And in a world overflowing with information, that may be one of the most valuable skills of all. Forgetting isn't failure, it's efficiency, it's protection. It's the brain being selective in the best possible way, filtering the noise, highlighting the signal, and gently, quietly allowing you to live not with a perfect record, but with clarity. After all, life isn't about remembering everything, it's about remembering enough. Enough to learn, to grow, to connect, and enough to let go, to forgive, to rest. What a journey it's been, wandering through the tangled forests of memory, pulling back the curtain on how the brain decides what to hold on to and what to let gently fade. We've explored forgetting not as a failure, but as a feature, not a crack in the foundation, but a form of quiet brilliance. Memory is not a filing cabinet. It's alive. It reshapes. It forgets on purpose. And in doing so, it gives us the freedom to change. The freedom to not be bound by every painful detail, every outdated rule, every single thing we ever thought or learned. Forgetting allows for forgiveness, for creativity, for peace. It's how we sleep soundly at night, how we move on after heartbreak, how we make room in our minds for the things that matter most. It forgets the color of the socks you wore on a random Tuesday so you can remember how it felt when someone made you laugh in the middle of a hard week. It forgets the irrelevant to spotlight the meaningful. It forgets where you put your keys, but remembers the melody your grandmother hummed. And sure, it forgets appointments and to-do lists from time to time, but it also forgets pain. It forgets fear. It forgets grief just enough to let you breathe again. Forgetting is not your enemy. It is your brain doing what it must, sorting through the noise, lightening the load, and offering you the grace of a little less weight to carry. And maybe that's the most important takeaway of all. Forgetting is a part of being human, an elegant, necessary part. Not a hole in the story, but the pause that gives it rhythm. Not an erasure, but an evolution. It's how the brain edits life into something livable, how it clears space, not just for memories, but for meaning. So as we bring this story to a close, let's circle back to where we began, with a question or two. Where are you listening from? And what time is it in your corner of the world right now? Whether it's morning or midnight, I hope this journey has helped you unwind. I hope it hasn't been too interesting, though if it kept you awake, at least you've learned something. And if by tomorrow you forget some of the details, that's okay too. It was designed to do just that, letting go gently. Good night, and may your mind find quiet rest. Hello, and welcome back to our quiet corner of the cosmos. As the world outside grows still and the moon begins its slow climb through the sky, we will embark on a new kind of journey tonight. A journey not into the heart of a burning star, but into the gentle, quiet embrace of the cold. Tonight, we will drift toward the edge of the universe's great shiver, a place where heat is a distant memory and time moves with the patience of starlight. Take a moment to settle in. Fluff your pillow, find a comfortable position, and let your body soften. Close your eyes if you like, and simply listen to the sound of my voice. Imagine a small, warm place within you, perhaps just behind your ribs, a gentle glow of energy, a slow and steady hum. That is your core, your own private star. All of life, all of motion radiates from a place like this. Now, with your eyes closed, visualize a single drop of morning dew on a blade of grass. It sparkles like a tiny lens, a miniature universe of its own. Look closer. On the molecular level, this seemingly motionless drop is alive with silent activity. Its water molecules are in constant, frantic motion, bumping and spinning and dancing in a chaotic, invisible ballet. This restless dance is heat. The more they dance, the more energy they hold. The more energy they hold, the warmer they feel. This is the first, most fundamental truth of our journey. Heat is motion. Now, imagine that same dewdrop as the sun sets and the air cools. The frantic dance of the molecules begins to slow. The bumping becomes a gentle nudge, the spinning a slow, lazy turn. The vibrations calm, the wild energy softens, and the drop begins to solidify, to freeze. When the movement has all but ceased, when the particles are locked into a rigid, crystalline lattice, we call that cold. In science, we've learned that cold isn't really a thing at all. It is simply the absence of motion, a space where the music has faded and the dancers have stood still. The cold you feel when you step outside on a winter's night is your body, your little inner star, losing its heat to the still outer air. It isn't cold invading you, it is your warmth slowly leaving. It's a transfer of energy, a quiet sigh from the hot to the cold. Like a crowd leaving a theater, heat races out of you all at once. Your body simply registers the absence and names it cold. And we measure this absence in different ways. Most of us are familiar with the Celsius scale, where water freezes at 0 degrees and boils at 100 degrees. A scale that feels clean, symmetrical, and intuitive. Or perhaps you live in a place that uses the Fahrenheit scale, where water freezes at 32 degrees and boils at 212 degrees. A more idiosyncratic system, perhaps, but one with its own sense of rhythm and reason. But in the quiet places of the universe and in the deep rooms of science, we use a different scale, the Kelvin scale. The Kelvin scale is the universe's own language for temperature. It doesn't bother with the arbitrary freezing or boiling points of water. Instead, it starts at the beginning, or rather, at the end, at the ultimate stillness. It starts at absolute 0. This theoretical point, which is 0 Kelvin, or roughly minus 273.15 degrees Celsius, is the temperature at which all molecular motion ceases completely. A kind of perfect, motionless quiet. A place so cold that atoms would no longer dare to shiver. A temperature that we believe does not exist naturally anywhere in the universe in its pure form. So, as we begin the slow drift toward the frozen edge of reality, let this idea settle into your mind. Cold isn't an enemy. It isn't a thing that is. It's the name we give to a state of being, a state of profound rest and stillness. It is the end of the dance, a gentle pause button pressed on the microscopic jittering of all things. Drift with me now away from the warmth you know and toward this gentle quiet. We'll leave the familiar heat behind, the molten cores of planets and the searing surfaces of suns. We'll travel slowly, gently, to where the air itself has lost its fever and where the very fabric of space is holding its breath. Our journey begins with a single slow step toward the universe at its most still. A place that challenges what we think we know about warmth and motion. The kind of place you might find in your dreams. Chapter 2. The Cosmic Thermometer. Let's continue our slow descent into the silent, chilly depths of the universe. In our last moment together, we spoke of the Kelvin scale, the one that starts at the ultimate stillness of absolute 0. To truly appreciate its meaning, we must first understand the vastness of the universe's full temperature range. It's a spectrum that spans more than 15 million degrees, from the unimaginably hot to the nearly non-existent cold. It's on this grand scale that our quiet journey begins to make sense. Imagine for a moment the hottest fire you can think of, perhaps the molten lava of a volcano, fresh from the Earth's heart, glowing at around 1200 Celsius. This is a dramatic kind of heat, full of destructive energy and brilliant light. But it is only a lukewarm puddle in the grand scheme of things. Now let's drift much hotter, past the chemical fires of Earth and toward the grand inferno of our sun. On the sun's surface, the temperature swells to an incredible 5500 Celsius. But go deeper still into the sun's core, and things reach a staggering 15 million degrees. At this point, heat is so intense that atoms can no longer hold on to their electrons. Hydrogen atoms are smashed together to form helium in a process we call nuclear fusion, and this is the heat that gives our sun its light and our world its warmth. Most of the universe, however, prefers a much cooler demeanor. As we begin to slide down the scale, we leave behind the scorching heat and pass through the comfortable middle ground where life, as we know it, thrives. We drift through the warmth of a summer's day at a pleasant 30 Celsius, past room temperature, and through the core temperature of your own body, a perfect balance at around 37 Celsius. Everything still feels familiar here within this narrow, cozy band. Keep descending with me now. We pass the freezing point of water at 0 Celsius and glide into the sub-zero air of winter mornings. At this stage, the molecules around you are moving so slowly that they begin to lock together, forming the delicate, symmetrical crystals of ice. As we go even lower to around -70 Celsius, a place that is colder than Antarctica on its most frigid days, things start to feel otherworldly. And if we drop further to a bone-chilling -196 Celsius, we find a place where nitrogen gas turns to a liquid, a substance so cold it can shatter a rose like glass. Below that, we enter the true realm of our journey, the cold of space. The deep emptiness between stars and galaxies is not just dark, it is filled with an almost perfect stillness. The temperature of this deep void hovers at a frigid 2.7 Kelvin. This is the temperature of the cosmic microwave background, the faint, gentle afterglow of the Big Bang itself. It is a whisper from the very beginning of time, a background hum of heat that still permeates the universe, setting a universal floor for temperature. You can't naturally find a cosmic location any colder than this. It's a base hum of warmth that the cosmos has never quite managed to shake. Now we approach our theoretical endpoint, absolute zero. At 0 Kelvin or -273.15 Celsius, all motion would cease. No jittering, no vibration. A kind of perfect, utter stillness. It is the finish line of the temperature race, a boundary that physics tells us we can approach but never fully reach. Why? Because the third law of thermodynamics states that to cool something to absolute zero, you would need to expend an infinite amount of energy. The closer you get, the more effort it takes. It's a mathematical and physical wall that stands as a testament to the universe's natural resistance to perfect stillness. But even if it's impossible to reach, the journey toward it has revealed some of the strangest and most beautiful secrets. At temperatures just a tiny fraction of a degree above absolute zero, atoms behave in totally bizarre ways, forming new states of matter and showing us a world governed by the strange rules of quantum mechanics. So as you rest, imagine the stunning range of this cosmic thermometer, from the raging heart of a star to the silent, frigid void between galaxies. And right in the middle, in that narrow band of gentle warmth, is you, tucked in, safe, and breathing. Our tiny familiar slice of existence is nestled between two grand extremes. The cold is not an empty absence, but a presence with its own unique rules. It's a place where energy fades and a new, more elegant form of physics begins to take shape. And the coldest places in the universe, it turns out, are a quiet, reassuring reminder that even the deepest voids follow a grand and beautiful order.
Chapter 3. The Boomerang Nebula. Drift with me now far from the familiar heat of our solar system toward the southern skies. Picture a place 5,000 light-years from Earth.
nestled somewhere in the direction of the Centaurus constellation. It's here, in the cold, unblinking vacuum of deep space, that we find a truly extraordinary cosmic oddity, the Boomerang Nebula. Nebulae are often places of dramatic endings and new beginnings. Some are the fiery birthplaces of stars, where clouds of gas and dust swirl together, pulled by the relentless hand of gravity. Others are the quiet cemeteries of the cosmos, the shimmering shrouds left behind by stars that have lived long, burned bright, and finally let go. The Boomerang Nebula is one of the latter. It's what astronomers call a planetary nebula, a term that, despite its name, has nothing at all to do with planets. It is the breathtaking final breath of a dying star. What makes this particular nebula so uniquely, astonishingly cold is its temperature. At just 1 Kelvin, or around minus 272.15 Celsius, it is colder than the lingering afterglow of the Big Bang, colder than the background temperature of space itself. And this is where the quiet paradox of the Boomerang Nebula begins to reveal itself. Space is already incredibly frigid, sitting at a baseline of 2.7 Kelvin. This faint hum of heat is a constant presence, the last echo of the universe's fiery infancy. So how can anything, especially a dying star, get colder than the very vacuum it floats in? The answer lies in the slow, powerful sigh of the central star. In its twilight years, this star began to shed its outer layers, but it did so in a rapid and spectacular fashion. It expelled gas at a staggering speed, over 500,000 kilometers per hour. When a gas expands rapidly into a vacuum, it cools down dramatically. It's the same principle behind your refrigerator, or the reason a spray can of air duster feels icy to the touch. As the gas spreads out, its energy is dispersed over a greater volume, and the temperature plummets. In the Boomerang Nebula, this effect is taken to a cosmic extreme. The expansion is so fast and so unimpeded that the gas cools far below the temperature of the surrounding cosmic microwave background. The nebula itself becomes a shield, an icy cocoon that blocks the faint warmth from the Big Bang's afterglow, allowing its core to descend into a realm of utter frost. When it was first discovered in the 1980s, astronomers noticed something odd. It was emitting far less radiation than they expected, a clear sign that it was cold. Later, sharper images from the Hubble Space Telescope revealed a beautiful hourglass shape, a cosmic butterfly made of pure frost and mist. Jets of frigid gas blasting outward from the central star formed symmetrical wings, a quiet testament to the slow, precise physics of a stellar farewell. This entire frigid display is temporary. As the gas continues to expand and thin out, the shield will weaken. The faint warmth of the cosmic background will eventually seep in, and the Boomerang Nebula will slowly, inevitably warm back up to the common cosmic chill of 2.7 Kelvin. For a brief cosmic moment, a fleeting oasis of stillness, it holds the record for the coldest naturally occurring place we have ever found. There's a deep poetry in this. Stars are supposed to burn, to radiate, to flood the cosmos with light and energy. Yet here, a dying star creates not a blaze of glory, but a magnificent exhalation of frost. It doesn't rage or roar, it sighs, and that sigh freezes into a magnificent shroud of silence. It is a beautiful paradox, a farewell made in frost, rather than fire. Imagine standing within it if you could. There would be no sound, no sensation, no feeling of cold, for your body would disintegrate long before you could register the stillness. It would be the closest you could ever come to standing inside a whisper, a moment where motion and heat have almost completely vanished, leaving behind a magnificent, silent monument to a star's final breath.
Chapter 4: The Voice of the Past. Let's continue our journey. Leaving the Boomerang Nebula to its temporary stillness, we now float in the deepest, emptiest regions of space, far from the warmth of any star. Here, the temperature settles at a baseline so profound and so ancient that it holds a secret to the universe's past. Long before galaxies spun themselves into graceful spirals, before stars began to twinkle their steady light, the universe was a hot, dense, chaotic soup. It was a place of blinding, seething energy with no cool air and certainly no silence. But as time unfurled its long ribbon, this fiery blaze began to expand and to cool. A blink of a moment in cosmic time, just 380,000 years after the Big Bang, the universe had expanded enough and cooled enough for a major transformation to occur. Atoms could finally form. The wild, free-roaming electrons settled into calm orbits around protons, creating the first neutral hydrogen atoms. This seemingly simple event had a profound consequence. The universe became transparent. For the first time, light could travel freely without constantly bouncing off a chaotic fog of particles. And that light, the very first light of the universe, is still traveling. We call it the cosmic microwave background, or CMB for short. It is the oldest light in the cosmos, a faint afterglow from a time when everything was still young and unformed. It is everywhere, all around you, all the time, a quiet, gentle hum. The temperature of the CMB is an extraordinarily chilly 2.725 Kelvin, just a hair above absolute zero. In terms of energy, it's barely a whisper, a trace of what once was, but because it fills all of space, it is significant. It represents the minimum natural temperature of the universe. It's the base hum of warmth that the cosmos has not yet managed to shake, a constant reminder of our fiery origins. It's a peculiar thing to think about. This ancient light, older than any star or galaxy you can see, has been stretching and cooling for over 13 billion years. As the universe expanded, the wavelengths of this light stretched right along with it, moving from the fiery, visible spectrum all the way down to the long, low-energy microwaves we detect today. If the universe hadn't expanded, this relic light would still be blazing in ultraviolet or X-rays. Instead, it has cooled in rhythm with space itself, like a memory that has faded to a gentle echo. The story of its discovery is one of those delightful accidents that make science so magical. In the 1960s, two radio engineers, Arno Penzias and Robert Wilson, were working at Bell Labs. They kept encountering a mysterious static in their equipment, an unexplained noise that came from every direction, no matter where they pointed their antenna. They tried everything to get rid of the interference, but the noise persisted. What they had accidentally stumbled upon was the cosmic microwave background itself. It wasn't noise from Earth, it was the soft sound of the universe's infancy, reaching into their antenna from across the vast emptiness of time and space. For their serendipitous discovery, they were awarded the Nobel Prize. Since then, scientists have been mapping the CMB with ever-increasing precision. The maps show a sky filled with faint blotches of warmer and cooler regions, like ripples on a fine sheet of silk. These subtle temperature variations, no larger than 1 part in 100,000, were the seeds of everything.
They were the subtle gravitational imperfections that eventually drew matter together, giving rise to galaxies, clusters, and the very structures that make up the universe we see today. It's like reading the baby pictures of all of existence. Because this radiation fills space so evenly, it acts as a kind of cosmic nightlight, a soft, steady glow that has never turned off. It is the light of the universe, frozen in time, stretched and softened, but never quite extinguished. We are literally bathed in the light of the early universe. The atoms in your body, the air you breathe, the warmth in your blanket, all of it exists against this ancient backdrop. It's not romanticized poetry, it's physics. The cosmic microwave background may not dazzle the eye like a shooting star or a glowing nebula, but its stillness is profound. It is the canvas upon which the rest of the cosmos was painted, a gentle echo from the dawn of time, still whispering across the void. It reminds us that sometimes it's the quietest things that carry the deepest stories.
Chapter 5: The Chill of Interstellar Voids. As you rest now, imagine drifting further from home, past the faint, ancient glow of the cosmic microwave background, and into the vast, sprawling stillness between galaxies. This is intergalactic space, a profound and beautiful emptiness that stretches for millions of light years at a time. It is a place where warmth is a rumor and matter is almost non-existent. Here, in the most isolated regions of the universe, you would find a silence so complete it would be terrifying if you could truly experience it. The temperature settles to an almost perfect 2.7 Kelvin, a direct consequence of the universe's ancient light. But what is more remarkable than the cold itself is the sheer lack of anything to feel it. Intergalactic space is not truly empty, but it is as close as we can imagine. A cubic centimeter of air you're breathing right now holds trillions upon trillions of molecules. In the deepest intergalactic void, that same volume might contain just 1 or 2 atoms. It is a sparseness that defies our comprehension. You would have to scoop up a volume of space the size of a planet just to gather enough material to make a human-sized pinhead. And yet, in its quietest corners, this cosmic emptiness isn't entirely without activity. The cold, it turns out, is a key ingredient for one of the universe's most patient and profound transformations. Tucked away in the spiral arms of galaxies like our own Milky Way lie immense, shadowy regions called cold molecular clouds. These are the nurseries of stars. They are not warm, glowing places, but rather the opposite. Their temperatures can fall as low as 10 Kelvin. They're made mostly of hydrogen molecules, along with dust particles and traces of other complex molecules. The dust is crucial here. It acts like a cosmic blanket, shielding the gas from the radiation of nearby stars and keeping it cold. Without this deep chill, the atoms would move too fast, too chaotically, to ever come together and form the complex molecules needed to build a star system. In these frigid, dark clouds, atoms move gently, softly. They bump, they cling, and they slowly begin to build. Over millions of years, gravity works its magic, drawing these sparse particles into denser and denser pockets. As a pocket of gas and dust grows, it begins to collapse inward, slowly heating up as it does. Over time, that collapse creates enough pressure and heat to ignite a star. The cold, it turns out, is a necessary precursor for fire.
For something as fiery and bright as a star to be born, you first need a place that is still and cold. These clouds are so cold that they are invisible to our eyes. They absorb and scatter visible light, appearing as dark smudges against a backdrop of stars. We can only detect them using radio telescopes, which pick up the faint emissions of the molecules within. It is a slow, quiet work, a glacial choreography of chemistry. Molecules like formaldehyde, methanol, and even the building blocks of amino acids are slowly, patiently forming on the backs of tiny dust particles. It's a beautiful contradiction. The coldest, most desolate places we can find are also the most hopeful. The chill of interstellar space isn't an ending, it is a beginning. It is the necessary background for stars to shine brighter, for galaxies to swirl more dramatically, and for planets to feel more alive. Without the cold, there would be no contrast, no edge to the warmth. There would be no silence to make the music of the universe stand out. So when you think of the emptiness of space, don't imagine a sterile void. Imagine a place of profound potential, quietly assembling the future out of hydrogen, gravity, and silence. In a strange and beautiful way, the coldest places in the universe are also its most pregnant with possibility.
Chapter 6: The Coldest Places on Earth. We've journeyed through the vast, cold expanse of space, from the frigid sigh of a dying star to the quiet birthplaces of suns. But some of the most astonishingly cold environments aren't found naturally in the cosmos. They are crafted right here on Earth, in carefully engineered laboratories where scientists are determined to touch the untouchable and get as close as possible to absolute zero. This isn't your average sub-zero freezer. When you get to temperatures a fraction of a degree above absolute zero, the rules of our everyday world begin to fall apart. Atoms slow down so much that they no longer behave like individual particles. Instead, they begin to blur into the strange world of quantum mechanics, where they act more like waves than solid objects. To achieve this surreal state, scientists have had to develop incredibly clever tools. One of the most elegant methods is called laser cooling. It sounds counterintuitive, doesn't it? Lasers are for heat, for cutting metal and burning through materials. But in the right context, a laser can be used to chill something down. Imagine an atom moving in one direction. If you shine a laser beam at it from the opposite direction, the atom absorbs a photon, which gives it a tiny push backwards. If you repeat this process with lasers from every direction, the atom is essentially stopped in its tracks. It's like gently nudging a bouncing ball until it's barely moving at all. By doing this, scientists can reduce the temperature of atomic gases to just millionths of a degree above absolute zero. To go even further, they use magnetic trapping. Once the atoms are slowed down by the lasers, powerful magnetic fields hold them in place, like invisible tweezers. From there, they use a process called evaporative cooling, which works on the same principle as sweat on your skin. The hottest atoms are allowed to escape the trap, which lowers the average energy and temperature of the remaining atoms. Using these methods in tandem, scientists have achieved temperatures that are measured in nanokelvin or even picokelvin, billionths and trillionths of a degree above absolute zero. And in this realm of unimaginable cold, something truly weird and beautiful happens. The atoms,
no longer behaving as individuals, begin to merge. They lose their separate identities and become one unified entity, a single collective wave of matter. This is a Bose-Einstein condensate, a state of matter so fragile and strange that it was predicted by Albert Einstein almost a century before it was first created in a lab in 1995. It's as if the atoms are marching perfectly in sync, every footstep, every breath unified, a single, serene river of matter. Scientists aren't just doing this to break records. The pursuit of ultra-cold temperatures is a window into the most fundamental truths of the universe. When you remove all the chaotic thermal noise of everyday motion, the subtle whispers of quantum mechanics become clearer. In these labs, we can observe behaviors that are otherwise hidden: superconductivity, where electrons flow with zero resistance; superfluidity, where a liquid like helium flows with no friction, even climbing the walls of its container. This research isn't just for physics textbooks either. It's paving the way for revolutionary technologies like quantum computing, where maintaining this kind of perfect stillness is critical to making the fragile quantum bits work. The cold becomes a kind of magnifying glass for the laws of nature, a tool for revealing the fine print of physics. So while the universe at large prefers a baseline of just under 3 Kelvin, the human mind, with its endless curiosity, is creating places thousands of times colder than anything found in nature. In the quiet chill of these labs, matter shows us what it's capable of when all distractions are stripped away. It is here, in the near-perfect stillness, that the universe whispers its secrets.
Chapter 7: The Physics of Stillness. As we continue our slow drift, let's revisit the surreal behaviors of matter in the deep cold. It's as though the universe, in its frostiest corners, is peeling back its everyday mask to reveal its stranger, subtler self. The rules of physics as we know them begin to stutter, and a new, more mysterious performance takes center stage. To understand this, imagine a bustling street in a crowded city at noon. People are energetic, bumping into each other, each with their own purpose. That's how atoms and molecules behave at high temperatures, a chaotic, energetic jumble. But now imagine that same street late at night, in the deepest hours of a quiet, cold winter. The crowd has vanished. The few remaining people walk slowly, with deliberation. This is a bit like what happens when matter cools. The thermal motion, the noise of the system fades away. And in that quiet, a new kind of order emerges, governed by the precise, elegant rules of quantum mechanics. One of the most dramatic examples of this quantum weirdness is a phenomenon called superfluidity. It occurs in liquid helium when it's cooled to just below 2.17 Kelvin. At this temperature, the helium undergoes a phase transition, but not into a solid. Instead, it becomes a substance unlike any liquid you have ever seen. Superfluid helium flows without any friction or internal resistance. If you set it swirling in a container, it will keep spinning forever with no memory of its motion. Even more bizarrely, it can defy gravity and spontaneously creep up the walls of its container as if it's possessed by some otherworldly spirit of physics. This is possible because the atoms in the superfluid are so perfectly coordinated that they act as a single, unified quantum whole.
flowing as one continuous, coherent entity. There are no individual sloshing parts, just a united wave of matter. A related phenomenon is superconductivity. This applies to electrons instead of atoms. Normally, when electricity flows through a wire, electrons bump into atoms and lose energy as heat, which is why your phone gets warm or a toaster glows. But in certain materials, cooled to just a few Kelvin, electrons suddenly stop resisting. They form pairs and begin to move through the material without scattering. It's like a rush hour crowd that suddenly begins to walk in perfect, choreographed synchrony. There is no traffic, no jostling, just a serene, lossless river of motion. This effect is powerful enough to levitate magnets, trap magnetic fields, and transmit energy with zero waste. It's not just a scientific curiosity, it's a technology that powers MRI machines, particle accelerators, and is a key to developing quantum computers. In these conditions, even time seems to behave differently, not in a science fiction sense, but in the way quantum systems evolve. As the noise of heat fades away, the fuzziness of quantum mechanics becomes more pronounced. Particles can tunnel through barriers they shouldn't be able to cross, and they can occupy multiple states simultaneously. This quantum coherence, the idea that particles can remain in a stable, linked state over time, becomes more visible. It's crucial for quantum computing, which relies on maintaining these delicate states. In a way, extreme cold is a powerful lens through which we can glimpse the fine print of physics. The rules haven't changed, but they are much easier to read when the atoms aren't shouting over each other with thermal energy. It's a kind of cosmic minimalism. At room temperature, matter is messy and complicated, but lower the temperature and complexity gives way to unity. Atoms align, particles merge, and motion becomes a gentle dance instead of a chaotic scramble. It is the universe at its most refined. So, if you ever think of cold as being empty or lifeless, remember this. The deepest magic often requires the quietest stage, and near absolute zero, the universe gives its most elegant performance, revealing its profound, secret life in a state of nearly perfect stillness.
Chapter 8: The Unreachable Goal. For all the incredible feats that modern science has accomplished, splitting the atom, landing robots on distant planets, and decoding the human genome, there is one stubborn boundary we just can't cross, a line we inch toward with ever-increasing precision, yet never quite touch. That boundary is absolute zero, the ultimate stillness, the point where all atomic motion stops. Why? Why does nature hold this particular prize just out of our reach? The answer lies in one of the fundamental rules of physics, the third law of thermodynamics. It may not get the dramatic spotlight like the laws of motion or gravity, but it quietly governs the deep, chilly end of the temperature pool. In simple terms, the third law states that as a system approaches absolute zero, the entropy, or disorder of that system, also approaches a minimum. But more importantly, it implies something very inconvenient. You can't reach absolute zero in a finite number of steps or in a finite amount of time. No matter how clever our cooling techniques become, there will always be some stubborn residual motion you can't quite eliminate. It's like trying to turn off the very last flickering light in a room where the switch keeps moving just out of reach. You can dim it, suppress it, and quiet it down until it's barely glowing, but actually switching it off, it's not going to happen. The problem is partly mathematical. As you cool something closer and closer to absolute zero, the energy you need to remove per degree gets smaller, but the effort required to remove it gets larger.
the system becomes increasingly reluctant to give up that last bit of heat. It's a bit like trying to scoop up every last grain of sand off a beach. You get close, you scoop up almost all of them, but there's always one more hiding in the crevice of a rock. There's also a deep quantum mechanical reason that absolute zero is unreachable. According to Heisenberg's uncertainty principle, you can never know both the exact position and the exact momentum of a particle at the same time. If atoms were to come to a complete stop at absolute zero, you would know both exactly where they are and exactly how fast they're moving, which would be zero. This would break the fundamental rules of quantum mechanics, which doesn't allow for that kind of perfect certainty. So even the most chilled out atom must retain a little bit of jitter, a faint reminder that uncertainty never fully freezes. Despite all this, scientists have come impressively close. Laboratories have chilled atoms to within a few billionths of a degree above 0 Kelvin. At these incredible temperatures, atomic motion slows to a crawl, and entire systems of atoms begin to act as single, unified entities. It's the birthplace of exotic states of matter like Bose-Einstein condensates, where particles merge into one quantum wave. It's truly spectacular, but still not zero. Why does this matter? Because these extreme temperatures help us understand the very foundations of reality. Near absolute zero, matter behaves in ways that are otherwise hidden. The thermal noise of everyday temperatures masks the delicate subtleties of quantum behavior. But when the heat is gone, when motion slows and entropy drops, we get a clearer look at how particles interact, how forces behave, and what matter is capable of when it has nowhere left to hide. So the pursuit of absolute zero is a bit like chasing a mirage. You never arrive, but the journey itself is where the magic happens. And along the way, you start to understand not just how cold the universe can be, but how beautifully strange it becomes when everything slows down. It reminds us that some limits are built into the very fabric of reality, not as an obstacle to be conquered, but as a horizon to be approached.
Chapter 9: The Sentinels of the Void. Deep space is cold. Not a wear a sweater kind of cold, but a deep, unblinking chill that hovers around minus 250 degrees Celsius. It's a place with no air to carry heat, no atmosphere to trap warmth, just an infinite, silent emptiness. And yet, floating through this profound stillness are some of humanity's most delicate and incredible creations, our spacecraft. You might think that keeping a machine cold in space is simple, but the vacuum of space doesn't conduct heat well. There's nothing for heat to travel through. So if you put an object in space, it doesn't immediately freeze. Instead, it slowly radiates its internal heat away. The challenge for engineers isn't just keeping a satellite warm. It's a precise balancing act. Too much heat, and the sensitive instruments will fry. Too little, and lubricants freeze, batteries fail, and electronics stop working. It's like trying to keep a cup of tea warm in the middle of a desert with no air, no fire, and no electrical outlet for millions of miles. So how do we do it? The first trick is insulation. Spacecraft are often wrapped in shiny, crinkly-looking layers of a material called multi-layer insulation, or MLI. If you've seen a satellite, you've seen this gold or silver foil. Each layer reflects thermal radiation, and the multiple layers trap heat like an ultra-light, high-tech sleeping bag, slowing the loss of warmth dramatically. But passive insulation only gets you so far. For missions that venture far from the sun's warmth, like those to the outer solar system, spacecraft need a more robust heat source. This is where radioisotope thermoelectric generators, or RTGs, come in. An RTG is essentially a nuclear battery. It uses the natural heat from the decay of a radioactive material, typically plutonium-238, to generate a steady trickle of both warmth and electricity. With no moving parts, no fuel tanks to worry about, and no need for sunlight, RTGs can last for decades. This is how the Voyager probes, launched back in 1977, are still powered as they drift ever deeper into interstellar space, far beyond where solar panels would be useful. Their tiny nuclear hearts keep beating, sending back whispers from the very edge of the sun's domain. Then there are spacecraft like the James Webb Telescope, a marvel of engineering that wants to be cold. Its instruments are designed to detect infrared light, which is essentially heat radiation. Any warmth from the telescope itself would create noise and obscure its view of faint cosmic signals. To stay chilled, Webb uses a gigantic 5-layer sun shield the size of a tennis court to block light and heat from the sun, Earth, and Moon. This allows it to cool passively to just about 40 Kelvin. One of its instruments is even actively cooled with a cryocooler to bring it down to about 7 Kelvin. It's a cosmic cold front, custom built to peer into the universe's most profound moments. The cold of space is a harsh teacher, forcing engineers to account for materials contracting, lubricants freezing, and components becoming brittle. Traditional grease doesn't work at -200 degrees Celsius. Instead, they use dry lubricants. Cables must be flexible and electronics must be shielded. It's like building a toaster that works inside a freezer the size of the solar system, and then asking it to never malfunction. And yet, in a strange twist, this relentless cold also helps. Without air, there's no corrosion, no weather, and very little degradation from the environment itself. The very vacuum that chills also preserves. The Voyager probes, drifting through interstellar space, may last for millions of years, their records protected in the freezing stillness. The cold is both an enemy and an ally, a threat that also allows for clarity, stability, and longevity. It is a profound paradox that reminds us how resilient and inventive the human mind can be. Chapter 10. The Dream of Cryosleep. There is something undeniably magical about the idea of cryosleep. It's the classic science fiction solution to a very real problem. How do you send people on a journey that takes decades, maybe even centuries, without them aging, going stir-crazy, or running out of food? The answer, in countless books and films, is elegantly simple. You just freeze them. Pop them into a futuristic pod, press a button, and they drift off into a perfectly preserved slumber while their ship cruises through the vast, cold void. But what if this isn't just a fantasy? In the world of biology, suspended animation is not unheard of. Some animals, like the Arctic wood frog, can survive being frozen solid during winter. Their hearts completely stop, their breathing ceases, and their bodies turn into solid ice. Yet, when spring arrives, they thaw out and hop away as if nothing happened. This is possible because their bodies produce a natural antifreeze, a type of glucose that protects their cells from the damaging ice crystals that form during freezing. Nature, it seems, has figured out a few tricks. Humans, on the other hand, are not built for freezing. Our cells are full of water, and when that water freezes, it forms sharp, destructive ice crystals. These crystals puncture cell membranes like tiny daggers, causing catastrophic damage. To get around this, scientists have developed a process called cryopreservation. It involves cooling biological tissue to very low temperatures, usually around -196 degrees Celsius, the boiling point of liquid nitrogen, while preventing ice from forming. This is done with special chemicals called cryoprotectants, which act like antifreeze, replacing the water inside the cells and protecting them from freezing damage.
cryopreservation is already a cornerstone of modern medicine. We routinely freeze and store sperm, eggs, and embryos, and even small pieces of tissue for years. But there's a catch. This process works best with very small, simple structures. Whole, complex organs like a heart or a liver are much more difficult to freeze and thaw without injury. And a whole human body is a problem of immense proportions. The main hurdles are ensuring even cooling throughout the entire body, and then, even more challenging, a safe and uniform rewarming. This hasn't stopped some people from signing up for this technology anyway. Companies offer full body or just brain preservation after legal death, with the hope that future technology will be able to repair the freezing damage and revive the person when science has caught up. It remains a speculative leap of faith, a kind of scientific time capsule filled with frozen hope, because no human has ever been successfully revived from this state. So, what would it take to make cryosleep for space travel a reality? You would first need a way to cool a person to near zero metabolic function without forming ice crystals or damaging tissues. Then you'd have to keep them stable for years, possibly generations, without power failures or system malfunctions. Finally, you'd need to safely rewarm them and fully restore their biological and cognitive functions. Even if all these technical problems were solved, a host of profound ethical questions would remain. If a person wakes up 1,000 years in the future, are they still the same person? What happens to memory, to identity, to the sense of time? And yet, the allure remains. Long-distance space travel is impractical when measured in human lifespans. Cryosleep could, in theory, allow us to explore distant worlds, colonize other planets, or ride out long voyages without consuming endless supplies or going completely mad from boredom. In this way, cryosleep isn't just about freezing bodies, it's about preserving dreams, about tucking ourselves away for a future we hope will be kinder and more advanced. For now, it belongs to the realm of stories, of glowing pods, and a distant, hopeful waking.
Chapter 11: The Icy Hearts of the Solar System. Our own solar system, with all its familiar fiery planets and swirling gas giants, has a quiet secret. It's also home to some of the coldest, most isolated worlds we've ever discovered. These frozen realms don't glow like the sun or sparkle like Saturn's rings. Instead, they lurk in the dark, icy and silent. And yet, beneath their frozen crusts, there might be something astonishing, a glimmer of life. Let's begin our descent with Europa, one of Jupiter's largest moons. At first glance, Europa looks like a ball dipped in a frozen crackle glaze. Its surface is a smooth white shell of ice, etched with long reddish-brown lines that snake across its surface like veins on a marble sculpture. The temperature there is not what you would call balmy. Daytime highs hover around minus 160 degrees Celsius. The surface is a solid, ancient, and brittle shell of ice. But beneath that icy crust, something fascinating is hiding. Evidence suggests that Europa harbors a vast global ocean. This isn't a puddle, it's a deep, possibly saltwater ocean containing more liquid water than all of Earth's oceans combined. And this ocean is kept in motion not by sunlight, but by the powerful gravitational pull of Jupiter. As Europa orbits its immense parent planet, it gets stretched and squeezed, generating internal heat. That warmth is believed to be enough to keep the ocean from freezing solid, creating a potential habitat sealed beneath kilometers of ice. Then there is Enceladus, a small moon of Saturn that punches far above its weight and scientific intrigue. It is tiny,
only about 500 kilometers across, roughly the width of Arizona. But it is one of the most geologically active bodies in the solar system. Its surface is a gleaming white with fractures near the South Pole that vent enormous geysers of water vapor, ice particles, and organic molecules out into space. These plumes shoot hundreds of kilometers above the surface, forming a misty halo that feeds Saturn's outer rings. The average surface temperature is around minus 200 degrees Celsius. But just like Europa, it's believed to have a subsurface ocean kept liquid by tidal flexing from Saturn's gravity. What's even more exciting is that the Cassini spacecraft actually flew through these plumes and detected signs of organic chemistry, the carbon-based molecules that form the foundation of life as we know it. Even farther out lies Pluto, the king of the Kuiper Belt. At a distance of nearly 6 billion kilometers from the sun, Pluto receives less sunlight than a candle in a cave. Surface temperatures plunge to around minus 230 degrees Celsius. And yet, when the New Horizons spacecraft flew past in 2015, the little world surprised us. It wasn't just a frozen rock. It had mountains made of water ice, plains of nitrogen snow, glaciers, and even what looked like a giant heart-shaped region. The images showed a complex surface shaped by ongoing geologic activity. Some scientists believe there could still be pockets of liquid beneath Pluto's crust, slowly freezing, but perhaps not entirely solid just yet. The idea that these cold, distant worlds could harbor life might seem strange. We tend to imagine life in warm, sun-drenched environments. But life on Earth has proven to be surprisingly adaptable. Microbes thrive in the deep ocean where sunlight never reaches. Other extremophiles live in the ice of Antarctica, in acidic lakes, and inside nuclear reactors. Life, it seems, is more flexible than we once believed. On Europa and Enceladus, the combination of liquid water, heat, and organic molecules creates a tantalizing possibility. If hydrothermal vents exist on their ocean floors, like the ones on Earth's seafloor, they could provide the energy and nutrients to support entire ecosystems. On Earth, these vents host vibrant communities of tube worms, crabs, and bacteria, all sustained by chemosynthesis, life powered not by sunlight, but by chemical reactions. The lesson here is profound. Cold doesn't mean dead. The absence of surface warmth doesn't rule out the presence of life. In fact, some of the best candidates for extraterrestrial life in our solar system are not the scorched rocks near the sun, but these distant, icy spheres, sheltered, secretive, and perhaps quietly alive beneath their frosty skins. They are a humbling reminder that our view of life is shaped by our own planet's quirks, and that the real heartbeat of the cosmos could be echoing from places we once dismissed as too cold, too quiet, and too far away. Chapter 12: The Cold, Dark Weaving of the Cosmos. If you've been drifting along on this chilly tour of the universe, you may have come across the term cold, dark matter. It sounds appropriately mysterious and dramatic, like something whispered by astronomers over mugs of black coffee at 2 a.m. And it's a concept that shows up all over cosmology, scientific papers, and even science fiction. But while the name suggests a shadowy substance locked in a state of deep freeze, the reality is both more abstract and more fascinating. Let's start with the dark part. Dark matter isn't dark in the way a shadow is dark. It's dark because it doesn't emit, absorb, or reflect light. It's completely invisible, a ghost to our telescopes. But we know it's there because we can see what it does, even if we can't see what it is. Galaxies rotate in a way that suggests there is far more mass present than we can account for with stars, gas, and planets. Stars at the outer edges of galaxies move faster than they should if all the mass were concentrated near the center. Something is adding extra gravity, something invisible. That something is what we call dark matter. It's the scaffolding that holds galaxies together and shapes the large-scale structure of the universe. So, where does the cold come in? In cosmology, cold doesn't refer to temperature in the traditional sense. It doesn't mean these mysterious particles are frosty or that they'd give you a chill if you could somehow touch them. Instead, cold refers to their speed. Cold dark matter particles are theorized to be non-relativistic, meaning they moved relatively slowly compared to the speed of light in the early universe. This slow motion allowed them to clump together more easily, forming dense knots of gravitational glue that helped galaxies and galaxy clusters form. These clumps acted like seeds, drawing in normal matter, gas, dust, and stars, and giving rise to the cosmic structures we see today. This is in contrast to hot dark matter, which would have been moving close to the speed of light. Particles moving that fast would have smoothed over any small fluctuations in density, making it difficult for galaxies to form. A universe dominated by hot dark matter would look very different, far more empty and homogeneous. Then there's a kind of theoretical middle ground, warm dark matter. Not too fast and not too slow, which could still allow structure to form, but perhaps not in the same way as cold dark matter. The current leading theory, the one that best fits our observations of the universe's structure, is that dark matter is cold, but we haven't found the actual particles yet. They remain elusive. Many candidates have been proposed over the years, from the heavy WIMP, or weakly interacting massive particle, to the ultralight axion. If they exist, trillions of them would be passing through you every second without you ever noticing. What we do know is that dark matter makes up about 27% of the universe's total mass and energy content. That's over 5 times more than all the ordinary matter we are made of. Everything we've ever touched, tasted, built, or seen, all the stars and planets and people, make up less than 5% of the universe. The rest is dark matter and an even stranger thing called dark energy, which means that almost everything in the universe is made of something we've never seen. And yet, this invisible stuff plays a vital role. Without cold dark matter, galaxies wouldn't hold together. The universe would be a much smoother, emptier place. Computer simulations that model cosmic evolution with cold dark matter produce structures that closely resemble the universe we actually observe. Dense filaments of galaxies stretching across space, enormous voids in between, and intricate web-like patterns of matter on vast scales. It's as if the cosmos is knitting itself together with an invisible thread, and cold dark matter is the needle. It's humbling, really. The universe we see, the beautiful, brilliant part with all its light and motion, is just a faint glow riding on top of something vast and unknown. Cold dark matter isn't just about temperature or mass, it's about the parts of reality we've yet to grasp. The silent majority of the cosmos holding everything together from behind the scenes. So the next time you look up at the stars, consider the invisible hand shaping their patterns. It may be cold, it may be dark, but without it, the universe would have no structure at all.
Chapter 13. The Gentle End of the Universe. If the universe had a bedtime story, this would be its final chapter. Not a loud, fiery bang, but a slow, steady sigh. Not a dramatic, meteor-filled apocalypse, but a gentle fading into stillness. This is the theoretical finale of everything, a concept known as the heat death of the universe. And despite its name, it has very little to do with heat as we know it.
It is actually the ultimate cold, a cosmic quietude where everything that could happen already has, and all that remains is a slow, cold unfurling into silence. To understand how we get there, we must begin with the second law of thermodynamics. This rule, which governs how energy moves and transforms, tells us that entropy, or disorder, always increases in a closed system. Left to its own devices, the universe tends to spread out its energy evenly, like sugar dissolving into tea. Over time, differences in energy will even out. Hot things will cool, organized things will decay. Complexity will give way to simplicity. That is entropy's way. Right now, the universe is full of interesting things. Stars are burning, galaxies are colliding, and black holes are munching on the occasional unlucky gas cloud. There's light, warmth, motion, and imbalance, which is just the way entropy likes to play. But this won't last forever. Fast forward a few trillion years, the stars will begin to go out. The big, bright stars burn out quickly, but even the smaller ones, like red dwarfs, will eventually run out of fuel. When the last star dies, it will leave behind a cold, dark remnant, a white dwarf, a neutron star, or a black hole. Over immense spans of time, even the glowing embers of white dwarfs will cool and fade into black dwarfs, radiating no light or heat. The galaxies themselves will grow dim. With no new stars forming and old stars winking out, the night sky will slowly lose its sparkle. The cosmos will become a quieter, darker place. Black holes, once thought to be eternal, will also fade away. Thanks to a prediction by Stephen Hawking, we now believe black holes slowly lose mass through a process called Hawking radiation. They emit tiny amounts of energy over time, shrinking ever so slightly with each passing eon. This evaporation is extraordinarily slow, but given enough time, vastly more time than the universe has had so far, even the largest black holes will fizzle out and vanish into the quantum mist. What will be left? Not much. Some particles, some lonely photons, a smattering of neutrons and protons, drifting through a space that is unimaginably vast and mostly empty. The temperature will have approached absolute zero, hovering infinitesimally above it. At that point, no new stars will ignite, no structures will form, and no work will be done. Every gradient, every imbalance that once drove activity will be gone. This is heat death. Not a sudden collapse or a catastrophic event, but a state of maximum entropy. Everything is evenly distributed and no usable energy is left to fuel change. The universe, still expanding, will contain nothing but a sparse, cold soup of particles and faded radiation. It's a strange name, really. Heat death sounds like it should be fiery and final, but it is more like the gentle dimming into candle that was never relit. In this final stillness, in the cosmic hush that follows eons of light and motion, the story ends. It is not a fiery apocalypse, but a frozen whisper, a sigh of entropy echoing softly across an empty stage. It is a strange and peaceful image, a cosmos that has lived a full, fiery life and now rests in perfect equilibrium. It's a reminder that not all endings are violent. Some come slowly, like winter settling in, not with a roar, but with a hush. The cosmos doesn't rage. It drifts, frozen and eternal.
Chapter 14: The Paradox of Cold. We have traveled a long way together, from the subtle stillness of a freezing dewdrop to the vast, quiet expanse between galaxies. We have seen how the universe measures temperature
and how its laws bend and shift when the heat fades away. Now, as our journey nears its gentle conclusion, let us take a moment to reflect on a beautiful paradox that has appeared time and again throughout our exploration. It is the idea that cold, which we so often associate with absence, death, and decay, is in fact a necessary and creative force, the ultimate enabler of new beginnings. We are, as creatures, biased toward warmth. Our senses are designed to appreciate light and heat. Our bodies require a very specific, narrow band of temperature to function. We see the warmth of the sun as a gift, the glow of a fire as a comfort, and the heat of a volcano as a dramatic, powerful spectacle. Our stories of the cosmos are often stories of fire, of stars burning, of planets being forged in molten rock, of galaxies blazing with light. And yet, this is only half the truth. Go back for a moment to the deepest parts of our galaxy. Picture those vast, dark stretches of interstellar space, the so-called cold molecular clouds. To our eyes, they would appear as nothing, just a void, a smudge of black against the distant stars. But we now know that within those frigid, dusty wombs, new life is being born. The temperature within these clouds can drop to just 10 Kelvin. It is a stillness so profound that gas atoms and dust particles have no choice but to slow down. Their wild, chaotic energy is gone, and they begin to cooperate. They gently collide, clinging to one another, and over millions of years, they assemble the ingredients for a new star. A star that will eventually become a bright, fiery beacon. But that fire would never have existed without the cold that came before. The cold is a prerequisite for creation, a necessary silence before the universe can begin to compose its next song. Think also of the Boomerang Nebula, the majestic, frigid butterfly made of a dying star's breath. It defies our expectations. We anticipate a grand fiery finale. Instead, this star whispers its final secrets in a language of pure frost. And in doing so, it creates the coldest place in the known universe, a place that pushes the boundaries of our understanding. It shows us that endings in the cosmos are not always loud and dramatic. Sometimes they are quiet, elegant, and strangely beautiful. The cold, in this case, is not an end in itself, but a brief, magnificent transition, a final act of grace before the star's material is reabsorbed into the cosmic quiet. And what about our own scientific pursuits? We use extreme cold not to destroy, but to reveal. In the deepest, coldest laboratories on Earth, we don't just cool things down. We peer into the universe's most profound behaviors. We use stillness as a tool, a magnifying glass to see the delicate choreography of quantum mechanics. When we chill atoms to a fraction of a degree above absolute zero, we don't get nothingness, we get something new. We get Bose-Einstein condensates, where matter unifies into a single entity, a serene river of particles flowing as one. We get superconductors, where electricity moves with zero resistance, revealing a perfection of flow we never thought possible. Cold here isn't a force of stagnation, but a key that unlocks a new realm of physics, a place where the universe's underlying elegant patterns are no longer obscured by the loud noise of heat. Even in the search for life, we are being taught a lesson. For decades, we looked for signs of life on planets that were warm, wet, and Earth-like. But now, our most promising candidates lie beneath the icy shells of moons like Europa and Enceladus. We are learning that life may not need the warmth of a sun to begin. It might just need liquid water and a source of energy, even if that energy comes from the gentle tidal kneading of a massive planet. These icy moons, once dismissed as frozen tombstones in the outer solar system, now hold our most profound hope. The cold of their surfaces is a perfect shield, protecting the secrets of their subsurface oceans from the harsh radiation of space, allowing life to possibly flourish in a quiet, undisturbed darkness. The paradox of cold, then, is that it is a force of creation and preservation. It slows time down for living tissue, protects fragile molecules in space, and reveals the hidden architecture of matter. It is the patient artist sketching out the blueprints for new stars in molecular clouds and allowing new states of matter to emerge in laboratories. It is the backdrop against which all warmth and motion must be judged. So as you rest, let this thought settle gently in your mind. The universe is not just fire and fury, light and speed. It is also stillness and patience, darkness and cold. And in those cold and quiet places, some of its most magnificent and unexpected stories are waiting to be told. The universe seems to know something we are only just beginning to grasp. That to create a new kind of beauty, a new kind of order, sometimes all you have to do is turn down the heat.
Chapter 15. The Universe as it sleeps. As our long, quiet journey through the frozen cosmos comes to its gentle close, let's imagine our final destination. A universe fully asleep. This is not a place of chaos or catastrophe. It's not a place filled with crashing planets or screaming supernovas. No, this universe is calm, utterly, infinitely calm. It is the quiet after all songs have ended, a place where temperature, that great driver of motion and life, has settled as close to zero as physics allows. What would it feel like to be there? Not in the human sense, of course, for there are no nerves to tingle, no skin to goosebump, but in the grand abstract shape of things, it would feel still, motionless and silent, but not empty. The galaxies have stopped spinning, the last stars have burned out, the black holes have evaporated into a dusting of radiation so faint it barely registers. What remains are particles drifting in a vast, ever-expanding space with nowhere to go and no energy left to change anything. This is not a frozen hell. It is more like a cosmic whisper, a gentle end, like exhaling after holding your breath for billions of years. In a fully cold universe, entropy has won. Energy has spread itself as evenly as possible, and nothing is left to power change. The background temperature of the universe has cooled to an almost perfect absolute zero. Only the faintest trace of heat remains, the echo of what once was. Could life adapt to this? Could something survive here in this pure stillness? Life, at least as we understand it, is powered by contrast, warm versus cold, high energy versus low. Every living thing on Earth thrives in imbalance. Plants feed on photons from a hot star. Animals shuffle energy around like a cosmic relay race. Life is a tightrope walk of energy exchange. In a universe where temperature gradients no longer exist, where everything is the same everywhere, there is no flow. And with no flow, there is no work. Without work, there is no metabolism, no thought, no life. Even if a life form could somehow perfectly insulate itself and store energy for trillions of years, it would eventually spend that energy, and then it would join the great stillness. And yet,
The idea of a universe without warmth is not entirely bleak. There is a strange elegance in the image, a cosmos that has lived a full, fiery life and now rests in perfect equilibrium. It is not in mourning, it is resting. All the battles have been fought. The stars have told their stories. The galaxies have pirouetted across the void, and now, like dancers after a performance, the universe lets the curtain fall. There's a kind of peace in that. No rush, no noise, just vast, cold space humming ever so gently with the memory of light. We often associate cold with discomfort, with frostbitten fingers and silent streets, but taken to its cosmic extreme, cold becomes something else. It becomes a stage where the deepest truths of the universe can be seen clearly, where heat and light no longer cloud our view, a place where matter becomes minimal and what remains is pure geometry, pure structure, and pure time. It is here that the poetry of physics becomes most profound. In this frozen quiet, we can ask questions without expecting answers. What is the shape of a universe that no longer changes? What does time mean when nothing moves? When there is no heat, no clocks ticking, no atoms vibrating, what becomes of duration? These are not just scientific questions, they are philosophical. They nudge at the limits of understanding. When you think about the cold end of the universe, you're not just thinking about temperature, you're contemplating the nature of existence itself. And still, even in that silence, there is beauty. The symmetry of space stretched across unimaginable distances, the quiet dignity of particles content to drift, the persistence of gravity holding on until the very end. There is something deeply moving about a universe that doesn't rage against the dying of the light, but simply allows itself to cool and rest. It's a reminder that not all endings are violent. Some come slowly, like winter settling in, not with a roar, but with a hush. And yet, even as we imagine this final chapter, we're still here, warm and awake, breathing in a sliver of time when stars still shine and molecules still hum with life. Our tiny planet is perched in a very special moment, a moment when warmth still flows and energy still dances. That in itself is worth appreciating. In the grand arc of cosmic time, our warm, glowing now is brief, precious, and extraordinary. Perhaps that's the most meaningful takeaway from imagining a cold universe. It reminds us how rare warmth really is, how fragile, how beautiful, and how worth cherishing. Because one day, if the theories hold true, warmth will fade. And when it does, the universe will close its eyes, not in sorrow, but in peace. Drift with me now and imagine a world that feels both familiar and far away. It is the year 1977. The air on Earth hums with a quiet tension, a silent standoff between two great powers. But beneath the surface of that global unease, something else is stirring, something entirely different, a gentle and profound curiosity that whispers from the heart of humanity itself. This is a time of clunky technology and bold dreams, of rotary phones and the first flickering digital watches, a time when our television screens were still broadcast in grainy, black and white images of a man bounding across a dusty lunar landscape. We had reached the moon. We had stood on its surface and declared to the universe, we did it. But after that giant leap, a strange quiet settled in. The spotlight of public attention, which had so brightly illuminated the Apollo missions, began to dim. Budgets for space exploration were tightened. The collective breath we had held for so many years was finally released. And with that sigh, a question arose. What now? What's left? The answer was waiting. It had always been there, a silent constellation of giants spinning in the outer darkness, far beyond the familiar orbits of Mars and the asteroid belt. The gas giants, Jupiter, Saturn, Uranus, and Neptune. Worlds so vast, so distant, and so shrouded in mystery that for centuries they had remained little more than blurry points of light in our telescopes. Colossal, mysterious planets encircled by rings of ice, cloaked in swirls of gas, and orbited by dozens of strange, unknown moons. They were beautiful enigmas, untouchable and unseen. But in the quiet corners of NASA, among the engineers and the dreamers, a brilliant solution began to take shape. It wasn't about more power or bigger rockets. It was about patience. It was about a dance that the planets themselves were about to begin, a celestial ballet that happens only once every 175 years. In the late 1970s, those giants of the outer solar system would align in such a way that a single spacecraft, if launched at precisely the right time, could use their gravity to slingshot from one to the next, like a stone skipping across a pond. This was the Grand Tour, a breathtaking vision that in its original form was too expensive to pursue. But the dream didn't fade, it adapted. It distilled itself down to a more modest, yet still breathtaking plan. Instead of a fleet of probes, NASA would launch 2 twin spacecraft, identical in design, built with a simple elegance and a rugged stubbornness. They would be robust, smart, and designed for a journey that was audacious in its scope and poetic in its ambition. These were the Voyager missions. Imagine now a long, quiet room at the Jet Propulsion Laboratory. The air is still, but the minds within it are buzzing with a beautiful kind of noise, the hum of calculation and the murmur of curiosity. Pencils whisper across paper, drawing out trajectories. Scientists debate over the color of a planet's atmosphere. Engineers argue over the thermal shielding needed to survive a journey into the bone-deep cold of deep space. Every wire is a tiny strand of hope. Every piece of code is a whispered instruction. This mission isn't for the cameras or for the headlines. It is a slow, endearing act of faith. And what do you build for such a journey? You build something that must last, something that has no need of flashy screens or powerful microchips, something that is simple enough to survive for decades without a human hand to guide it. A single ship to carry a small, precious cargo, a collection of instruments, and a golden record. The golden record, perhaps the most poetic piece of the entire project. It wasn't a scientific instrument, it was a message, a greeting in dozens of languages, the sounds of Earth, from the laughter of children to the song of a whale, and a carefully selected mixtape of humanity's greatest music. It was a bottle cast into the cosmic ocean, a declaration that said, "We were here. This is who we are." The odds of it ever being found were impossibly small, but that wasn't the point. The point was the gesture itself, the simple, profound act of saying hello to the unknown. So, as we drift deeper into the silence of this story, let the image of that golden record, that tiny shimmering time capsule, settle in your mind. It is a symbol of everything to come. It reminds us that at our core, we are not just a species of fear and conflict, but a species of curiosity and hope, a species that, even in a world full of noise, is capable of a very quiet and beautiful act, the act of reaching out. And with that thought, let us prepare for the beginning of our own journey, for the moment when two quiet ships, built in a long-gone era, stood poised to change the way we see everything. They were destined not to return, but to remind us what it truly means to leave.
Chapter 2. The Architectures of Endurance. Visualize with me now the quiet hum of a clean room, a space so sterile that even the air feels different. It is here that the Voyagers are taking shape, not as sleek, futuristic starships, but as something more honest and resilient. They are built for the long haul, designed in an era when durability was a form of elegance, and a well-placed solder joint was a mark of artistry. The task was clear, but the challenges were immense. This was before the age of smartphones and cloud computing. The engineers at NASA's Jet Propulsion Laboratory worked with slide rules and punch cards, with pencils drawing careful lines on large sheets of paper. They were building something to survive not just a few years, but decades. Billions of miles from home, with no chance of repair, no pit stops, and no second chances. The first challenge was the environment itself. Space is a cold and hostile place, a vacuum filled with this silent thread of cosmic radiation and tiny, fast-moving particles of dust. Voyagers needed to be tough, not fast or flashy, just stubbornly, resiliently durable. The very skeleton of each spacecraft was a sturdy aluminum frame, designed to withstand the violent shudder of launch and the endless silent stress of a journey that would take them far beyond the sun's comforting warmth. From this central frame, the instruments and antennas extended like the delicate limbs of an insect. The most iconic of these was the great white high-gain dish, a graceful 3-meter-wide structure that looked like a satellite TV dish with a dream of the stars. This was to be Voyager's voice, and what a whisper it would be. Even now, more than 4 decades later, Voyager's signal, traveling across unimaginable distances, reaches us with a strength of less than a billionth of a watt. It is a whisper softer than the static buzz of an old television, yet the massive, listening ears of NASA's Deep Space Network can still hear it. Inside the spacecraft, the onboard computers were marvels of simplicity. Each Voyager carried a humble 69 kilobytes of memory. To put that in perspective, the smallest photo on your phone holds more data than Voyager's entire brain. There were no flashing lights, no touchscreens, just solid-state logic and pre-programmed instructions. These humble electronics were carefully designed to be radiation-hardened and utterly reliable. A command sent from Earth would take hours to reach the spacecraft, and another long, quiet journey for the response to return. It was a patient conversation conducted across the vastness of the cosmos. Power was another hurdle. Solar panels, the go-to solution for probes orbiting Earth, were useless out where the sun is little more than a brilliant star among other stars. The solution came in the form of radioisotope thermoelectric generators, or RTGs. These were like small, self-contained nuclear campfires. They used the heat from decaying plutonium-238 to create a steady stream of electricity, keeping the instruments warm and the lights on for decades to come. At launch, they provided enough power to run a few light bulbs. Today, that output has dwindled, but even in their old age, they still cling to life, a testament to their longevity. The scientific instruments themselves were a carefully curated collection,
a small toolkit of sensors designed to peer into the unknown. Each spacecraft carried a magnetometer to measure the subtle magnetic fields of distant planets, plasma detectors to taste the solar wind, and cosmic ray sensors to feel the energetic particles from other stars. And of course, there were the cameras. Despite being less powerful than the one in your pocket, these cameras would go on to capture some of the most iconic images in the history of space exploration, from the swirling chaos of Jupiter to the elegant rings of Saturn. One of the most profound aspects of the design was its lack of a return ticket. Voyager wasn't built to land or to bring samples back or to be retrieved. It was built to simply keep going. This focus allowed the mission team to pour all their effort into quality and perfection. Every wire was checked and double-checked. Every piece of solder was precisely placed. They were building an artifact not just for a mission, but for a legacy. And so the Voyagers became more than just machines. They became time capsules, filled not just with technology, but with the quiet hope of the 1970s. They embodied our best selves, our curiosity, our ingenuity, and our enduring desire to reach out into the dark. Imagine now those twin ships standing silently on their launch pads, two small towers of human ingenuity, waiting for their moment. They have no voice of their own, only the quiet hum of their own systems and the patience of a world that is holding its breath.
Chapter 3: The Great Escape. Drift with me now and visualize the final days of summer in 1977. The air is warm, the world is humming with disco music and the echoes of the moon landings. But on two separate launch pads in Florida, a more profound kind of sound is waiting to be born. The sound of two silent liftoffs, a quiet roar that would send two tiny ships on the longest journey in human history. These are the moments before the beginning. The twin spacecraft, Voyager 1 and Voyager 2, stood poised, identical in design, yet with slightly different destinies. You might think that Voyager 1 would launch first, being number 1. But as with so much in the cosmos, the journey did not follow a tidy numerical rule. Voyager 2, with its longer and more intricate path, lifted off first on August 20th, 1977. Just 16 days later, on September 5th, Voyager 1 followed, set on a faster, more direct trajectory to its initial targets. Their shared mission was extraordinary. It wasn't just about visiting one faraway world. It was about riding a cosmic highway, a planetary pinball game where each encounter would fling the spacecraft onward with even greater speed. This was made possible by the Grand Tour's celestial secret, a rare and beautiful planetary alignment that only happens once every 175 years. This gravitational ballet, known as a gravity assist, is one of the cleverest tricks in the spaceflight playbook. Imagine a small, graceful dancer approaching a spinning giant. As the dancer falls into the giant's embrace, they speed up. Instead of getting pulled into an endless waltz, the dancer elegantly slingshots around and is flung onward, faster and in a new direction. The giant doesn't even notice the stolen momentum, but for the tiny dancer, it makes all the difference. This wasn't just a fuel-saving maneuver. It was the key that unlocked the entire outer solar system. Voyager 2, with its more complex route, took a slower, more deliberate course, keeping its options open for a grander tour. Its destination was not just Jupiter and Saturn, but potentially Uranus and Neptune as well. It was the patient, hopeful sibling. Voyager 1, on the other hand, was all about speed and efficiency. Its path optimized for a swift passage to Jupiter and Saturn.
After Saturn, its trajectory would take a sharp turn away from the plane of the solar system, soaring into the dark unknown above the planetary disk. The launches themselves were not the kind of grand spectacles that the Apollo missions had been. There were no crowds waving, no astronauts to be hailed as heroes, just a quiet, determined liftoff and a flurry of calculations. The Titan 3E Centaur rockets, powerful and precise, pushed their precious cargo beyond Earth's gravity well and set them on a course that had been planned for years. The launches were textbook perfect, and within hours, both spacecraft were on their way, leaving Earth as a memory, a faint blue marble in their rearview mirror. As the Voyagers sped onward, a powerful feeling took hold. These machines, with their humble electronics and their stubbornly durable frames, were no longer just our creations. They were our emissaries, carrying not just instruments, but a golden heart filled with the best parts of us. They were writing a whisper of physics and a surge of human ingenuity into a cosmic ocean we had only ever dreamed of crossing. And so, the quiet beginning of one of humanity's greatest stories unfolded. Two small ships, built with the humble tools of the 1970s, were now hurtling through the dark, their journey just beginning, a testament to the idea that a single, fleeting planetary alignment, a dash of precision, and a whole lot of hope can take you to places you never thought possible. Chapter 4: The Great Red Eye. Drift with me now and imagine the long, quiet glide of a ship through the star-dusted night. After months of patient travel, the celestial highway began to show its first landmark. The whispers of the outer solar system grew louder, and a new kind of light, a cold, distant glow, began to fill the viewfinders. In early 1979, the silent form of Voyager 1 drew closer to its first destination, a world so large it could contain all the other planets in the solar system, with plenty of room to spare. This was Jupiter, the king of the planets. For centuries, we had admired its striped and stormy face through telescopes, a beautiful, enigmatic orb spinning in the dark. But now, as Voyager 1 and, a few months later, its twin, Voyager 2, approached, our view was about to be transformed forever. The first thing that struck the scientists was not the grandeur, but the sheer, breathtaking chaos. From a distance, Jupiter's banded atmosphere had looked serene, almost placid, but the close-up images from Voyager's cameras revealed a world in violent, magnificent motion. The calm bands gave way to a maelstrom of swirling storms, jet streams roaring in opposite directions, and ovals of gas the size of entire continents. And then there it was, the Great Red Spot. This legendary storm, a feature first observed more than 3 centuries ago, was revealed in stunning textured detail. It wasn't just a red dot, it was a swirling crimson maelstrom, a hurricane so massive that it could swallow Earth whole and still have space left over. Voyager showed it to be a dynamic, living entity, its clouds swirling and twisting in a counterclockwise rotation with a speed that made terrestrial hurricanes seem like lazy whirlpools. The Great Red Spot wasn't alone. Dozens of smaller storms danced across the atmosphere, an intricate ballet of immense power and astonishing grace. The reason for all this drama lies in Jupiter's immense size and rapid spin. It is more than 11 times wider than Earth, and its day lasts less than 10 hours. This rapid rotation stretches its deep atmosphere of hydrogen and helium into the distinct bands we see and fuels the powerful storms that can rage for centuries. But the biggest surprises were not on the planet itself. They were in the company it kept. Before Voyager, we knew of a handful of Jupiter's moons, but we assumed they were little more than cold, cratered rocks. What the spacecraft revealed was a planetary family bursting with character and secrets. First, there was Io, a moon that completely rewrote the rules of geology. Voyager 1's cameras captured something no one had ever expected: plumes of material shooting hundreds of miles into space. These were not gas or dust, they were massive volcanic eruptions. It was the first time an active volcano had ever been seen beyond Earth. Io was a chaotic mess of molten plains and sulfur lakes, a tormented landscape painted in wild yellows, reds, and oranges. The source of this violence? Tidal heating. Io is caught in a tidal tug-of-war between Jupiter and its neighboring moons, and the constant squeezing and flexing of its core generate enough heat to power relentless volcanism. Then came Europa. At first glance, it seemed calmer, a smooth, icy shell with very few craters. But Voyager's images revealed a surface crisscrossed with long, dark lines, like fractures in a frozen sheet of glass. These lines hinted at something far more profound: a liquid ocean hiding beneath miles of frozen crust. An ocean warmed by those same powerful tidal forces that held the tantalizing possibility of life. Before Voyager, Europa was just another satellite. Afterward, it became one of the most intriguing places in the entire solar system. The other moons, Ganymede and Callisto, also had their stories to tell. Ganymede was revealed to be the largest moon in the solar system, even bigger than the planet Mercury. Callisto, ancient and heavily cratered, wore its history on its face, a testament to billions of years of silent cosmic history. As the Voyagers flew on, they also studied Jupiter's immense magnetosphere, a region of space dominated by its magnetic field, which is 20,000 times stronger than Earth's. It's a vast, invisible shield that traps charged particles and creates intense radiation belts. Voyager had to be specially shielded just to survive its brief flyby. The spacecraft also caught sight of Jupiter's faint, dusty rings, a subtle discovery that proved Saturn was not the only ringed master in the solar system. By the time the encounters were over, Jupiter was no longer a distant gas ball. It was a complex, dynamic system of furious weather, intense radiation, and an entourage of moons that defied all expectation. The Voyagers had transformed a question mark into a living, breathing epic. The ships had already accomplished more than anyone had dared to hope, but this was just the beginning of their journey. With the chaos of Jupiter behind them, their next destination lay in the darkness ahead, a place of quiet, ethereal grace wrapped in shimmering rings of ice and starlight.
Chapter 5: The Master of Rings. Drift with me now, and let your mind settle on the quiet majesty of Saturn. If Jupiter was all fiery chaos, Saturn was its elegant, contemplative cousin. For centuries, its rings had captured human imagination, a beautiful, impossible piece of cosmic jewelry that seemed to defy the very laws of physics. Galileo saw them first in the early 1600s, though his telescope could only resolve them as ears on either side of the planet. Now, with the Voyagers approaching, we were about to get our first true, high-definition look at this iconic world. In November of 1980, Voyager 1 made its close approach, followed less than a year later by Voyager 2. The view was breathtaking. Saturn wasn't just a golden orb with rings, it was an intricate, living system,
The planet itself, a stunning spectacle of shimmering golden bands and subtle storms, was dwarfed by the grandeur of its icy halo. The rings were, of course, the stars of the show. We had long known them to be wide, but Voyager revealed their astonishing thinness. Made mostly of water ice, ranging from tiny grains to house-sized chunks, the rings stretch for more than 200,000 miles across, yet are often no more than 30 feet thick. That's like stretching a sheet of paper across the length of an entire football stadium. How they remain so perfectly flat and neatly arranged is a mystery that still fascinates scientists today. Voyager's cameras peered into that delicate lacework and revealed far more than a few broad bands. They showed thousands of individual ringlets with subtle waves, intricate gaps, and strange, puzzling patterns. The Cassini division, a dark gap visible even from Earth, wasn't empty at all. It was filled with its own set of thin, faint rings. Even more curious was the discovery of so-called shepherd moons, tiny satellites that orbit on the inner and outer edges of the rings. Their gravitational influence acts like a cosmic sheepdog, herding the particles and maintaining the sharp, elegant edges of the rings with invisible hands. The rings also showed ghostly features called spokes, which looked like radial lines drifting across the surface like shadows. Scientists aren't sure what causes them, perhaps magnetic interactions with Saturn's field, or brief clouds of particles kicked up by tiny impacts. Whatever their origin, they gave the rings a haunting, ethereal quality. The planet itself proved to be no less fascinating. While less colorful than Jupiter, its atmosphere was dynamic, with jet streams and storms. Voyager observed curious hexagonal patterns near the poles, though the full mystery of the strange polar hexagon would not be unraveled until decades later by the Cassini mission. And then there was Titan. Of all Saturn's many moons, Titan stood out. Larger than Mercury, it was shrouded in a thick orange haze. Voyager's instruments detected that this atmosphere was denser than Earth's and composed mostly of nitrogen. It was the only moon in the solar system with such a dense atmosphere. But the haze was impenetrable. Voyager couldn't see the surface, leaving scientists to wonder what lay beneath that mysterious veil. An icy, hydrocarbon-rich landscape? Lakes, or even oceans of liquid methane? The questions lingered, tantalizing and unanswered. Voyager 1's flyby of Titan was a pivotal moment for the mission. To get a good look at this intriguing moon, Voyager 1 had to take a path that sent it out of the plane of the solar system after the encounter, ending its grand tour of the planets. It was a deliberate choice, a trade-off that sacrificed a potential flyby of the distant ice giants for a closer look at this mysterious moon. Voyager 2, by contrast, skipped the close-up of Titan and stayed in the solar system's main lane, preserving its route to the outer planets. With its job at Saturn complete, Voyager 1 bowed out of the planetary tour and began its new, solitary journey into interstellar space, leaving Saturn to wave farewell with its shimmering rings. Its planetary tour was over, but its grander voyage had only just begun. It left behind an endless stream of data, stunning images, and a new understanding of a planet that had once been a distant enigma. Saturn, with its quiet grace, was now part of our story.
Chapter 6: The Forgotten Siblings. Drift with me now and journey farther still into the deepest, coldest reaches of our solar system. Long after Voyager 1 turned its gaze outward toward the galaxy, its twin, Voyager 2, continued its quiet, patient glide. The year was 1986. Voyager 2 had already earned a glowing resume of close encounters with Jupiter and Saturn. But it wasn't finished. It was headed for the last two unexplored worlds in our planetary family, the ice giants, Uranus and Neptune. No other spacecraft had ever visited them, and to this day, no other has returned. Voyager 2 remains our sole emissary to these remote, enigmatic worlds. First up was Uranus. Voyager 2 arrived in January of 1986. At first, it looked almost too simple. A pale turquoise orb, seemingly featureless and calm. But as the spacecraft's instruments began to work, they peeled back the stillness to find a bizarre complexity lurking beneath the calm. The most striking feature of Uranus is its peculiar tilt. While most planets spin like tops, upright and steady, Uranus spins on its side, rolling around the Sun with an axial tilt of nearly 98 degrees. No one knows for certain how it ended up that way, but the result is a world of extreme seasons. One pole can face the Sun for over 20 years, bathed in constant light, while the other is plunged into a decades-long darkness. The atmosphere itself was colder than anything previously measured, a frigid minus 370 degrees Fahrenheit. Voyager detected faint cloud bands and signs of wind, but nothing as dramatic as Jupiter storms. The planet's apparent stillness, however, was deceiving. Later analysis of the data would show that Uranus has winds of up to 500 miles per hour, hidden beneath its thick, tranquil haze of methane and ammonia. The magnetic field was an even bigger surprise. Unlike Earth, which has a magnetic field neatly aligned with its rotation, Uranus is tilted by nearly 60 degrees and offset from the planet's center. This creates a wobbly, lopsided magnetosphere that twists and shifts with each rotation, a delightful curveball that forced scientists to rethink how planetary magnetic fields are formed. Voyager 2 also discovered 10 new moons and a faint system of dark, narrow rings. These rings, unlike Saturn's shimmering halo, were almost invisible, made of rock and dust coated in dark material that reflected very little sunlight. The spacecraft also captured an unforgettable view of one of the moons, Miranda, a small, battered orb that looked like it had been shattered and reassembled from spare parts, with enormous cliffs and strange, scarred valleys. After the Uranus flyby, Voyager 2 continued its long, solitary journey. It was a testament to both its durability and the mission's quiet ambition. It traveled another 1 billion miles, all while hurtling through the dark with a failing power supply and a dwindling suite of instruments. It was a journey of pure endurance. Then, in August of 1989, Voyager 2 reached its final planetary target, Neptune. The eighth and final planet in our classical solar system, Neptune appeared as a deep blue jewel in the viewfinder. But unlike Uranus, Neptune was not shy. It was dynamic, vibrant, and full of surprises. Despite being even farther from the Sun, Neptune was remarkably active. Voyager 2 discovered massive storm systems, including the famous Great Dark Spot, a swirling oval roughly the size of Earth. Winds on Neptune reached supersonic speeds of up to 1,300 miles per hour, the fastest observed in the entire solar system. How this cold, distant world generates such powerful weather remains a profound mystery. Like Uranus, Neptune's magnetic field was strange, tilted and offset, giving rise to a magnetosphere that writhed and wobbled with each rotation,
a delightful curveball that forced scientists to rethink how planetary magnetic fields are formed. Then came Triton, Neptune's largest moon. Voyager 2 found it to be a cold, strange, and unexpectedly active world. The spacecraft saw geysers of nitrogen gas erupting from its surface, a sign of what is known as cryovolcanism. This activity hinted at internal heat, perhaps driven by radioactive decay or tidal forces. Triton's retrograde orbit, meaning it orbits in the opposite direction of Neptune's rotation, was a strong clue that it was likely a captured object, perhaps a wanderer from the outer reaches of the solar system. The Neptune flyby marked the end of Voyager 2's planetary tour. After that, its cameras were turned off for good. But what it left behind was remarkable. It had transformed distant blue dots into real, complex worlds, moons with geysers, storms faster than sound, and magnetic fields that danced like drunken tops. Voyager 2 didn't just extend the mission, it redefined what was possible. It proved that the most remote places can hold the richest stories if we are willing to go far enough to hear them. The great planetary tour was over, but the Voyagers were just beginning their longest and most solitary journey of all.
Chapter 7. The Cosmic Mixtape. Drift with me now, and let's leave the planets behind. We're moving into the quiet, interstellar night, where the sun is just another star, and the background hum of the universe grows louder. It's a place no human has ever been, yet a piece of us is already there. It's the golden record, humanity's first and only mixtape for the cosmos. Imagine a bottle cast into a vast, dark ocean. It might never be found. It might drift for an eternity. But the act of sending it, the sheer audacious hope in that single gesture, that's the point. The golden record was the brainchild of a small, imaginative team led by the astronomer Carl Sagan. The Voyager missions were already ambitious enough, but Sagan and his colleagues saw an opportunity to add something more, something profoundly human. If the spacecraft were going to leave the solar system entirely, they reasoned, why not attach a message, a greeting in case an alien civilization ever found it in the far future? The odds of this were microscopic. Voyager is a tiny ship in an impossibly vast galaxy. But the gesture was everything. The result was a 12-inch, gold-plated copper disc, a true phonograph record, encased in a protective aluminum jacket. It was a time capsule, an art project, and an interstellar ambassador all rolled into one. And it had to represent, in just over an hour, the entire essence of life on Earth. No pressure. The team worked quickly, with a deep sense of wonder. They weren't just scientists, they were curators of the human experience. They started with greetings. The record holds spoken messages in 55 languages, ranging from ancient Sumerian to modern Mandarin. Some are formal, others are warm and playful. The greeting in English is simple and sweet. Hello from the children of planet Earth. It's delivered in the clear, hopeful voice of a child, a sound that is both a hello and a promise. But the team didn't stop with language. They included a rich tapestry of natural sounds from our planet. These were not just academic choices. They were designed to be emotional. The record contains the roar of surf, the rustle of wind, the crackle of thunder.
It holds the calls of birds, the laughter of children, the sound of a kiss, and even the whoosh of a rocket lifting off. One particularly haunting addition is the song of a humpback whale, an eerie and beautiful echo cast into the cosmic silence. Then came the music. The record holds 90 minutes of carefully selected music from around the world, intended to showcase our diversity and our unity. There is a Bach Brandenburg concerto, a gamelan piece from Indonesia, a Navajo night chant, and the melancholy blues of Louis Armstrong. There is also a track from Blind Willie Johnson, Dark Was the Night, Cold Was the Ground, a blues recording filled with wordless moans. Carl Sagan described it as expressing the human condition better than any spoken language could. The record also contained 116 images, encoded in analog format. These images were a kind of visual poem designed to introduce whoever found the record to our planet and our species. There were pictures of landscapes, animals, human anatomy, people eating and dancing, a mother nursing her child, and a photo of Earth from space. There were also scientific and mathematical diagrams, pulsar maps, and the structure of our DNA, all designed to give the finders a frame of reference. One of the most poetic and personal inclusions was a set of brainwaves from Anne Druin, a member of the production team who later became Carl Sagan's wife. For an hour, electrodes recorded her neural activity as she meditated on a wide range of ideas, including the history of Earth, the nature of humanity, and the experience of falling in love. That brainwave data was then encoded into the record, a mental fingerprint frozen in time. Somewhere in deep space, Anne's thoughts continue to travel, a heartbeat of human consciousness reaching into the dark. It's easy to dismiss this project as a romantic gesture, and in many ways, it was. But it was also a deeply practical statement. It reminded us that space exploration isn't just about rocks, orbits, and radiation belts. It's also about meaning, about sending not just our machines, but something of ourselves into the cosmos. Carl Sagan once said that the record was a bottle cast into the cosmic ocean. It might never be found, and if it is, it might not be understood. But the act of sending it, the sheer audacious hope in that single gesture, that's the point. The Golden Record was the brainchild of a small, imaginative team that continues to pierce the interstellar night. It's comforting in a strange way to know that somewhere, billions of miles from here, our little golden disk is still flying. It's not broadcasting, it's not blinking or beeping, it's simply there, turning slowly, gently, forever. A quiet promise that we were here, that we made music, that we looked up and wondered, and that we said hello. The 2 copies of the Golden Record, one on each spacecraft, are now the most distant human-made objects in existence. They carry our story into a silence no human has ever known, a final, beautiful gesture of hope and curiosity.
Chapter 8. The Pale Blue Dot. Now turn your mind's eye away from the darkness ahead. Look back with me, not with longing, but with a sense of quiet perspective. By the year 1990, Voyager 1 had completed its grand planetary tour. It had flown past Jupiter and Saturn, snapped its stunning photos, and helped rewrite the textbooks. Now it was a silent pilgrim, drifting into the deep, beyond the orbits of the known planets. Most spacecraft, once their primary mission is complete, simply fade from public view. But Voyager wasn't done yet.
not because it had more science to perform, but because it still had one more picture to take. A picture not of a planet or a moon, but of us. The idea was simple in concept, but profound in spirit. Turn Voyager's cameras back toward Earth and take a final snapshot from the edge of the solar system, a family portrait of sorts, with the sun and its planets seen from billions of miles away. It was Carl Sagan, ever the poetic voice of cosmic perspective, who pushed hardest for the idea. He believed that such a photograph could offer a rare and powerful moment of reflection, a visual reminder of our small place in the universe. There was some resistance to the plan. Engineers were cautious. Voyager's cameras were not designed to point near the sun, even from that great distance. A misstep could have damaged sensitive equipment, but by 1990, the risk was minimal. The cameras were already being retired from regular use, and the opportunity was too rare to pass up. So on February 14th of that year, Valentine's Day, NASA sent the command. The spacecraft, a tiny pinprick of human ingenuity, slowly rotated in the silent blackness. The shutter clicked. And the result, at first glance, was not particularly dramatic. In the final image, Earth appeared as a tiny pale blue dot, less than a pixel wide. It was caught in a shaft of scattered sunlight, a faint shimmer against the immense darkness of space, almost lost in the static. If you didn't know what you were looking at, you might have missed it entirely. But when you understood what you were seeing, it became one of the most profound photographs ever taken. That faint speck was Earth, home. Everyone you've ever known, every civilization, every story, every joy and every sorrow, all contained within a single shimmering mote of light. From nearly 4 billion miles away, our planet was reduced to a whisper. Carl Sagan later reflected on this image in what became one of the most moving passages in the history of science communication. In his book, Pale Blue Dot, he wrote, "Look again at that dot. That's here. That's home. That's us." Then he expanded on what that dot contained. Every king and every peasant, every hopeful child, every hero and coward, every corrupt politician, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. Carl Sagan's words were not just poetic, they were a gentle plea. He reminded us of the folly of human arrogance, of the endless battles we fight over borders and ideologies, and of the importance of kindness and of preserving our fragile planet. From a cosmic perspective, we're all riding the same speck of dust through an indifferent universe. That photograph, taken from the edge of the known solar system, became a mirror held up to humanity. It didn't show us our grandeur, but our fragility. And interestingly, Earth wasn't the only object captured in that portrait. Voyager's cameras also snapped images of Neptune, Uranus, Saturn, Jupiter, and Venus, all arranged together as a family portrait. But Earth, that pale blue dot, stole the show. The subtle blue tint in the image comes from the scattering of light by our atmosphere, the same phenomenon that makes the sky blue when we look up. Even from billions of miles away, that soft blue is visible. It is the color of oceans and sky, of breathable air and liquid water, a subtle clue that this tiny speck is unique and special. The image also captures the profound loneliness of space. There are no other lights, no flags, no flares, just a pinprick in a vast black sea. But that emptiness, far from being depressing, is actually kind of freeing. It strips away the noise and reminds us of what truly matters, not territory or titles, but connection, curiosity, and the desire to understand our world and our place in it. After this final farewell portrait, Voyager's cameras were powered off for good. It would never take another photograph. In that way, the pale blue dot was Voyager's final artistic statement, a last look back, a gentle turning of the gaze before heading into the long silence of interstellar space. And with that, it gave humanity a gift that no other mission had offered: perspective. A reminder that even in the vastness of space, a tiny world can hold infinite meaning, and that maybe, just maybe, looking back from a great distance helps us see what is right in front of us a little more clearly. Chapter 9. Beyond the Sun's Breath. Drift with me now and imagine a house where the warmth from the fireplace, the sun, slowly fades. We live comfortably in its light, but far beyond the familiar rooms, the house has a boundary, a point where the warmth ends and the wild, endless cold begins. For the Voyager spacecraft, that boundary is something called the heliopause, and crossing it marked one of the most significant milestones in the history of human exploration. To understand this journey, we have to see the sun not just as a source of light, but as a cosmic campfire, sending out a constant stream of charged particles known as the solar wind. This solar wind blows outward in all directions, creating a vast magnetic bubble around our solar system. That bubble is the heliosphere. Inside it, the sun's influence reigns supreme. Its magnetic field shapes the environment, and its particles fill the void. But eventually, that influence has to end. The solar wind weakens as it pushes against the material between the stars, a cold, sparse mixture of gas and dust known as the interstellar medium. The heliopause is the boundary where the pressure from the solar wind finally gives way to the pressure of the interstellar medium. It is the outer skin of the sun's protective bubble. Beyond that, the long, silent journey through the galaxy truly begins. Scientists had long predicted where this boundary might be, but no one had ever visited it. Not until Voyager. In August of 2012, after more than 35 years of travel, an extraordinary announcement was made. Voyager 1 had crossed the heliopause. It was the first human-made object to enter interstellar space. It had officially left the sun's domain. But how do you know you've crossed an invisible, shifting boundary? There's no glowing sign that says, "You are now leaving the solar system." Voyager's instruments had to feel the change in its environment. The first clue was a drop in solar particles and a simultaneous sharp increase in cosmic rays, the high-energy particles streaming in from outside the solar system. That was a major red flag, a signal that Voyager was tasting a new kind of space. Then came the definitive moment, a solar shock wave. An energetic burst of particles from a distant solar flare reached Voyager more than a year after it left the sun. As that wave hit the spacecraft, its plasma detectors recorded a sudden, dramatic jump in the density of the space around it. The plasma density had increased by a factor of 40, a striking confirmation that Voyager was now in the much denser interstellar medium. That sealed it. The spacecraft had truly crossed the threshold. It's important to note that while Voyager 1 is in interstellar space, it hasn't left the solar system entirely. The sun's gravitational pull extends far beyond the heliopause, deep into a theoretical shell of icy bodies known as the Oort cloud. Voyager, moving at over 38,000 miles per hour, won't reach the inner edge of the Oort cloud for another 300 years and won't exit it for another 30,000. So technically, it's still within the sun's gravitational neighborhood, but it is beyond the sun's direct protective influence. In November of 2018, Voyager 2 followed its sibling into interstellar space, though it took a different route. For the first time, we had not one but two data points from the edge of the sun's domain, providing valuable and often surprising information about the nature of the interstellar medium. Voyager found that the space out there is colder, denser, and more complex than previously imagined. It hums with low-frequency waves and is shaped by magnetic forces that reach across light years. Crossing the heliopause was a symbolic boundary as much as a scientific one. Voyager had gone from being a planetary mission to a galactic one. It had become an interstellar traveler. This was the fulfillment of a dream going back centuries, the idea of traveling to the stars. Voyager 1 is the first to actually do it, not with speed or glamour, but with quiet, faithful endurance. And it's still talking to us, faintly, patiently, a signal so weak that it takes over 22 hours to reach Earth. But it comes through, a whisper from beyond the sun, telling us about magnetic fields and particle density and the subtle nature of the interstellar breeze. Crossing the heliopause didn't make front-page news for long, but it was one of the most important thresholds humanity has ever crossed. It marked the beginning of a new chapter for how we see ourselves. Voyager left the warmth of the solar bubble and entered the cold, quiet dark, and it kept going. That perseverance, that curiosity, that quiet push beyond every horizon, it's hard not to see it as a reflection of something deeply human. A part of us left the solar system, and it hasn't looked back.
Chapter 10. The Long Goodbye. Drift with me now and listen for a whisper in the cosmic dark. After more than 4 decades of continuous flight, the Voyager spacecraft are still going. They no longer snap dramatic photos or soar past new worlds. And yet, even now, these twin explorers continue their long, lonely journey outward, slipping farther into the great unknown, while their faint voices still reach us across the cosmic silence. Voyager 1, the faster and farther of the two, is currently more than 15 billion miles from Earth. To put that distance in perspective, light itself, the fastest thing in the universe, takes over 22 hours to travel from Voyager 1 back to us. It is the most distant human-made object in existence. Voyager 2 is a little behind, traveling in a different direction at a slightly slower speed, but not by much. It is now more than 12 billion miles from Earth. At these incredible distances, nothing is easy. Communicating with either spacecraft is a delicate dance of timing, calibration, and hope. NASA's Deep Space Network, a global array of enormous radio antennas, listens day and night for Voyager's faint signal. And faint is an understatement. By the time their transmissions reach Earth, they are a whisper, about 10 billion times weaker than the power needed to operate a digital wristwatch. Detecting them is like picking up the gentle ping of a cell phone from another planet. And yet, the whispers arrive, faint but steady, patiently spelling out data that help scientists learn about the space beyond our solar bubble. But these spacecraft are getting old and tired. Each Voyager was designed to operate for about 5 years. 5 years, that was the plan. Just enough time to make it to Jupiter and Saturn, send back some photos, and retire with honor. Instead, they have kept going for nearly 50 years, far beyond their original expectations. Of course, they have had to make sacrifices to stay functional. Their power sources, the RTGs, are slowly but surely fading. At launch, they generated around 470 watts of power. Today, they produce less than half of that, and the power output is still falling. Less power means fewer systems can remain on.
Over the years, mission controllers have had to make tough choices, like managing a dimming lantern on a cold night. They've shut down heaters, turned off backup systems, and selectively powered down scientific instruments. Each decision is a small, quiet moment of mourning. An instrument isn't broken, it's just out of energy. As of now, each spacecraft has only a handful of instruments still running. The cameras were turned off decades ago to conserve energy and bandwidth, but they can still measure things: magnetic fields, charged particles, and plasma waves, and that data is invaluable. Voyager is the only mission giving us direct measurements from the interstellar medium, a region we have never visited before. The environment out there is very different from the sunlit regions we know. There are no planets, no rings, no moons, just vast emptiness, punctuated by cosmic rays and drifting atoms. Voyager is helping us understand how our sun interacts with the rest of the galaxy and how the edge of the solar system blends into everything beyond. The spacecraft themselves, built in the era of disco and floppy disks, remain surprisingly healthy. Their main computers are still functioning. The same redundant programming systems that once aimed cameras at Jupiter's moons are now carefully regulating their thermal balance and signal timing. Occasionally, a glitch occurs, a command gets garbled, a system hiccups. But engineers at NASA's Deep Space Network, many of whom weren't even born when Voyager launched, know how to coax the spacecraft back into line. In 2023, for example, Voyager 1 began sending back corrupted data. Months of patient detective work eventually led to a solution. Engineers deduced that a single faulty memory chip had likely gone bad. They crafted a workaround, a kind of cosmic software patch, and beamed it across the stars. It took over a day for the signal to arrive and another day to confirm success. And it worked. Each fix is a minor miracle. Each transmission is a small triumph. Of course, the end is inevitable. At some point in the next few years, the remaining instruments will be shut off one by one. The power will dwindle to the point where even the radio transmitter can no longer function. When that happens, the signal will fade and Voyager will go silent. Not because it failed, but because it succeeded for far longer than anyone thought possible. And yet, the spacecraft won't stop. They will keep traveling, a silent, graceful drift. Long after they fall silent, long after Earth loses contact, Voyager 1 and Voyager 2 will continue their journey. In about 40,000 years, Voyager 1 will pass within a light year or two of a small star called Gliese 455. By then, Earth's continents have shifted, languages have changed, and Voyager's signal will have long been a memory. But the spacecraft will still be out there, intact, drifting between stars. A tiny piece of human craftsmanship sailing through an unimaginable sea.
Chapter 11. The Message in a Bottle. Drift with me now and imagine a profound silence. Out there, in the chill of interstellar space, two small spacecraft are coasting, their last sparks of power fading away. But if you were to lean in close, very close, you might just hear the whisper of something else, the quiet song of the golden record, a final message in a bottle cast into the cosmic sea. It is easy to imagine the end of the Voyagers in terms of technology, systems failing, power dwindling, a final heart-wrenching loss of signal. But the Voyagers are not just machines. They are carrying a legacy, a piece of us that will continue to exist long after their final transmission fades. That legacy is the golden record, and it was never about high odds or a guaranteed reply. Carl Sagan and his team knew the likelihood of any civilization ever finding this tiny artifact was vanishingly small. The galaxy is an impossibly vast place, and the distances between stars are almost beyond comprehension. But as a thought experiment and as an act of pure,
audacious hope, the idea is irresistible. So let's suppose that thousands or even millions of years from now, an alien civilization, intelligent and curious, intercepts one of the Voyager spacecraft. It would be an object of great curiosity, a cold, silent artifact no larger than a compact car, glinting faintly in the starlight. But what would truly capture their attention is that strange golden disk bolted to the side and encased in a protective aluminum jacket. It would be the extraterrestrial equivalent of finding a message in a bottle, except the bottle is made of metal and the ocean is about 98% empty. Imagine their scientists in a lab cautiously unbolting the disk and discovering the engraved diagrams on the cover. These are the instructions for playback, etched in a symbolic language of mathematics and physics, showing how to assemble the needle and how to decode its contents. It might be the interstellar equivalent of assembling a piece of furniture without a manual, but it would be fascinating. The diagrams include universal signposts, the hydrogen atom, mathematical constants, and a map of pulsars to show the location of Earth. With time and effort, they might figure out how to play the record and reconstruct the encoded images and sounds. And then the real adventure would begin. What would an alien make of Chuck Berry's Johnny B. Good, a rollicking, joyful slice of 1950s rock and roll? To us, it is iconic. To a species with no ears, no cultural context, and perhaps no concept of rhythm, it might come across as pure emotional chaos or a distress signal. The musical selections were deliberately diverse, a carefully curated mixtape of Earth's sounds. There is Bach, Beethoven, and Louis Armstrong, but there is also traditional music from Indonesia, Senegal, Bulgaria, and Peru. If nothing else, the finders would be able to tell that Earth was a noisy, diverse place, capable of creating art and expressing emotion. And then there are the sounds, a sonic collage of our world, the roar of the ocean, the cry of a baby, the sound of a kiss, the hum of a rocket lifting off. One can only imagine the conversations among alien analysts trying to decode what any of this means. What is the sound of the wet smacking? A ritual? An emotional bonding? The song of the humpback whale? Surely a profound philosopher. There is something both humbling and hilarious about the idea that a highly advanced civilization might one day sift through our audio leftovers and try to reconstruct what kind of beings we were. The record also holds images, 116 of them, showing landscapes, animals, anatomical diagrams, and people eating, dancing, and giving birth, all very ordinary to us. But to someone without context, it might look like documentary footage of a bizarre carbon-based civilization that once flourished on a moist blue marble. And then there is the most personal inclusion, the brainwave data of Anne Druin, a moment of beauty frozen in electromagnetic patterns. To us, it represents the experience of falling in love and contemplating the history of our world. To them, it might be a series of erratic pulses. But who knows? Maybe they will be able to decode not just the signal, but the feeling behind it. Of course, all of this assumes the finders are capable and interested. Maybe they'll glance at the record, shrug their appendages, and go back to harnessing dark energy. But maybe, just maybe, they will listen. And in that listening, they will hear the laughter of children and the songs of whales. They will hear ancient greetings and a spinning record, the whisper of wind and the hum of machines. They will hear Earth, not as a collection of data, but as a living, striving, singing planet that once looked up at the stars and wondered, are we alone? In that sense, the message isn't just for aliens, it's for us. It's a declaration frozen in gold that says, this is who we were. We tried to understand. We tried to reach out. We made something beautiful, and we sent it into the dark. And even if no one ever finds it, even if the record spins through space untouched for 1 billion years, it still matters because it's out there, still drifting, still whispering, still hopeful. A testament to the idea that sometimes the simple act of sending a greeting is a story in itself.
Chapter 12. The Enduring Legacy. Drift with me now and reflect on the long, quiet echoes of a mission that began in a different time. It's hard to imagine a space journey that has lasted longer, traveled farther, or touched more hearts than Voyager. Launched in the late 1970s with the tools of an earlier age, these twin spacecraft weren't just explorers. They were ambassadors, archivists, and accidental poets. And while they continue to coast silently through interstellar space, their influence echoes loudly here on Earth. Voyager's legacy didn't end with its last planetary flyby. If anything, that's when its true impact began. It lit a spark, not just among scientists, but in the imagination of an entire planet. It's hard to imagine a space journey that has lasted longer, traveled farther, or touched more hearts than Voyager. Launched in the late 1970s with the tools of an earlier age, these twin spacecraft weren't just explorers. They were ambassadors, archivists, and accidental poets. And while they continue to coast silently through interstellar space, their influence echoes loudly here on Earth. Voyager's legacy didn't end with its last planetary flyby. If anything, that's when its true impact began. It lit a spark, not just among scientists, but in the imagination of an entire planet. It's no exaggeration to say that Voyager changed how we think about space exploration and left footprints on the path that many future missions would follow. For planetary scientists, Voyager was a revelation. Before it, the outer solar system was a blur of fuzzy, telescopic images and educated guesses. Voyager turned those question marks into high-resolution answers. Moons, once assumed to be lifeless and inert, were revealed to be geologically active. Worlds once thought to be simple gas balls were found to have complex weather systems and exotic magnetic fields. All of this redefined what we considered interesting in the solar system. Suddenly, moons were in the running for potential habitats for life. Atmospheres were more exotic, planetary weather more extreme. There was more to see, more to wonder about, and much more to explore. And explore we did. Missions like Galileo at Jupiter, Cassini at Saturn, and Juno at Jupiter didn't just follow in Voyager's footsteps, they stood on its shoulders. They were designed to provide the long, slow answers to the questions Voyager first asked. Cassini, for instance, a mission that orbited Saturn for over a decade, was a direct heir to Voyager. It didn't just look at Titan's atmosphere, it dropped a lander into it. It didn't just admire Saturn's rings, it mapped their structure in exquisite detail. These newer missions took the treasures Voyager had cracked open and sifted through them with tweezers and microscopes. Even missions to other targets, like New Horizons at Pluto, drew on Voyager's legacy, earning the nickname Voyager 3 because its spirit was the same: a single-shot flyby, an encounter with a world we'd never seen up close, a moment of pure awe. Voyager also set new standards for what long-duration missions could look like.
It showed that with good engineering and a bit of luck, a spacecraft could remain operational not for months, but for decades. That changed how agencies thought about planning, funding, and maintaining missions. It also changed how scientists thought about their own careers. A student just starting out in the 1980s could work on Voyager their entire life, and some did. But Voyager's legacy isn't confined to labs or launch pads. It also punched its way into pop culture. It showed up in films and was referenced in countless documentaries, books, and songs. It became a metaphor for persistence, for exploration, for humanity's quiet courage to look outward. The Golden Record in particular became a cultural icon, celebrated and parodied, and used as a seed for countless stories. More than anything, Voyager became a symbol, not just of triumph, but of wonder. It didn't explode across the sky like Apollo, or land like a dusty hero like the Mars rovers. It just kept going. A tiny whisper in the dark, a vote of confidence in the long view. The spacecraft themselves, simple as they seem now, were engineering marvels. Built with 1970s technology, hand-soldered circuits and analog tape recorders, and computers with less memory than a modern calculator. They've outlived most of the people who designed them. Their very endurance has become legendary. And yet, they are still making discoveries, still sending back data from regions no other spacecraft has ever traveled. Voyager also reshaped our philosophical understanding of exploration. It wasn't just about reaching new places, it was about asking better questions. What is the shape of a planetary magnetic field? How does solar wind interact with interstellar space? These were once the domain of theory. Now, thanks to Voyager, we have data. Even the way we talk about Voyager has changed. It is no longer just a probe. It has become a kind of cosmic poet, carrying humanity's dreams across the stars. Not loudly, not boastfully, but persistently, patiently, with the same quiet strength that marks our best stories. Perhaps that is the real legacy of Voyager. Not just what it discovered or where it went, but what it reminded us about ourselves. That we are a species that asks questions, that we build things not just to use, but to understand, and that we sometimes make art, not for fame or profit, but because it feels right to send music to the stars. Voyager's journey has been a slow unfolding, a message in a bottle not meant to be answered, but simply to be cast into the sea because sending it said something meaningful about the ones who did. As long as the Voyagers are still drifting, still sending, still spinning their golden records through the dark, a piece of us is out there, not searching for recognition, but quietly carrying the legacy of wonder.
Chapter 13. The Stars in Our Hands. Drift with me now, and close your eyes. Imagine the vast, cold emptiness of space beyond the planets and the cold breath of the heliosphere, a place where the sun is just another bright dot, and the background hum of the universe grows louder. It's in this profound and beautiful silence that our story finds its quiet conclusion, but not its end. Voyager 1 and Voyager 2 are still out there, still traveling, still listening. They are old now by any standard. They were born in a world of rotary phones and disco balls, handwritten code and slide rules. They launched when some people were still convinced that Pluto was the final stop on our cosmic tour. They've flown through solar flares, radiation belts, and the ever-thinning edge of the sun's influence. They've seen worlds we once only guessed at, and sent back evidence of geysers, volcanoes,
rings, oceans, and storms. And now, with just a few instruments still warm, they continue into the vast silence. But it isn't really silence they move through. It's just too quiet for our ears to notice. The space beyond the solar system hums with charged particles and ripples of ancient starlight. It's a place where atoms drift for eons without meeting, where distance loses all practical meaning, and where time itself stretches out like a road without signs. And yet, in the middle of all that quiet, something human is there. A piece of us wrapped in metal and gold, humming softly with fading power and carrying a message we wrote long ago. It's easy to forget how extraordinary that is. We built these spacecraft to explore the outer planets. That was their job, their assignment, their scope. But the moment they passed those final planetary encounters, they became something more. Not because they changed, but because we did. We realized they were no longer just tools. They were storytellers, pilgrims, time capsules, cosmic postcards with no return address. Voyager's journey is in many ways a metaphor for what it means to be human, to ask questions that have no clear answers, to build things that will outlive us, to wonder not for profit or conquest, but for curiosity, for the sheer joy of seeing what's out there. The spacecraft aren't fast, they're not flashy, they're not built to impress, but they persist, and there's a quiet dignity in that. Even now, long after their cameras have gone dark and most of their instruments have been turned off, they still speak. Their signals are faint, weaker than a whisper from across a continent. But they arrive, steady and disciplined. The same tones that once relayed images of volcanic moons and icy rings now carry information about the density of interstellar plasma and the direction of the magnetic field lines beyond the sun's grasp. It's not glamorous data, perhaps, but it's pure gold to the scientists who listen for it. And in that listening, there is something sacred, because listening is an act of hope. It says we believe there is still something to learn, still something worth hearing. Maybe that's the heart of the Voyager story. It never shouted. It never demanded attention. It just kept going. It taught us that wonder doesn't always arrive with a bang. Sometimes it comes pixel by pixel, bit by bit. A tiny dot on a screen that turns out to be a moon we never knew existed. The golden record, bolted to each spacecraft's side, was a final gift not to science, but to imagination. We didn't have to include it. There was no scientific requirement to send whale songs and greetings in Sumerian, but we did it anyway, because we hoped someone someday might find it. We hoped it would matter. And even if it never is found, it still mattered because the act of sending it, of choosing to say hello before anyone else did, revealed something essential about us. The stars have always been silent, but we spoke first. We sent music, laughter, the sound of footsteps, the crackle of thunder, the roar of rockets, and the hush of breath. We sent data and diagrams and the brainwaves of someone in love. We didn't send warnings, we didn't send threats. We sent wonder. Voyager's legacy isn't just about what it found, it's about what it inspired. New missions, new scientists, new dreams. It helped us realize that even our most distant machines can be storytellers, that even a spacecraft can carry meaning far beyond its mass, and that the farther we reach, the more we understand what it means to be home. One day soon, Voyager's power will finally run out. The signal will fade. The instruments will fall silent. No one will notice immediately. There will be no explosion, no dramatic farewell, just a long pause in a signal that never resumes. But even then, the spacecraft will not be lost. They will keep moving, slowly and steadily, among the stars, silent but not forgotten. And someone, perhaps us, perhaps not, might remember that we once built 2 small ships and sent them into the dark, not for answers, but for the joy of the question. And maybe that's all the legacy we need. As the story of the Voyagers concludes, I want to ask you what I asked when we began. Are you still awake? Still drifting among the stars with me? Or have you already slipped off into sleep, Voyager's gentle signal carrying you toward dreams? Either way, thank you for joining me on this quiet journey. And if you've enjoyed this voyage through time and stars, please consider leaving a like and subscribing to the Midnight Scientists. It helps more dreamers find their way here and helps keep the signal going just a little longer. Till next time, rest well, stay curious, and remember, we spoke first.
Hello there. A very warm and a very quiet welcome to the Midnight Scientists. I am so glad that our paths have crossed here in this peaceful space, in this moment suspended between the day that was and the night that is to come. Wherever you are, whatever kind of day you have had, I invite you now to let it all go. Allow the weight of your body to sink a little deeper into the surface beneath you. Feel the gentle rise and fall of your own breath, a quiet rhythm that has been with you all along. Tonight, we're going to embark on a quiet stroll, a gentle wandering through the subtle, soothing mathematics of the natural world. This is not a world of stark equations or difficult problems, but rather one of soft, repeating whispers, a hidden code that nature uses to write its most beautiful poetry. From the impossibly perfect spirals you can trace in the heart of a sunflower to the intricate, self-repeating branches of a winter tree, and even in the frothy, beautiful chaos of a passing cloud, we will uncover how the world around us seems to hum with these hidden patterns. It is a world where numbers are not cold and rigid, but gentle guides that show a leaf the way to unfurl. It is a world where great storms swirl across the oceans with a secret and profound symmetry, and where even the lazy, meandering path of a river has a quiet geometry flowing just beneath its surface. Now, I should offer a gentle warning. This journey might be just interesting enough to keep your brain softly, quietly curious. If you find yourself lying awake in the dark, pondering the precise angle at which a pine cone arranges its scales, I can only offer my sincerest apologies. But then again, if you are to lose a little sleep, let it be in the noble and peaceful pursuit of understanding why a simple fern looks like a piece of living, mathematical poetry, a perfect thought expressed in green. Before we venture too far, if you find that this slow and curious journey brings you a measure of calm, may I kindly ask that you consider giving this video a like and subscribing to the channel. It is a small gesture that helps more sleepy seekers of knowledge just like you find their way to this quiet corner of the world. And if you feel so inclined, please let me know in the comments where in the world you are listening from tonight and what time it is for you in this very moment. I always find it so wonderful to imagine how far these quiet evenings can reach,
connecting us all in this shared stillness. So please, snuggle in a little deeper. Let the day and all its concerns fall away behind you, like a single autumn leaf letting go of its branch to drift down onto the surface of still, quiet water. There is nothing left to do now, nothing to solve, nothing to hold on to. There is only the gentle current of this journey as we drift through the calm, quiet beauty of numbers in nature. And just a gentle reminder before we begin, this video is created for educational and relaxation purposes only. Now, let your breathing find its own slow, easy rhythm. Let your mind begin to soften. Let us begin. Let us begin our journey with something you have likely seen 1,000 times before. Something so common it is easy to overlook its quiet genius. Let us begin with a sunflower. Picture it in your mind's eye. You have surely admired its bright, brilliant yellow petals like rays of sunshine captured and held in place. You may have noticed its wonderfully sunny disposition, the way its face seems to follow the light across the sky. Perhaps you've even admired its tall, proud stance in a vast summer field, a sea of golden heads nodding gently in the breeze. But have you ever paused to stare into the very center of a sunflower and truly looked? Not just a passing glance, but a deep and curious gaze, the way a child might look at a seashell held in their palm for the very first time, tracing its curves and textures as if it holds some great secret. If you have, you may have noticed something odd, or rather, something oddly perfect. The dark seeds packed into its great round face are not scattered about randomly, nor are they simply crammed in as tightly as possible like marbles in a jar. No, they follow a pattern, a precise, swirling, mesmerizing dance of intersecting spirals that mathematicians and artists and nature lovers alike have come to recognize as one of nature's most elegant and persistent signatures. This pattern is born from something called the Fibonacci sequence. Now, please do not worry. We are not about to descend into a world of complex equations. This is not a lecture, and I can promise you there will not be a quiz. But there is a fascinating and wonderfully simple number story hiding at the heart of this perfect pattern, and it is a story worth telling. The Fibonacci sequence is, at its core, a simple series of numbers. It begins with 0 and 1, and each number that follows is simply the sum of the two numbers that came before it. So it begins 0, 1. Then 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 3 is 5, 5 plus 8 is 13, then comes 21, 34, 55, and so on, stretching out towards infinity, one simple step at a time. It is simple enough to explain, is it not? And yet, from that profound simplicity, a world of complexity and breathtaking beauty springs forth, a pattern that stretches from the smallest blossom to the grandest designs in the cosmos. Let us travel back in time for just a moment to meet the man whose name is forever tied to this sequence. He was an Italian mathematician from the 12th and 13th centuries, born Leonardo of Pisa, but he is known to history as Fibonacci. He didn't truly invent this sequence. Its principles had appeared in Indian mathematics centuries earlier, linked to the rhythms of Sanskrit poetry. But it was Fibonacci who introduced it to the Western world in his book Liber Abaci, a title that sounds like a magical spell, but was in fact a very practical manual on calculations for merchants. And in this book, Hidden amongst chapters on bookkeeping and currency conversion, Fibonacci posed a curious thought experiment, a question about rabbits. He asked his readers to imagine a single pair of rabbits placed in a field. He wanted to know how many pairs of rabbits would be produced in 1 year with 2 simple rules. Every month, each mature pair of rabbits produces 1 new pair, and a new pair becomes mature and able to reproduce after its 2nd month of life.
Yes, rabbits. It seems an unlikely place to find a universal mathematical key. But as it turns out, this fluffy, hypothetical puzzle of multiplying rabbits yields, month by month, the numbers of the Fibonacci sequence. And from that simple, earthy problem, things begin to spiral outwards, quite literally. Because those numbers do not just sit quietly on a page. They seem to breathe and live within the very structure of the world around us. In our sunflower, for example, the seeds are arranged in 2 sets of spirals that radiate outward from the center. One set curves clockwise, and the other curves counterclockwise. And if you take the time to count them, you will almost always find 2 neighboring numbers from the Fibonacci sequence. You might count 34 spirals, gracefully curving in one direction, and 55 spirals crossing them in the other. Or in a larger sunflower, perhaps you would find 55 and 89, or even 89 and 144. The numbers change, but the relationship remains wonderfully, peacefully consistent. But why? Why does nature do this? Is the sunflower a secret mathematician, counting its seeds as they grow? Well, not quite. The real explanation is even more elegant, grounded in the quiet logic of physics and the patient work of evolution. A plant's goal is simple: to pack as many seeds as possible into the head of the flower, ensuring each one has enough space to thrive. It is a problem of optimization. Too much overlap between seeds, and you waste valuable room. Too little, and you are not using the space efficiently. The solution nature discovered lies not in the Fibonacci sequence itself, but in its very close cousin, the golden ratio, which gives rise to something called the golden angle. This angle is an irrational number, approximately 137.5 degrees. When a plant produces a new seed, or a new leaf, or a new petal, it places it at this specific angle from the previous one. Imagine you are placing tiny dots around a center point. You place the first one, then you rotate 137.5 degrees and place the second. You rotate another 137.5 degrees and place the third. What emerges is a pattern of perfect packing. Because the angle is irrational, the pattern never repeats. No new seed ever grows directly on top of an old one. Instead, each new seed fits perfectly into the neatest, most efficient gap left by the ones before. That is what sunflowers do, and it is what pine cones do when they arrange their scales. It is what pineapples do with their diamond-patterned skin, and what the petals of an artichoke do as they curl around its heart. They do not try to form Fibonacci spirals. The spirals are simply the beautiful, ghost-like pattern that emerges as a side effect of following this deeply efficient rule of growth. It's like a perfect natural traffic system where each new car follows the exact same turning pattern, and as a result, the entire flow of traffic arranges itself into a state of perfect, unjammed harmony. The result is order that is disguised as beauty, or perhaps beauty that is the inevitable result of perfect order. This golden angle is derived from the golden ratio, a number that has fascinated thinkers for thousands of years.
It is often represented by the Greek letter phi, and its value is approximately 1.618. Like pi, it is an irrational number, which means its decimal points stretch on forever, never repeating, never settling into a simple pattern, a quiet, endless hum of digits. It is said that if you take any two successive numbers in the Fibonacci sequence and divide the larger one by the smaller one, your answer gets closer and closer to the golden ratio the further along the sequence you go. This mystical seeming number appears with suspicious frequency throughout art, architecture, and the natural world. It has been found in the ancient proportions of Greek temples, in the composition of Renaissance paintings, and some say even in the very proportions of the human body. The length of your arm compared to your hand, the joints of your fingers, the structure of your face. Many of these relationships hover near the golden ratio. It's not a strict, unbreakable rule set in stone, but it shows up just often enough to make you wonder, to make you feel a sense of connection to a pattern far older and larger than yourself. Back in the natural world, the beautiful spiral shells of the nautilus are often presented as perfect examples of the golden ratio in action. And while this is a slight simplification, many natural spirals are what are known as logarithmic spirals. The principle is the same. A logarithmic spiral grows outward at a constant angle, meaning it gets wider but keeps the very same shape. The golden spiral is just one very special type of this spiral, and while nature may not hit that exact value every time, it often gets close enough to make you pause and raise a curious eyebrow. And here's a deeply calming thought to hold on to as you rest. This pattern-seeking behavior is not just something that our human minds impose upon nature. It is something nature does all on its own. The spirals, the ratios, the sequences, they are not mere decorations. They are tools. They are solutions to physical problems. When a sunflower packs its seeds with such impossible precision, or a pine cone arranges its scales into a perfect spiral, it is doing so in the most efficient way possible, given the constraints of its space, the nutrients available, and the unshakable laws of physics. These are not just pretty designs. They are living, breathing, mathematical adaptations. It is a profound reminder that beauty and function are not separate things in nature. They often walk hand in hand. The world is not just beautiful for our benefit. It is efficient. It is optimized. And it just so happens that for us, optimization often looks and feels breathtakingly beautiful. Perhaps we have simply evolved to find these optimized patterns beautiful because they're so central to the story of life and survival. You can see these Fibonacci echoes in the delicate branching of succulents and in the swirling arms of a vast hurricane. Even the great spiral galaxies, spinning in the silent darkness of space, seem to nod gently to the same numerical ideas that shape a single flower.
That might be a coincidence. It might be what scientists call an emergent pattern. Or it might be something deeper still. Some strange, quiet, cosmic rhythm that binds the tiniest seed on Earth to the vastest, most distant star. Now, it is worth noting, with a gentle whisper of scientific honesty, that our human minds are wonderful pattern-seeking machines. Sometimes we see these sacred numbers where they do not truly exist. The golden ratio and the Fibonacci sequence have been supposedly found in everything from stock market trends to ancient pyramids, and many of these claims are a bit of a stretch. It is a bit like seeing familiar shapes in the clouds. We are so eager to find structure, so comforted by it, that we sometimes impose the pattern after the fact. It is part of our human need to make sense of the world. But even allowing for a touch of this wishful thinking, there is no denying that the sequence shows up in the biological world with a frequency that is far beyond mere coincidence. And yet, for all of this breathtaking mathematical elegance, a plant does not know math. A sunflower does not count its seeds. A pine cone does not solve equations. What they do is grow. They grow according to the simple, unbreakable rules of physics, chemistry, and biology. And those rules, it just so happens, favor certain numbers and certain angles because they are the most efficient. The Fibonacci sequence is not the cause of this beauty, but the result. It is a pattern that emerges peacefully and naturally from a few simple rules applied over and over and over again. And when you truly think about it, that idea is rather reassuring. Nature does not need to be told what to do. It does not require complex instructions or detailed blueprints. With the right conditions and with the patient gift of time, order arises from simplicity. Spirals emerge. Seeds find their perfect place. Everything moves outward in elegant, efficient, silent loops. There is something deeply peaceful in that knowledge. In a world that so often feels chaotic, complicated, and rushed, the idea that a sunflower quietly follows a centuries-old numerical sequence just to make the best possible use of space is a kind of quiet, profound wisdom. It is nature's way of saying, slow down, trust the pattern. Everything has its place, even the spirals. And as you allow yourself to settle deeper now, deeper into rest, it is comforting to imagine that even in sleep, your body follows its own hidden rhythms. Your breath, your heartbeat, the slow, gentle dance of your thoughts as they begin to drift, all are part of a greater pattern, one that you do not need to control, one that has been unfolding since long before you were born, and one that, much like the perfect spiral of a sunflower, carries on quietly, beautifully, without ever needing to ask why. Now, let us leave the sunny field and wander somewhere shadier, somewhere cool and green. Imagine you have found a fern growing in the damp earth at the base of an old tree. If you were to gently hold one of its leaves in your hand and look closely, you might notice something truly curious. The fronds, those large, arching, leafy branches, are made up of smaller fronds that branch off from a central stem. And if you look closer still, you will see that those smaller fronds are themselves made up of even smaller, nearly identical versions of themselves. It is as if nature took the blueprint for a single leaf, shrunk it down, copied it a dozen times, and then artfully glued the pieces together to create a larger version of the very same thing. And then it did it again and again, in layers of repeating perfection. This beautiful, recursive idea, this pattern within a pattern, is what the world of mathematics and natural design calls a fractal. A fractal is a shape whose parts resemble the whole.
It is a system built on self-similarity, which means that whether you zoom in or you zoom out, you continue to see a structure that looks remarkably like the original. In the case of our fern, each small leaflet looks like a tiny, perfect fern of its own, nestled into the larger architecture. If you were to stand on a rugged coastline, you might see the same jagged, irregular curves, whether you're looking at a few meters of rock or a few kilometers of shoreline. And if you have ever been lucky enough to see a Romanesco broccoli at the market, one of those bright chartreuse green vegetables that looks like it came from another planet, you have seen one of nature's most perfect fractals on your dinner plate. Each of its spiral towers is made of smaller, identical spiral towers. What makes fractals so utterly fascinating is that they seem to live in the space between perfect order and complete chaos. They are not perfectly regular, like a neat grid of squares, but they are not completely random either. They possess a kind of rough, organic symmetry. You can always recognize the underlying pattern, but it never repeats in the exact same way twice. Fractals are nature's way of being precise and wonderfully messy all at the same time. Now, mathematically speaking, the idea of fractals was given its formal shape in the 20th century, but like so many beautiful ideas, these patterns existed in nature for eons before we humans finally found a name for them. The term fractal was coined by the brilliant and unconventional mathematician Benoît Mandelbrot in the 1970s. He was a thinker who saw patterns where others saw only roughness and complexity. He was studying a seemingly simple question: how long is the coastline of Britain? It sounds like a question with a straightforward answer, but the deeper Mandelbrot looked, the more slippery the answer became. Imagine trying to measure it. If you take a very long ruler, say 100 kilometers long, and lay it end to end on a map, you'll get a certain length. But with that large of a ruler, you miss all the little details. You skip right over the small bays and inlets. Now, try again with a shorter ruler, perhaps 10 kilometers long. This time, you can follow the curves more closely. You measure into the mouths of harbors and around small peninsulas. And as you do, the length you measure increases. Now, imagine using a 1-meter stick. Suddenly, you're on the beach itself, picking your way around every single rock, tracing every tiny nook and cranny in the cliffside. The closer you look, the more coastline there is to measure. The length, in a very real way, seems to depend entirely on how closely you are willing to look. It approaches infinity.
This strange, wonderful property that the detail and complexity grow as you zoom in is the very hallmark of a fractal. Mandelbrot took this mind-bending idea and applied it to a vast range of patterns he saw in the world, showing that so many natural forms could be described using this new language of fractal geometry. The shapes of clouds, the jagged peaks of mountain ranges, the delicate branching of blood vessels, the chaotic forks of a lightning bolt, all of them have this self-similar, irregular, but deeply patterned structure. Let us pause for a moment and think about clouds. Have you ever tried to draw a real cloud? It is almost impossible. A cartoon cloud is simple enough, just a fluffy white oval with a few gentle bumps. But a real cloud has that complex, textured, frothy edge, full of little curls and wisps that seem to echo the larger shape of the cloud itself. You cannot draw a convincing cloud with a simple ruler and a compass. Its edges are too complex.
But fractal equations can generate images that look uncannily like real clouds, capturing that natural irregularity. Fractals give us a tool, a language, for modeling the beautiful messiness of the real world. And then there is the startling instantaneous beauty of a lightning bolt. A single brilliant fork of lightning splits the sky, and then in a fraction of a second, it splits again and again and again in branching, jagged paths that look eerily similar no matter how far you zoom in. That branching structure is a perfect, fleeting fractal. And that very same basic form shows up in the branching of river networks as they carve their way to the sea, in the vast network of blood vessels that carries life through your body, and even in the silent, searching tips of tree roots deep underground. It is nature's favorite way of building a distribution network, a branching system that allows things to move, electricity, water, blood, nutrients, through a space with incredible efficiency. The tree is a particularly elegant example. When you look at the branching of an oak tree in winter, its dark skeleton against a pale sky, you can see it so clearly. Each large branch splits into smaller branches, and those divide into even smaller twigs. The angles and lengths are not perfectly identical, but the structure echoes itself at every single level. This is how a tree solves the problem of capturing sunlight, creating a vast surface area for its leaves without wasting precious space or energy. It is evolution, sculpting geometry with a slow, biological chisel. And these patterns do not just appear in the visible structures of living things, they are also fundamental to how those things function. Take a deep, slow breath. As the air enters your lungs, it doesn't just fill two big pink balloons. Inside your chest, your airway branches again and again into smaller and smaller tubes called bronchioles, ending in millions of tiny, delicate air sacs called alveoli. This fractal branching system allows an enormous surface area to be packed into a relatively small and protected space. It is estimated that if you could flatten out the surface of your lungs, it would cover an area roughly the size of a tennis court. All of that tucked neatly and safely inside your chest, a life-giving biological fractal at work with every breath you take. Even the rhythm of your own heart has fractal patterns hidden within it. When your heart is healthy and relaxed, the time between each beat does not stay perfectly mechanically even. It varies, just slightly, in a pattern that is complex, subtle, and self-similar over time. Too much regularity in a heartbeat can be a sign that something is wrong. Too much chaos is not good either. A healthy, resilient heart has a rhythm that is just irregular enough, dancing gracefully between order and disorder, much like the edge of a cloud or a coastline. Now, let us drift for a moment from the organic world into the pure, quiet world of mathematics, to look at the most famous fractal of all. It is an image you may have seen before, known as the Mandelbrot set. It looks like a strange, black cardioid shape with a large circle attached to one side and countless smaller circles budding off from its edges. But as you get closer, you see that its boundary is not smooth at all. It's an infinitely complex coastline of swirls, curls, and fine hair-like filaments that stretch out into beautiful, chaotic patterns.
It is named for Benoit Mandelbrot, of course, and it is generated using a very simple equation applied to the numbers on a complex plane, repeated over and over and over again. The incredible, almost magical thing about the Mandelbrot set is that if you zoom in on its fuzzy, intricate edge, you keep finding more and more detail. You do not just find tiny, abstract shapes. You find entire new worlds of complexity. You will find tiny, spiraling seahorse tails, lightning-like branches, and most astonishingly of all, you will find tiny, distorted copies of the entire Mandelbrot set itself, hiding within its own boundary,
over and over again into infinity. It is like looking into a mirror made of pure mathematics, where each reflection contains another, smaller reflection, each one unique yet hauntingly familiar, just waiting to be explored. And yet all of this infinite, breathtaking complexity comes from one simple rule, patiently repeated. That is the deep, quiet magic of fractals. You begin with a simple instruction, a simple seed of an idea, and you allow it to repeat. With just a few basic rules and a great deal of iteration, something truly astonishing begins to take shape. You do not need a complicated blueprint for the entire structure. You just need to follow the simple rule and let the pattern unfold itself. This, in a profound way, is how nature builds itself. Not with grand, top-down plans, but with simple, local rules carried out billions of times. A tree does not know how to be a tree. Its cells are simply following genetic instructions to divide, to grow a little stem, which then branches. Those branches grow and then branch again, following the same simple rules. The final result is something that looks intentional, majestic, even artistic, but it is all driven by small, humble steps repeated with the unending patience of the natural world. There is a quiet and powerful lesson in that. In a world where we so often feel the pressure to do big, important things all at once, fractals remind us that staggering complexity can emerge from the simplest of beginnings, that true beauty can arise from gentle repetition, and that something as intricate as a fern or as sprawling as a thunderstorm can be born from just doing the same small thing, thoughtfully, again and again. And just as fractals exist in the physical world, they have also found their way, almost instinctively, into the world of human art and music. Some composers have used fractal algorithms to generate musical patterns that are complex yet coherent. Visual artists have built entire digital landscapes and otherworldly scenes from fractal structures. And the video games and films that transport us to other worlds often rely on fractals to create their lifelike environments, the rugged mountains, the twisting trees, and the realistic coastlines, all born from the simple, repeating logic of fractal geometry. You can also find these patterns woven into ancient cultural artifacts. Traditional African art, Indian textiles, and Islamic architecture sometimes include stunningly complex fractal patterns in their designs. Long before the word fractal was ever invented, humans were already intuitively mimicking these repeating, self-similar patterns in their craft. It seems our brains are naturally, deeply drawn to them, even if we do not always realize why. What is it about these patterns that can feel so deeply soothing? Perhaps it is the way they suggest a sense of endlessness without ever tipping into pure chaos. They give your mind something to follow, a path to trace, without ever overwhelming you with too much information. They are structured, but they are never rigid. They are predictable, but they are never boring. They feel like a walk along a forest trail that winds just enough to keep you curious about what is around the next bend, but not so much that you ever feel lost. Fractals live in that beautiful in-between space, the soft edge of chaos, the gentle shore of order. They are not one thing or the other, they are both at once, forever balancing complexity and calm. And in their branching, spiraling, infinitely detailed forms, they invite you to look deeper, to slow your breathing, to notice the way the world builds itself from the smallest of pieces, and maybe, just maybe, to find a little comfort in the quiet repeating rhythms of the universe. In the early 1960s, a meteorologist at MIT named Edward Lorenz was working on a rather humble problem, trying to predict the weather. In his lab, he had one of the early, room-sized computers of the era, a humming machine of vacuum tubes and wires. On it, he had built a simplified model of the Earth's atmospheric conditions. It was sort of a stripped-down toy version of a weather system, with a handful of equations representing the dance of temperature, pressure, and wind. One day, he ran a simulation, letting the computer churn out a long forecast of this imaginary weather. He then decided he wanted to repeat part of the simulation to examine a section more closely. To save time, he didn't start from the very beginning. He took the numbers from a midpoint in his first printout and typed them back into the machine. But instead of typing in all 6 of the decimal places the computer had originally used, he rounded them off slightly, typing in only 3. It was a minor difference, something like using the number 0.506 instead of the original 0.506127, an almost imperceptible difference. He set the machine running again and stepped away to get a cup of coffee, expecting the new simulation to unfold nearly identical to the first. But when he returned an hour later, something astonishing had happened. The 2 weather patterns had diverged completely. At first, they were almost the same, but then the tiny rounding off error began to amplify until his new forecast showed a weather system that bore no resemblance to the original. It was as if he had created an entirely different world. This seemingly minor laboratory hiccup led Lorenz to uncover one of the most profound and poetic ideas in modern science, chaos theory. And from his discovery came one of the most famous metaphors in all of mathematics, the butterfly effect. In a lecture he gave some years later, he titled his talk, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" Of course, this is not something that literally happens, but the metaphor captures a deep and humbling truth. In large, complex, dynamic systems, the smallest of changes at the beginning can lead to enormous and unpredictable differences later. Let's slow that idea down for a moment. Chaos, in the scientific sense, does not mean pure randomness or complete disorder. It refers to systems that are perfectly deterministic. That is, they follow strict, unwavering rules, but whose long-term outcomes are impossible to predict because of their extreme sensitivity to initial conditions. Imagine 2 small, identical balls placed at the very top of a hill to roll down. If you start them from the exact same position, they will follow the exact same path. But what if you start one just a single millimeter to the left of the other? At first, their paths will look almost identical. But if the hill is covered in small bumps, gentle curves, and twisting gullies, that tiny initial difference will be magnified with every bump they encounter. Soon, they will be rolling on entirely different parts of the hill, and by the time they reach the bottom, they may be nowhere near each other. That is what Edward Lorenz saw in his weather model. He hadn't broken the rules of physics, he had followed them perfectly. But the results were wildly unpredictable, because the system itself was just that sensitive. This profound realization was both thrilling and deeply humbling for the scientific world. It meant that, in theory, even if we had the most powerful computers imaginable and the most perfect equations for the atmosphere, we could likely never predict the long-term weather with perfect accuracy. Not because the universe is random, but because it is simply too complex. We could never possibly measure the exact position and velocity of every single molecule of air, every gust of wind, every tiny butterfly wing. Chaos theory soon found its home in all sorts of natural systems. Weather remains the classic example, but the very same principles apply to the delicate balance of ecosystems, the majestic dance of planetary motion, the rise and fall of animal populations, and even the intricate firing of neurons in the human brain. Anywhere you find a system with feedback loops, where the output of an action feeds back to influence the next action, anywhere you find nonlinearity, where cause and effect are not simply proportional, and anywhere you find lots of interacting parts, chaos is just waiting patiently around the corner, humming a quiet, unpredictable tune. Let us consider a much calmer, closer to home example: a dripping faucet in a quiet kitchen. You might think a leaky tap is just a simple, annoying sound. But researchers who have studied the timing of those drips have found the signature of chaos hidden within them. When the tap is dripping very slowly, the drops fall in a steady, predictable rhythm. Drip, drip, drip. Perfect timekeeping. But if you open the valve just a tiny bit more, the pattern changes. The drips might start falling in pairs. Drip, drip, pause. Drip, drip, pause. A little more, and they might fall in groups of 4. And then as the flow increases just a little bit more, the system dissolves into chaos. The pattern of drips becomes wildly unpredictable, never repeating. Even though the physics of the water, the gravity, and the pressure have not changed, the system has simply moved from a state of simple stability into one of beautiful, dynamic chaos. Now, imagine that same principle playing out on the grand scale of an ecosystem. A tiny, seemingly insignificant change, a slight increase in the average temperature of a lake, the introduction of a new insect, a small shift in rainfall can ripple outwards, cascading through the intricate web of life and creating entirely new balances, or imbalances. Chaos theory helps to explain why ecosystems can sometimes suddenly collapse or transform, even when the change that triggered it was so small it was barely noticed. A few too many fish are caught from a river. A patch of forest just a little too large is cleared, and suddenly, the dominoes begin to fall in ways no one could have predicted. But chaos is not always a harbinger of doom. Far from it. It is also the engine of creation, the source of complexity. It is how simple rules can give rise to rich, dynamic, and endlessly fascinating patterns. Think of a great flock of birds swirling in the evening sky. There is no leader, no choreographer, and yet the group moves as one, a fluid, living cloud. This is an emergent behavior built on the simple, chaotic interactions of individual birds, each one following its own simple rules. And from that local chaos, a global, graceful order is born. In the world of mathematics, these chaotic systems often produce stunningly beautiful images, known as strange attractors. These are visual representations of the path a system takes over time. It never settles into a single fixed point, nor does it repeat in a simple, endless loop. Instead, it spirals, twists, and folds back on itself, tracing an infinitely detailed pattern that never crosses its own path and never repeats. The most famous of these is the Lorentz attractor, the very pattern discovered by Edward Lorenz from his weather simulations. It is a set of swirly, looping curves that look, remarkably, like the wings of a butterfly, an accidental mathematical poem. This healthy, beautiful chaos is even present in your own body. As we touched on before, your resting heart rate, your quiet breathing patterns, they both show signs of chaos. Not a dangerous random fluttering, but a complex, non-repeating variation that is a sign of your body's health and adaptability. A perfectly regular, metronome-like heartbeat might in fact be a sign of a system that is too rigid, too inflexible. The healthy human body thrives in that gentle edge zone, both stable and responsive, predictable and yet flexible. Let us wander for a moment out into the vast, silent theater of space. Our solar system looks like a model of perfect order, with planets tracing neat elliptical orbits around the sun like marbles on invisible strings. But even here, in this clockwork universe, chaos gently sneaks in. The constant gravitational interactions between the planets create tiny, infinitesimal nudges and pulls on one another. Over millions and billions of years, these tiny nudges can accumulate, leading to unpredictable shifts in their orbits. The motion of asteroids in particular can be wildly chaotic. A small change in velocity or position, caused by a close pass with Jupiter, can be enough to fling an asteroid across the solar system, or send it on a path we can never fully predict. Thankfully for us, space is very, very big, and chaos tends to take its sweet geological time. If all of this sounds a little unsettling, a little too unpredictable, here's the comforting part. Chaos is not the enemy of calm. In fact, they often coexist in the most beautiful of ways. There is a quiet, deep elegance in watching how the world balances between them. You can't predict the exact path of every single falling leaf in a forest, but you can feel the calm of the forest as a whole. You can't know the shape of the next flicker in a campfire, but you can feel its steady warmth. In nature, chaos creates diversity. It prevents stagnation. It encourages adaptation. A perfectly ordered system would be brittle, unable to change. A purely random one would be unworkable, unable to build anything lasting. But chaos systems dance gracefully between the two. Think of a river. It is always flowing, always changing, never the same river twice. Yet it is always a river, always following the unwavering pull of gravity. Or that campfire, its flames flickering, leaping, changing shape every second, yet still contained, warm, and inviting. That is chaos in its softer form, not destruction, but dynamic, living beauty. And while chaos theory has its solid foundation in mathematics and physics, it is also deeply philosophical. It invites a sense of humility. It reminds us that certainty is often an illusion, that our control is limited, and that small, quiet acts truly matter. You never know what subtle, gentle influence your own presence, your own quiet choices might have in a room, in a day, or in a life. This does not mean we should live in fear of consequences we cannot predict. Quite the opposite. It means we can take comfort in the unpredictability. The world is allowed to surprise us. The future is not a fixed written story. There is always room for spontaneity, for change, for the unexpected and wonderful turn of events. At the very heart of chaos theory is a simple but profound truth. Even in systems governed by the strictest of rules, the future can be a beautiful, unfolding mystery. And this is not a flaw in the universe. It is a feature. It is what makes the world interesting, alive, and endlessly full of possibility. The butterfly effect is not just a quirky metaphor. It is a gentle, soothing reminder that even the tiniest actions can echo through time and space. That somewhere, in some great unfolding chain of events, a small gesture of kindness, a passing, hopeful thought, a single, quiet choice, might just be the beginning of something much, much bigger than you could ever imagine. And there is a certain profound peace to be found in that. Now, let us bring our focus back from the vastness of space and the grand sweep of time and land softly, gently in the middle of a quiet forest. Imagine yourself standing there, not rushing through on a hike, not checking your phone for a signal or worrying about where the path might lead, just standing. The air is cool and smells of damp earth and pine. Above you, a high canopy of leaves filters the sunlight into a soft, dappled green glow that dances on the forest floor. Listen. Can you hear the sound of the wind as it moves through the leaves? Not as a single gust, but as 1,000 tiny whispers. Listen to the slow, deep creak of branches as they sway. And as you stand there in that stillness, you might begin to feel, even if you do not consciously realize it, that there is something deeply, profoundly harmonious about the shapes that surround you. Trees do not just grow, they arrange themselves, and in their slow, silent, patient way, they follow the laws of geometry. Let us begin with something so simple, so familiar, that it is incredibly easy to overlook: the way a tree branches. You have seen it countless times, of course. A great solid trunk splits into a few thick, sturdy limbs. Those limbs divide again into smaller branches. Those branches fork into a delicate lace of twigs, and at the end of each twig, a cluster of leaves or needles reaches for the light. It looks natural, organic, perhaps even random. But there is a quiet, steady mathematics humming gently just beneath the surface. Trees do not branch by accident. They follow certain unwritten rules, elegant solutions that have been refined by evolution over millions of years to help them survive, thrive, and grow towards the light. One of those rules involves branching angles. That is, the angle at which a new branch grows out from its parent branch. It turns out that this angle is not a fluke. It is an optimized solution to a difficult problem. If the angle is too small, the branches will grow too close together, crowding each other and blocking their own precious access to the sunlight. If the angle is too wide, the branch might be structurally weak, unable to support the weight of its own leaves or the burden of winter snow. But somewhere in the middle, often around 38 to 45 degrees for many species, there is a perfect sweet spot. A delicate balance between strength and exposure to the sun. This optimal angle allows each new branch to maximize its own light capture while minimizing the shadow it casts upon its siblings. It's a little like being in a crowded theater. You could sit directly behind the person in front of you, but you wouldn't see a thing. You could sit too far to the side, and your view would be skewed. But there is one perfect spot that gives you the best possible view of the stage without getting in anyone else's way. Trees are experts at finding that spot. And that's just one part of the geometry at play. Another crucial concept is something called phyllotaxis. This refers to the arrangement of leaves on a stem or a branch. In many plants and trees, if you look closely, you will see the leaves are not arranged directly opposite each other, but in elegant spirals that wind their way up the stem. And what is the angle of rotation between each leaf in that spiral? Very often, it is our old friend, the golden angle, that same 137.5 degrees we found in the heart of the sunflower. This arrangement allows for the most efficient packing of leaves, ensuring that each one gets a clear and unobstructed shot at the sun. It's a quiet, graceful choreography, all in the pursuit of light. Because sunlight is energy, and energy is everything to a tree. Every single inch of its growth, every cell of its wood, every drop of its sweet sap is powered by light, captured and turned into sugar through the magic of photosynthesis. So it makes perfect sense that trees would evolve to become incredibly efficient masters of harvesting that light. The geometry of their branches and leaves is the beautiful result of millions of years of evolutionary tinkering with the quiet economics of energy. Even the height of a tree is a breathtaking balancing act of physics. Taller trees can outcompete their neighbors for light, but they are also faced with a monumental challenge of transporting water all the way from their deepest roots, hundreds of feet up, to their highest leaves, defying gravity every single inch of the way. Imagine being a single molecule of water being absorbed by a root tip deep in the cool, dark earth beneath a giant coastal redwood. You begin your journey upward, pulled into a vast network of microscopic tubes called xylem. You are pulled not by a pump, but by the power of evaporation from the leaves high above, and by the incredible cohesion between water molecules themselves, a force that allows you to cling to your neighbors, forming an unbroken chain of water stretching from soil to sky. It's an elegant and silent system, but it is not without limits. Gravity, friction, and the sheer physics of it all eventually put a cap on how tall a tree can possibly grow. There is even a theoretical maximum height for any tree on Earth, somewhere around 430 feet, beyond which the delicate, life-giving column of water would simply break under the strain. Now let us look at the tree as a whole. Its overall shape, the strong trunk rising, the great branches spreading, the deep roots anchoring, is not just a consequence of random growth. It is a living, breathing solution to a complex mathematical puzzle. How do you expose the most possible surface area to the light while using the least amount of material to build your structure, all while remaining strong enough to withstand the forces of wind and weather?
The answer, once again, lies in the repetitive, self-similar patterns of fractals. The structure of a tree is fractal in its very nature. A large branch, if you were to look at it alone, resembles a smaller, younger tree. A single twig echoes the branching pattern of the mighty limb it grew from. This fractal pattern is not just beautiful, it is incredibly efficient. It allows the tree to cover the most space, collect the most light, and transport the most nutrients, all with minimal material and energy costs. Fractals appear in trees because they are nature's perfect solution to a specific problem: how to fill a three-dimensional space effectively. The branching pattern creates a vast network where every part is connected, yet everything is gracefully spread out. This is especially vital for the unseen part of the tree, its root system. Roots, just like branches, grow in a fractal way, allowing the tree to explore a vast volume of soil with a relatively small amount of biological material. The root system is an underground mirror of the canopy high above, a twin pattern growing in the opposite direction, silently seeking water and nutrients, just as the branches above are seeking light. And this type of branching, fractal structure is not unique to trees. We find it everywhere in the biological world. The network of blood vessels in your own body, the bronchi in your lungs, even the delicate branching dendrites of the neurons in your brain. All of them follow these same similar fractal rules. The logic is always the same: spread out, reach many places, and do it with the utmost efficiency. In your brain right now, as you listen, your neurons are branching like tiny, intricate trees. Their dendrites reach out like roots and branches, seeking and receiving signals from other neurons. The very shape of these networks affects how you think, how you remember, how you feel. It is, in a very real sense, trees all the way down, living mathematics, shaping biology. There is something deeply, deeply poetic about that. Trees are not just biological organisms. They are physical manifestations of timeless mathematical principles. You can describe their essential shape with algorithms, simulate their growth with computer models, and even recreate their branching patterns in sculpture, architecture, and digital art. And yet, for all this underlying logic, no two trees are ever exactly alike. They all follow the same fundamental rules of growth, but the final results vary with the subtle shifts of wind, the quality of the soil, the competition from their neighbors, and the pure, simple element of chance. It is as if each tree is writing its own unique version of a familiar and ancient poem, using the same calming rhythm,
but with different personal words. This adaptability is part of their quiet genius. A tree can sense where light is most abundant and will redirect its growth accordingly. It will lean, twist, or even reshape itself entirely over the years to find the best possible position for its own survival. And beneath the soil, another layer of complexity pulses quietly. Trees in a forest are often connected by a vast, intricate network of fungi, an underground system sometimes called the wood wide web. Through this network, they can exchange nutrients, share information, and even warn their neighbors of stress or danger. It is a hidden, silent community, adding another layer of wonder to this already intricate geometry. But for a moment, let us step back. Think not just of the tree's function, but of its pure form. The way its branches stretch upward toward the sky, the graceful curve of a bough in winter, the delicate, intricate lace of bare twigs against a pale evening sky. There is a reason that people have drawn, painted, sung about, and studied trees for all of human history. Their structure is captivating. It feels both deeply familiar and wonderfully mysterious at the same time. They are quite literally living equations, quietly solving for light, for water, for strength, and for balance. And yet, for all their mathematical precision, they never seem cold or mechanical. Quite the opposite. There is a kind of deep, abiding calm in their order, a profound rhythm, a slow, steady breath drawn over centuries. The geometry of trees is not just about how they grow. It is about how they work, how they optimize, how they adapt, and how they endure. How they manage to be so perfectly efficient without ever losing their grace. They are silent, patient mathematicians of the forest, and all we ever have to do to appreciate their work is to slow down, look up, and let their branches do the talking. Now, let your mind drift from the quiet, rooted stillness of the forest. Let us travel in our imagination to a different place. A place of water and sand and endless horizons. Let us walk along the edge of a calm sea just as the tide begins to recede. Imagine you look down and see, half buried in the damp sand, something small, quiet, and perfectly curved, a seashell. You pick it up. It is still cool and damp from the ocean, and it rests comfortably in the palm of your hand. Its surface is smooth, and its colors are soft and sun-faded, creamy whites, soft pinks, gentle browns. You turn it over gently, and you notice its incredible shape. The way it curves inward, curling like a frozen wave or a spiral staircase to a tiny hidden world. It begins tightly at one end and slowly, gracefully widens as it swirls outward. This is not a random curve, and it is not even just a pretty one. That curve is mathematical. That curve is ancient. That curve is a logarithmic spiral. The logarithmic spiral, sometimes called the equiangular spiral, is a very special kind of pattern. It's a curve that keeps turning while at the same time getting progressively farther from its center point. But it does so in such a smooth, steady, and proportional way that it looks almost hypnotic. The key feature is this. With every quarter turn the spiral makes, it grows by the exact same factor, not by the same amount, but by the same ratio. That is the quiet magic of it. The spiral expands, but it does so without ever changing its fundamental shape. It's like nature took a compass to draw a perfect swirl, but the pencil moved farther away from the center at just the right consistent rate each time around. You can see this beautiful spiral hiding in all sorts of shells, but the most iconic and famous example is the nautilus. This beautiful, mysterious marine creature with its great coiled shell and its crown of searching tentacles is something of a living fossil. Its ancestors have been around for hundreds of millions of years, cruising silently through the deep oceans while the dinosaurs still stomped on land. The Nautilus builds its shell by adding new, larger chambers as it grows. Each new chamber it adds is larger than the last, but it follows that same gentle logarithmic curve, perfectly maintaining the spiral. The shell doesn't curl tighter and it doesn't flatten out. It holds that perfect curve again and again, as if it's following some deep internal blueprint, a mathematical guide printed right into its very DNA.
But the Nautilus does not do this just to be stylish. The spiral is profoundly functional. Each new chamber the Nautilus builds is part of an ingenious buoyancy system. The older, smaller chambers are sealed off and filled with gas, while the creature lives in the newest, outermost one. By carefully controlling the amount of gas and fluid in these chambers, the Nautilus can adjust its buoyancy, allowing it to float up or down through the water like a slow-moving organic submarine. The logarithmic spiral is what allows the Nautilus to grow without ever changing its essential shape. This means it can maintain its perfect proportions as it ages. No awkward growth spurts, no redesign required. It is a clever, efficient strategy, and it is one that does not require reinventing the wheel with each birthday. Just add a new chamber, stick with the spiral, and carry on. Other mollusks use this same quiet logic. Many gastropods, like snails and whelks, grow their protective homes in spirals too. Even the ammonites, those extinct ancient relatives of the Nautilus, followed the same beautiful formula. Their fossilized spiral shells, found in rocks around the world, a silent testament to a pattern that worked for millions of years. But shells are not the only ones in on the spiral secret. Spirals show up in plenty of places where shells are not involved at all. Look up at a satellite image of a hurricane. That vast, swirling mass of cloud is not just dramatic weather. It is also a gigantic spiral, shaped by the rotation of the Earth, the pressure gradients in the atmosphere, and the rising of warm, moist air. And then there are the spiral galaxies. Our own Milky Way, along with billions of others, curls its great arms through the blackness of space in massive, majestic spirals. The stars and gas and dust are drawn together into these graceful, sweeping curves that stretch across hundreds of thousands of light years. And if that is not impressive enough, this same spiral pattern also shows up deep inside your own body. Tucked safely within your inner ear lies the cochlea, a tiny, spiral-shaped, hollow bone that helps you to hear. This minuscule organ is curled into a spiral to conserve space while maximizing its surface area. Inside, it is filled with fluid and lined with thousands of tiny hair cells that vibrate in response to different frequencies of sound. The spiral shape allows your ear to decode the pitch of sounds with remarkable precision. In a way, your ear is a very quiet mathematician, unwinding the sound of the world into its component parts. From the spin of a galaxy to the way you hear these words, it all seems to come back to the same thing: the spiral as an efficient, elegant, natural solution. And as is so often the case in nature, what is practical also becomes beautiful. Spirals also turn up in so many other living forms once you begin to look for them. The proud curling horns of a ram, the delicate sticky beginnings of a spider's web, the searching, hopeful tendrils of a climbing plant, spiraling as they reach for support. Even DNA itself, the very blueprint of life, while a double helix rather than a flat spiral, still reflects this fundamental idea of twisting, repeating symmetry. The spiral form, in all its countless variations, seems to whisper something fundamental about the way energy, growth, and structure come together in our universe. And there is something oddly, deeply comforting in that. Despite all the breathtaking complexity in nature, despite the sheer, endless variety of forms and colors and functions, certain essential shapes come back again and again. The spiral is one of them.
Whether you are looking at a sunflower in your garden, a seashell on the beach, or a galaxy millions of light years away, the shape feels familiar, recognizable, and deeply reassuring. It is as if the universe, in its quiet moments, keeps doodling the same beautiful curve in all of its different notebooks. And it's worth remembering that nature is not obsessed with mathematical purity. It's not trying to perfectly match a diagram in a textbook. Many natural spirals are only approximations of the famous golden spiral. Some are a little steeper, some a little shallower. Nature rewards functionality above all else. If a shell grows slightly off course, but still provides a safe and efficient home, that is perfectly fine. The spiral, like so many patterns in nature, is flexible. It allows room for variation, for adaptation, for life itself. And so when you hold a shell in your hand, you are not just holding an object, you are holding a timeline. The entire life of a small creature, traced in calcium carbonate, winding outward in a precise and elegant arc. You are holding a quiet echo of the same curves that shape the storms, the galaxies, and the very mechanism of hearing inside your own head. A soft, gentle spiral written over and over again in nature's patient notebook. Now let your mind drift from the curve of the spiral and turn instead to another of nature's perfect forms. Let us go back to the image of a swirling cloud, but this time, let us imagine it's a cold winter cloud high in the atmosphere. And inside that cloud, something almost magical is beginning to happen. A tiny speck of dust, or perhaps a grain of pollen, floats in the supercooled air. A molecule of water vapor finds it and freezes onto it, forming a tiny, six-sided crystal of ice. This is the humble beginning of a snowflake. As this tiny seed of a snowflake begins its long, slow, tumbling journey down to the earth, it is shaped by the air around it. The temperature and the humidity of the clouds it passes through are constantly changing, and these subtle, ever-shifting environmental conditions influence how the crystal grows. First, simple facets may form. Then, as conditions change, elegant, branching arms begin to grow from its six corners. The six-fold symmetry comes from the very molecular structure of water itself. When water molecules freeze, they naturally arrange themselves into a hexagonal lattice, and that perfect, microscopic symmetry echoes outward as the entire flake grows.
You have likely heard the famous saying that no two snowflakes are exactly alike, and this is almost certainly true. Each flake follows its own unique path through the sky, experiencing its own unique history of temperature and moisture, and so each one becomes a unique frozen record of its journey. And yet, they all follow the same fundamental six-sided rule. The breathtaking symmetry arises not from a grand design, but from consistency. Because each of the six arms of a single snowflake grows outward through the exact same atmospheric conditions at the exact same time, they tend to mirror each other's growth with astonishing precision. It is a kind of spontaneous, emergent order. You do not need a designer. You do not need a blueprint. You just need water, cold air, and the patient, gentle hand of physics. Each tiny flake that falls is a six-sided work of art. Intricate, delicate, symmetrical, and beautifully fleeting. It is nature's frozen geometry, drifting silently down from the sky. Now, let us shift our gaze from the crystalline symmetry of frozen water to the liquid symmetry of soapy water. Picture a soap bubble, a shimmering, floating, perfect sphere catching the light and reflecting the world in its curved surface. It lasts only for a few moments before it pops and vanishes. Unlike snowflakes, which form through the slow process of crystal growth, bubbles are shaped by a force called surface tension.
It is a force that pulls the molecules at the surface of a liquid together, drawing them into the tightest possible shape. And what is that most efficient, most perfect shape? It is always a sphere. This is not a coincidence. A sphere is the one shape in the universe that can enclose the most volume with the very least amount of surface area. Nature adores efficiency. And so when a thin film of soap and water stretches around a puff of air, surface tension pulls it into the shape that requires the minimum amount of energy to maintain. And the sphere wins every single time. But bubbles do not stop at being pretty. They also reveal how geometry can emerge from simple physical forces. If you gently press two bubbles together, they will meet and flatten slightly, forming a perfectly straight wall between them. If you bring three bubbles together, their shared walls will always meet at a precise angle of 120 degrees. And when many bubbles are packed together in a froth, they naturally form hexagonal patterns, like a beautiful, chaotic mosaic. It is all very polite and very mathematical, as if the bubbles have an unspoken agreement to share their space as fairly and efficiently as possible. You can find this very same hexagonal pattern in the structure of a honeycomb, where bees build their wax cells in perfect hexagons because it is the shape that uses the least amount of wax to hold the most amount of honey. Once again, it's geometry doing its quiet, efficient work. And this love for symmetry shows up everywhere in nature. Flowers often display beautiful radial symmetry, their petals arranged in circles of 3 or 5 or 6. A starfish has 5 arms arranged symmetrically around a central point. Even the simplest of creatures, like a floating jellyfish, display this same rotational symmetry. For many organisms, symmetry offers practical evolutionary advantages. It helps with balance, with movement, and sometimes even with camouflage. A symmetrical body plan allows an animal to move efficiently and stay oriented in its environment. In us humans, symmetry is especially intriguing. Our bodies are built with what is called bilateral symmetry. 2 arms, 2 legs, 2 eyes, 1 nose, right in the center. We are essentially built as 2 mirror images, joined down the middle. Of course, we are not perfectly symmetrical. One of your feet is likely a tiny bit bigger than the other. You almost certainly have a dominant hand and a stronger eye. But the general layout holds true. And one of the biggest reasons for this is that it simplifies our biological development. Our DNA does not need to write a separate, complex set of instructions for the right side and the left side. It can simply use the same blueprint and flip it. But our relationship with symmetry is not just physical, it's deeply psychological. Countless studies have shown that humans, across all cultures, tend to find symmetrical faces more attractive. Not because we are shallow, but because our brains are exquisitely wired to process symmetry with great speed and ease. Symmetrical patterns are easier to recognize, easier to remember, and in the deep evolutionary part of our brain, they often serve as a quiet visual signal of good health and stable development. We see symmetry as a sign of balance, a kind of visual trustworthiness. This might explain why symmetry appears so often in our own art, design, and architecture. From the balanced columns of ancient temples to the clean lines of modern logos, symmetrical patterns create a sense of harmony, of peace, of rightness. They are pleasing to the eye and deeply soothing to the brain. There is a reason that mandalas, those intricate circular designs used in many cultures as a tool for meditation, are always symmetrical. Their repetitive, mirrored patterns provide an anchor for the wandering mind. They invite focus, calm, and a deep sense of contemplation. But nature, in its infinite wisdom, does not limit itself to one kind of symmetry. And it also understands the profound importance of breaking symmetry. Think of a fiddler crab with one great oversized claw and one small, delicate one. Or a tree on a wind-swept cliff, its branches growing almost entirely on one side, permanently leaning away from the wind. These asymmetries are not flaws. They are adaptations. They are solutions. In the great unwritten book of biology, function always takes priority for perfect form. If breaking symmetry offers a creature an advantage in survival or reproduction, then evolution is more than happy to do so. Even within your own brain, symmetry and asymmetry live together in a beautiful partnership. The two hemispheres of your brain are physically, broadly symmetrical, near mirror images of each other, but they are functionally distinct. For most people, the intricate machinery of language resides primarily in the left hemisphere, while the processing of spatial relationships and emotional tones lean toward the right. The symmetry of the brain provides the underlying structure, while its asymmetry provides for elegant specialization. It is a perfect balance of form and function.
And there is something so deeply human about our fascination with these patterns. We find symmetry in snowflakes and soap bubbles, in the faces of those we love and the slow unfolding of petals. We seek it out, and we replicate it in everything from our grandest architecture to the simple pattern of a knitted scarf. And yet, we also recognize the unique beauty of asymmetry, a jazz solo that veers off in an unexpected direction, a painting with an off-center subject that draws your eye, a story with a surprising and delightful twist. Too much perfect symmetry can begin to feel rigid, static, even lifeless. Too little, and things dissolve into incomprehensible chaos. The sweet spot, the place where life and beauty truly thrive, lies somewhere in between. Just enough order to feel stable, just enough variation to stay interesting. And this balance is perhaps why natural symmetry feels so deeply satisfying. It never seems to try too hard. A snowflake does not strive to be perfect, it just is, quietly following the laws of physics, forming silently as it falls. A soap bubble does not plot and plan its spherical shape. It is simply the inevitable, beautiful result of tension and air. The patterns are not forced. They emerge. Symmetry speaks to something deep within us. Perhaps it is the part that craves order in a sometimes disordered world, the part that seeks meaning in patterns. Or maybe it is simply that in a universe full of noise, symmetry offers a quiet kind of music, a harmony we can see. And in those soft, silent moments, a single snowflake caught on your glove, a shimmering bubble drifting in the sunlight, you can glimpse the gentle geometry at the very heart of everything, a stillness within the complexity, a simplicity within the swirl. You do not need to understand the math to feel it. It is already there, woven into the fabric of the world around you, balanced, mirrored, and waiting quietly to be noticed. Now, let us zoom out. Let us pull our focus away from the tiny, perfect symmetry of a single snowflake and rise high above the earth until we can see the grand, sweeping patterns of the land itself. Imagine you are staring down at a map and you begin to trace your finger along the outline of a country. Perhaps you follow the winding, intricate edge of a coastline,
or the jagged, saw-toothed lines of a great mountain range. You might have the curious sensation that the closer you look, the more there is to see. It's like chasing the edge of a puzzle piece that keeps adding new curves, new corners, new complexities every time you squint a little harder. That feeling is not just in your head. It turns out there is real, profound mathematics behind it. Welcome to the world where geography meets geometry, and where the very terrain of our planet becomes a tangled, beautiful web of hidden patterns. Let's begin with that deceptively simple-sounding task: measuring the coastline of Britain. We touched on this earlier, but let's revisit it. From the shoreline, you would think this would be straightforward, but here's where things become wonderfully tricky. If you were to measure it on a large map with a very long ruler, you would get one answer. But if you were to actually walk the coastline with a 1-meter stick, your measurement would be far, far longer. As you followed the curve of every bay, the edge of every inlet, the boundary of every single rock. This famous puzzle, known as the coastline paradox, challenges our very idea of measuring something that appears so concrete. A coastline, unlike a straight line, does not have one single definite length. Its length depends entirely on the scale at which you choose to measure it. The more detail you are willing to capture, the more complicated and longer the line becomes. The reason this happens is because coastlines are fractal. Their rugged, beautiful patterns repeat at different scales. If you look at a large satellite image of a coast, you will see great bays and peninsulas. Zoom in, and you will find smaller coves and rocky outcroppings. Zoom in further, and you will see that even the individual rocks have jagged edges, worn by the endless work of the waves into miniature cliffs and tiny folds. The structure continues from kilometers down to meters, and even down to the grains of sand. There is no smooth, simple line to follow. There is just more and more complexity the closer you look. A coastline is a perfect example of a natural fractal shaped over eons by countless forces: the rhythmic push and pull of waves and tides, the slow, patient work of erosion, the great deep movements of tectonic plates. Its shape is a reflection of that long and complex history, a mathematical fingerprint etched into the geography of the Earth. Now, let us shift our gaze inland, away from the edge of the sea and toward the veins of the land, the rivers. From high above, rivers look like a network of branching silvery threads. A main channel meanders through a wide valley, and it is fed by smaller tributaries, which are themselves fed by even smaller streams and creeks. The structure is unmistakably fractal. Each level of the vast network resembles the next, with smaller and smaller forks feeding into one another, like the branches of a great horizontal tree laid out upon the land. This is not just a coincidence. It is the inevitable result of physics, of gravity and erosion working together patiently over immense spans of time. As water flows downhill, it seeks the path of least resistance, carving channels that deepen and widen over the centuries. The fractal branching pattern emerges naturally as the entire system works to move water from the land to the sea as efficiently as possible. In fact, river networks are so consistent that they follow unwritten laws, not laws passed by governments, but deep statistical relationships known as scaling laws. One of them, called Hack's Law, describes the elegant mathematical relationship between the length of a river and the size of the area that it drains. The complexity of a river system, while it looks chaotic, is in fact an expression of a hidden mathematical order.
And this same quiet order emerges in the way that rivers meander. If you have ever flown over a flat landscape and seen a river that winds back and forth in lazy looping curves, you have witnessed another kind of natural pattern. Rivers do not always flow in straight lines. Instead, they gently erode their outer banks while depositing sediment on their inner banks, causing their bends to grow and shift and snake across the floodplain over time, sometimes even looping back to cut themselves off, forming a beautiful crescent-shaped oxbow lake. These meanders follow predictable rules, too. There is even a consistent mathematical relationship between the length of a river's curves and the width of its channel. It is almost eerie in its precision, as if the river itself knows exactly how much it should twist and turn. The same forces that shape rivers also sculpt our mountains. And while mountains may at first appear to be the very definition of chaos, a great random jumble of peaks and cliffs and ridges, they too follow these same quiet patterns. If you look closely at the silhouette of a mountain range against the sky, it shares that same fractal quality, jagged and intricate at every scale. Great ridges split into smaller ridges, which in turn split into sharp arêtes, and deep gullies, which split again into the smaller features of a single cliff face. The process that creates these majestic forms, the immense slow-motion collision of tectonic plates pushing the land upward, combined with the relentless, patient sculpting power of wind, water, and ice, plays out over geological timescales that are almost impossible to comprehend. But the resulting geometry is quietly, beautifully consistent. And once again, this is a kind of complexity that arises from simplicity. Scientists can now create stunningly realistic computer models of landscapes using relatively simple, repeated rules. They can simulate particles of sediment falling and sticking, or the slow process of water eroding a digital surface. And by repeating these simple actions millions of times, they can generate virtual landscapes that look just like the real thing. It is a profound and common theme in nature. The most intricate patterns, the endless branching of rivers, the craggy face of a cliff, the infinitely complex outline of a coastline do not require an elaborate master plan. They emerge naturally and patiently from the simplest of rules interacting with the world over time. Add water, add gravity, add an immensity of time, and the hidden math reveals itself. There is a kind of deep, quiet satisfaction in knowing that the messy, rugged outline of a cliff face or the erratic looping bend in a river is not truly random. It is the logical and beautiful result of processes that are ordered, repeatable, and profound. The gentle curves of a stream, the deep folds of a valley, the harsh, proud spines of a mountain, all of them have been shaped by water flowing ever downward, by rock resisting and then eventually yielding, and by time pushing ever steadily forward. The earth writes its story in a very slow handwriting, but the equations are there, hidden in the land, if you only know how to read them. And so the next time you find yourself gazing out at a landscape, whether it is a windswept coast, a winding stream, or a distant silent mountain, know that hidden in its forms is a quiet mathematics, a story told in curves and angles and repeating fractal lines. A story written not with ink, but with gravity and water and stone. And once you begin to see it, you will find it everywhere. In every ripple, every ridge, every line drawn by the earth's patient, steady hand. Now, let us lift our gaze from the slow, patient patterns of the earth and turn our eyes to the sky, just as the sun is beginning to set. Imagine you have seen it before, perhaps on a quiet evening walk,
A great flock of birds, maybe hundreds, even thousands of them, swooping and swirling together in the air. They form shapes that shift and ripple like a sheet of dark silk caught in the wind. There is no leader out in front barking instructions. There are no flashing lights to guide their path, and yet somehow they move as one. They twist, turn, dive, and rise, all without ever colliding. It is mesmerizing, almost hypnotic, and it is strangely, deeply mathematical. This type of coordinated, seemingly intelligent group behavior, whether we see it in birds, in fish, in insects, or even at times in crowds of people, is known as emergent behavior. It is what happens when a multitude of individuals all follow a few simple rules, and from those simple rules, a complex and beautiful group dynamic emerges. No one bird is in charge. No single fish dictates the direction of the school. Each member of the group simply pays attention to a few of its closest neighbors, and a magnificent coordinated pattern unfolds naturally from those local interactions. Take starlings, for instance. When they gather in those breathtaking, swirling clouds in the sky, a phenomenon known as a murmuration, they are each responding only to the position and the movement of about 6 or 7 of the birds flying nearest to them. That's all. They don't have to track the entire flock, which would be an impossible task. By simply aligning themselves with their immediate neighbors, keeping a small but safe amount of space, and adjusting their speed to match, they collectively create an intricate and spontaneous dance in the sky. Fish do something remarkably similar. Great schools of fish can move in tight, shimmering formations, shifting their direction almost instantly when a predator approaches, or turning in perfect fluid arcs as if they have been choreographed. Each fish is reacting not to the group as a whole, but only to the subtle movements of the fish directly beside it.
If one fish turns, its neighbor responds in a fraction of a second. The neighbor to that fish then responds, and the change cascades outward through the entire school like a ripple spreading across the surface of a still pond. It is breathtakingly fast, incredibly efficient, and a profoundly successful survival strategy. This is not telepathy. It is not even conscious, deliberative thought. It is simply a set of deep, instinctual rules, honed by millions of years of evolution. Simple, local rules. Keep close, but not too close. Move in roughly the same direction as your neighbors. Adjust your speed to match. And suddenly, without anyone giving orders, without any master plan, the group becomes a kind of superorganism, a living, breathing system flowing through the water or the air as if it had a single, collective mind of its own. You might wonder how these animals can possibly process all of this information so quickly. But nature, as it always does, has streamlined the process. Birds and fish are not performing complex calculations of trajectories like tiny flying or swimming computers. Instead, their nervous systems are exquisitely wired for these quick, instinctual responses. Visual cues, subtle shifts in the pressure of the water or the air, and the immediate behavior of their neighbors guide them in real time. It is less about thinking and more about reacting. Computer scientists have been fascinated by this kind of behavior for decades, and they have even used it to design powerful algorithms. There is something called the Boyd's model, which was developed by a researcher named Craig Reynolds in the 1980s. It simulates flocking behavior using only 3 wonderfully simple rules for each virtual bird or Boyd. The first rule is separation. Steer to avoid crowding your local flockmates. The second is alignment. Steer towards the average heading of your local flockmates. And the third is cohesion. Steer to move toward the average position of your local flockmates.
When these three simple rules are applied to thousands of virtual agents on a screen, they produce a behavior that looks uncannily, astonishingly like a real bird flock or a real school of fish. There is no master plan, just simple, local decisions leading to a complex and beautiful global pattern. Now, let us zoom in a bit, from the wide open sky down closer to the ground, and you will find another more intimate example of this beautiful organized chaos. Let us consider the world of ants. An ant colony can seem, at first glance, like a frantic, directionless buzz of activity. And yet, within that flurry of movement, there is a profound and efficient order. If you watch a trail of ants for any length of time, you will see a method to their movement, a shared purpose. When ants explore for food, they lay down invisible trails of chemicals called pheromones. If an ant is just wandering, the trail is weak, but if it finds a source of food, it will head back to the nest, laying down a much stronger pheromone trail as it goes. Other ants, sensing this trail, will follow it to the food source, and as they too return to the nest, they reinforce that same trail with their own pheromones. Over time, the most efficient and direct path to the food becomes the most heavily used, simply because it is the most heavily reinforced. It is a wonderfully simple, decentralized decision-making system, driven by feedback, chemistry, and the collective effort of the colony. What is so fascinating is that this emergent process can solve remarkably complex problems. In fact, engineers and computer scientists have borrowed this very idea from the ants to develop powerful optimization algorithms. These so-called ant colony optimization models are now used to figure out the best and most efficient routes for delivery trucks in a busy city, or the most effective layout for a complex telecommunications network. Tiny insects, just following invisible scent trails, have helped to inspire the tools that optimize our own modern logistics. And it is not just ants. Bees communicate the location of nectar-rich flowers to their hive mates using an intricate waggle dance, a literal wiggly dance where the angle of the dance relative to the vertical line of the honeycomb tells other bees the direction of the food source in relation to the sun, and the duration of the dance tells them the distance. It's a beautiful abstract language of geometry and movement. Termites, with no blueprint or architect, build towering, complex mounds with intricate internal structures and passive ventilation systems that keep the colony at a constant temperature and humidity. And in some parts of the world, on warm summer nights, thousands of fireflies will flash their lights in perfect, rhythmic unison, a living constellation blinking in the darkness, all coordinated by simple, local cues. What is so compelling about these systems is their incredible resilience. Because there is no central controller, there is no single point of failure. If a few birds fly off from the flock, the rest of the murmuration continues its dance. If a few hundred ants get lost, the colony still functions perfectly. The system adapts, heals, and carries on in real time. This incredible robustness is something that engineers strive to replicate in our own technology, especially in fields like robotics and artificial intelligence. If you have ever seen a video of a drone swarm with hundreds of small flying robots moving together like a synchronized flock of mechanical birds, you have seen this very principle in action. Each drone follows its own simple rules using sensors and algorithms directly inspired by the behavior of fish and birds. And the result is a coordinated, graceful ballet of machines. It is elegant, it is efficient, and it is a technology borrowed directly from the ancient wisdom of the animal kingdom. What makes all of this even more remarkable is how deeply calming it can be to simply observe. Watching a murmuration of starlings, a shimmering school of fish gliding through the water, or even a slow, steady stream of ants moving along a path has a strangely meditative quality. It feels both chaotic and organized at the same time, full of constant motion, but never rushed. There's a rhythm to it, a natural flow that is hard to describe, but so easy to feel. Part of the appeal, perhaps, is that these systems reflect something we're always looking for: connection without hierarchy, movement without command, and order without control. There is something deeply comforting about seeing hundreds of individuals moving as one, responding to each other, adapting together, and creating a beauty that is far greater than the sum of its parts, all without ever needing to explain how. Now, this idea of a collective, unconscious mathematics leads us to an even more intriguing question. You might not picture a bumblebee holding a tiny calculator or a sunflower solving complex equations, but nature has a very sneaky, very elegant way of doing math without ever writing anything down. Animals and plants do not perform mathematics in the way that we humans do, of course. There are no blackboards in a bird's nest and no spreadsheets in the soil beneath the tree, but that doesn't mean that they're not using sophisticated numerical and geometric strategies every single day. In fact, a surprising number of species show clear evidence of what scientists call number sense, a natural, innate ability to recognize patterns, to optimize their behavior, and to solve spatial puzzles that would make even a seasoned mathematician raise an eyebrow in appreciation.
Let us return for a moment to one of the most mathematically gifted members of the insect world, the honeybee. Bees do not just fly around aimlessly. Their lives are structured, efficient, and astonishingly geometric. And nowhere is that more beautifully apparent than in the perfect architecture of the honeycomb. Each and every cell in a honeycomb is a perfect hexagon, 6 sides of equal length packed together in a flawless repeating pattern that is both strong and beautiful. Hexagons are not the easiest shape for a tiny insect to build, so why do they use them? The answer, as the ancient Greeks first suspected, is pure efficiency. Of all the shapes that can be used to tile a flat surface without leaving any gaps, shapes like triangles, squares, and hexagons, the hexagon is the one that uses the very least amount of wax to hold the most amount of honey. It is the perfect solution to an optimization problem: how to build the strongest, most storage-friendly structure with the absolute minimum of materials and energy. It is advanced mathematics baked right into their biology. But their genius does not stop there. What is even more impressive is that individual bees can understand relative quantities. Studies have shown that bees can be trained to distinguish between different numbers of shapes. For example, they can learn to consistently choose a flower that has 3 blue dots on it instead of one that has 4 in order to earn a sugary reward. They do not count in the way that we do, 1, 2, 3, but they can estimate, they can compare, and they can even understand abstract concepts like more than or less than. For a creature with a brain that is smaller than a single sesame seed, that is nothing short of extraordinary. In one remarkable experiment, bees were trained to associate a certain number of objects with a sweet reward. They quickly learned to recognize these quantities and could even apply simple abstract rules like choose the group that has fewer items. They were, in a sense, performing a basic kind of addition and subtraction. For a creature with a brain no bigger than a pinhead, this is a truly mind-bending accomplishment. Now, let us take to the skies and consider the world of birds. Migratory birds, like the tiny Arctic tern or the incredible bar-tailed godwit, perform some of the most astonishing feats of navigation in the animal kingdom. They travel thousands upon thousands of kilometers across entire oceans and continents,
often returning to the very same nesting grounds year after year with pinpoint accuracy. How do they possibly do it? They are not following road signs or checking a GPS. Instead, they are masters of celestial geometry. They carry within them an internal clock and an internal compass, guided by the sun, the stars, and the invisible lines of the Earth's magnetic field. During the day, birds can detect the angle of the sun relative to the horizon, and using their internal 24-hour clock, they can use this information to determine their direction. At night, many use the stars as a navigational map. In a series of beautiful experiments, young birds like the indigo bunting were raised inside a planetarium. They had never seen the real night sky. The researchers found that these young birds learned to orient themselves by observing the rotation of the projected stars. They did not just memorize star patterns, they learned to identify the one point in the sky that did not move, the North Star. And they used this fixed point as the anchor for their entire celestial compass. And as if that were not enough, birds also possess a mysterious sense known as magnetoreception. They are believed to be able to actually see the Earth's magnetic field, perhaps as a faint pattern of light and shadow overlaid on the world, giving them an invisible map to follow even on cloudy days or moonless nights. What is truly extraordinary is how they integrate all of these different sources of information, the celestial, the magnetic, the topographic, recalibrating their route in real time as they travel. They are, in essence, solving a complex, multivariable navigation problem with their brains, a feat of instinctual, living trigonometry. And birds also display remarkable numerical abilities in their daily lives. Crows, ravens, and parrots, in particular, have shown the ability to count small numbers of objects, to solve puzzles that involve understanding sequences, and even to anticipate future outcomes. In a modern recreation of one of Aesop's fables, crows were presented with a tube of water that was too low for them to reach a floating treat. They quickly figured out that by dropping stones into the tube, they could raise the water level and bring the treat within reach. They even learned to choose larger stones over smaller ones, as if they had an intuitive understanding of volume and displacement. Some researchers even believe that crows and their relatives may understand the concept of zero, an abstract idea that took human civilization a remarkably long time to formally grasp. And even the tiny chickadee, that small, round songbird you might see flitting through snowy branches, organizes its world with a kind of spatial mathematics. Chickadees are famous for caching seeds in hundreds, sometimes thousands of different locations throughout the forest, and then remembering where they put them, sometimes for months. This incredible memory is deeply tied to spatial reasoning. It requires them to create a complex mental map of their environment, a map that mirrors the logic of geometry. It is practical, survival-driven mathematics. Now, let us float back down from the sky, past the branches of the trees, and turn our attention to something even more unexpected. Let us think about plants.
At first glance, plants seem like the very last place you would expect to find number sense. They do not have brains, they do not move quickly, and they certainly do not take math exams. But plants are brilliant problem solvers in their own slow, quiet, and patient way. Consider a plant's root system, that hidden underground world. A plant's roots grow constantly in their search for water and nutrients. And this growth is not random, it is optimized. Root systems follow those beautiful, branching, fractal patterns we spoke of earlier. They split and split again, covering the maximum amount of ground in a way that allows for the most efficient absorption, all while minimizing the energy it costs the plant to grow.
Each individual root tip can respond to its local conditions, to gradients of moisture, to the density of the soil, to chemical signals from neighboring plants, and it can adjust its direction of growth accordingly. The overall result is a structure that appears to have been intelligently planned, even though no single part of the plant is actually doing the planning. There is a particularly elegant example of this in climbing plants. Some vines spiral their way upward in search of support, tracing helical paths that often follow the sun's movement across the sky. This behavior, known as circumnutation, involves a constant, slow-motion adjustment of the plant's growth direction, all to maximize its exposure to the light. It is pure geometry in motion. Slow motion, to be sure, but no less precise. And let us not forget our friend the sunflower, which shows its geometric precision so openly. As it grows, its seeds arrange themselves in those perfect, intersecting spiral patterns that follow the numbers of the Fibonacci sequence. It is not that the sunflower is consciously calculating these numbers. It is that the simple genetic instructions that guide its growth naturally and inevitably produce that stunningly perfect arrangement. It is emergent geometry, encoded in the very heart of its biology. And then there is the strange and wonderful slime mold. Technically not an animal, not a fungus, and not a plant, this bizarre amoeba-like organism has demonstrated problem-solving skills that seem almost intelligent. In one famous experiment, researchers in Japan placed tiny sources of food on a petri dish, arranging them in the same pattern as the major cities surrounding Tokyo. They then placed a slime mold in the center. Over the course of a day, the slime mold grew outward, creating a network of nutrient-carrying tubes to connect all the food sources. And the final network it created looked remarkably, astonishingly similar to the actual layout of the efficient Tokyo subway system. No central brain, no planning committee, just simple local rules producing a brilliant global solution. All of this raises an intriguing and deeply peaceful question. Where does math really begin? Is it only something that we humans do when we count on our fingers or scribble equations on a piece of paper? Or is it something more universal, something woven into the very fabric of how organisms navigate, survive, and grow? It seems increasingly clear that nature does math in its own quiet, beautiful way, not through symbols or formulas, but through shapes and patterns and behaviors that align perfectly with the deepest principles of mathematics. Hexagons in hives, spirals in seeds, networks in roots, optimization, estimation, measurement, orientation. These are not just human inventions. They are strategies that life itself has evolved over millions and millions of years. And the numbers are always there, humming quietly in the background, guiding the bees as they build, the birds as they migrate, and the roots as they dig. Nature may not be doing math in the way that we understand it, but it is using the very same principles to solve the very same kinds of problems. How to move, how to find, how to build, how to grow. And the math, like everything else in nature, unfolds with a quiet, unhurried precision. The world, as we have seen, is full of patterns in space, but it is also alive with patterns in time. The world is full of rhythms, not just the rhythm of music or the steady ticking of a clock on the wall or the gentle tapping of your fingers on a table, but real, deep, biological rhythms that govern how living things grow and move and rest and wake. You may not feel it consciously while sitting under the artificial glow of electric lights or scrolling through your phone long after midnight, but your body is quietly, faithfully ticking along to a natural, ancient rhythm, a schedule that is millions and millions of years in the making. And it is not just you. From the way a tree drops its leaves in the autumn to the precise night that a sea turtle chooses to lay her eggs upon the sand, all of nature runs on clocks. Not the mechanical kind, but silent, living biological ones. Let us begin with the most familiar and fundamental of these rhythms, the circadian cycle. The name comes from the Latin circa diem, meaning about a day, and it is just that. Nearly every single living thing on this planet, from the smallest bacterium to the largest blue whale, has a circadian rhythm. It is a roughly 24-hour cycle that helps to regulate when to eat, when to sleep, when to move, and when to metabolize. This internal clock is not just a helpful suggestion. It is built into the very fabric of your cells. The master conductor of this grand biological orchestra is located deep in your brain, in a tiny, cross-shaped cluster of neurons called the suprachiasmatic nucleus, or SCN for short. This master clock keeps time using the gently oscillating levels of certain hormones and the rhythmic activity of what are known as clock genes. But these internal rhythms are not isolated. They are tied directly to the great rhythm of the planet, the cycle of light and darkness. When the soft light of morning first enters your eyes, it sends a signal directly to your SCN, which then resets the clock for the day ahead. That is why getting natural sunlight in the morning can feel so invigorating, helping you to wake up and feel alert. And it is why staring at the bright blue-toned light of a screen late at night can confuse your internal clock, delaying the natural onset of sleep. In response to these light cues, your body orchestrates a gentle daily chemical symphony. Melatonin, the hormone that helps you to feel sleepy, begins to rise in the evening as the darkness falls, and its levels drop away in the morning. Cortisol, which helps with alertness and energy, does the very opposite, peaking shortly after you wake. These gentle hormonal waves are what guide your energy levels, your mood, and even your digestion throughout the day.
And this is not just a human feature. Fruit flies, mice, fish, plants, even single-celled organisms show these daily cycles. Flowers open their delicate petals in the morning and close them again at dusk. Fungi release their spores at specific and predictable times of day. And on the great coral reefs of the world, entire colonies will spawn in breathtaking, coordinated bursts, all synchronized by the light of the moon. This biological clock is one of the most ancient and universal features of life on Earth. And it makes perfect sense. Our planet spins, creating a reliable cycle of light and darkness. Organisms that learned to align their biology with this cycle had a profound advantage. Those that could anticipate the coming of day and night could prepare, conserve energy, and stay safer. Over millions of years, this led to the evolution of internal rhythms that match the Earth's rotation almost perfectly. It is a kind of mathematics made of molecules and neurons, ticking away faithfully without a watch in sight. Now, let us zoom out a bit. Beyond the daily rhythm lies a grander, slower, and even more majestic pattern: the seasons. Winter, spring, summer, and fall. An elegant four-part harmony created by the Earth's orbit around the sun. But it is not just the orbit that creates our seasons. It is the tilt. The Earth leans on its axis at an angle of about 23.5 degrees. And as our planet makes its long 365.25-day journey around the sun, different parts of the planet receive varying amounts of direct sunlight. When the northern hemisphere is tilted toward the sun, its light falls more directly upon us, and we are warmed by summer. When it is tilted away, the sunlight strikes us at a shallower angle, and we are cooled by winter. It is a beautiful, silent, geometric dance written in the grand language of orbital mechanics. This slow, seasonal rhythm is the background music to all of life's choreography. Plants bloom, animals breed,
birds migrate, and bears hibernate, all in perfect time with the Earth's orbit. Deciduous trees drop their leaves as the daylight wanes, preparing for a long, quiet dormancy. Even the tiny microbes in the soil respond to the deep, slow cycles of temperature and moisture. And then there is the moon, a subtler drummer in nature's great orchestra. The moon does not just light up the night sky. It tugs ever so gently on the earth with its gravity, pulling at our vast oceans to create the tides. These tides rise and fall with a rhythm that is regular, predictable, and deeply mathematical. This lunar rhythm, which takes about 29 and a half days to cycle from one full moon to the next, affects more than just the water. Many animals time their most important behaviors to the moon's cycle. Sea turtles will come ashore to lay their eggs during certain phases of the moon, often around the full moon, when the high tides can carry them farther up the beach. As we mentioned, the great coral reefs synchronize their mass spawning events with the lunar calendar, releasing vast milky clouds of eggs and sperm on a schedule so precise, it's like a biological festival of mathematics. All of these rhythms, the daily, the monthly, the seasonal, layer on top of one another, creating a kind of biological calendar that every living thing on Earth follows. It's a quiet symphony, and we are all part of it, yawning in unison, waking with the sun, drifting into sleep as the world around us darkens. And there is something deeply comforting in that, is there not? In knowing that your body is part of a larger, ancient rhythm, that while your own daily schedule might be full of meetings and traffic and alarms, underneath it all, a deeper, truer pattern is ticking along. A pattern shaped by planetary orbits, by ancient sunlight, and by the gentle gravitational pull of the moon. A pattern that whispers when it is time to rise, when it is time to eat, and when, at last, it is time to rest. And when you do finally rest, you are not just recharging your body. You are aligning. You are matching your own internal metronome to the great, slow rhythm of the earth, letting the mathematics of time carry you gently forward, one perfect, peaceful cycle at a time. Now, for a moment, let us close our eyes and simply listen. Not just to the loud, obvious sounds of the world around you, the distant traffic, the hum of an appliance, or the murmur of a television in another room. Try to listen past all of that, to the quieter, more subtle rhythms underneath. Perhaps you can hear the gentle call of a night bird drifting through an open window, the soft, sibilant hush of leaves moving in a gentle breeze. Or maybe, in your memory, you can conjure the distant rhythmic roll of waves upon a shore. These sounds are not just pleasant background noise. They are patterns. They are vibrations. They are quiet equations hidden in the very air around you. Sound is what happens when something moves and causes the air around it to vibrate in ripples. Those ripples, those invisible sound waves, travel to your ears where they are translated by the miraculous machinery of your inner ear and your brain into a rich symphony of meaning. Whether it is the sound of music, the warmth of a familiar voice, or the lonely croak of a single frog in the darkness, all of it is made of waves, tiny rhythmic compressions and expansions of molecules dancing through the air with astonishing precision. And these waves follow unwavering mathematical rules. The pitch, or the frequency of a sound, is determined by how fast the wave is oscillating. High-pitched sounds are made of fast, tightly packed waves. Low-pitched sounds are made of long, slow, gentle waves. And the amplitude, the height of the wave, is what controls its volume. Bigger waves mean louder sounds. When a musical instrument plays a note, it does not just vibrate at one single frequency. It also vibrates at a whole series of other, quieter, higher notes at the same time. These are called overtones or harmonics. these frequencies are always simple, whole number multiples of the main fundamental note. So when you hear a single note played on a piano, you are not just hearing that one frequency. You are hearing the main note accompanied by a whole choir of quieter, higher notes that give the sound its warmth, its richness, its character. It's these harmonics that allow us to tell the difference between a violin and a flute playing the exact same note. And nature understands this principle deeply, even if it does so unintentionally. Birdsong, for instance, is built on these complex harmonics. Many songbirds, like thrushes and warblers, produce sounds with incredibly rich and intricate harmonic structures. Their songs are not just for show. Birds use them to claim territory, to attract mates, and to communicate across vast distances. The mathematical structure of these songs is fascinating. Some species will even change their tune depending on their environment. In a dense forest, where high-frequency sounds are easily scattered by leaves and branches, birds will often use lower-pitched, slower songs that can travel better through the thick vegetation. In wide-open spaces, high, fast, complex notes can carry much farther. It's a phenomenon known as acoustic adaptation, and it shows that even the forest itself has its own unwritten set of acoustical equations. And on a warm summer night, you might hear an entire chorus of frogs calling out across a dark pond. Each different species will be singing in a slightly different frequency range. This is not a coincidence. It is a brilliant strategy. If two species had identical calls, their signals would become muddled and confused. By separating their calls into distinct frequency bands, the frogs avoid this overlap and ensure that their own messages get through loud and clear. It is a kind of sonic social distancing enforced by evolution. And sound in nature does not only come from living things. The ocean has its own deep, resonant music. Stand near the shore and you will hear the rise and the fall of the waves, an eternal rhythm that is both beautifully chaotic and strangely, peacefully consistent. The frequency and the amplitude of these waves follow mathematical principles, from the simple, gentle sine waves of a calm sea to the complex, powerful interference patterns of a great storm. And then there is the beautiful phenomenon of resonance. Imagine you are gently pushing a child on a swing. If you time your pushes to match the natural rhythm of the swing, it will go higher and higher with very little effort. That is resonance. Every object has a natural frequency at which it prefers to vibrate. This is part of how our own inner ears work. As we discovered in the spiral of the cochlea, thousands of tiny, delicate hairs are arranged along its length, and each one is tuned to resonate at a specific frequency, vibrating in perfect sympathy with the incoming sounds of the world. Your ear is, quite literally, a biological instrument tuned to the music of the universe. It is no wonder that certain sounds are so deeply soothing to us. The sounds of gentle rainfall, the wind moving through trees, the rhythmic crash and hiss of waves on a beach. These sounds tend to fall within frequency ranges that our brains find calming. They are usually low to mid-frequencies, without any sharp, sudden, or high-pitched noises that might signal alarm. They mimic the peaceful, predictable rhythms of the natural world and of our own bodies at rest. There is a mathematical serenity to them. The ancient Greeks first discovered the deep connection between music and mathematics. The philosopher Pythagoras found that harmonious musical intervals, like octaves, fifths, and fourths, could all be expressed with simple, beautiful numerical ratios. This is why music is so often described as mathematics that you can hear. Every chord, every rhythm, every soaring harmony is a pattern, a wave, a frequency, dancing through time. And the natural world is full of this music, whether we are consciously listening or not. Great whales sing in low, resonant tones that can travel for hundreds of kilometers through the deep ocean water. Elephants communicate using infrasound, frequencies so low they are below the range of human hearing. Sound is not just a sense, it is a signal, it is a connection. It is a pattern passed through the air and the water and the wood, from one living thing to another. And the rules that shape these patterns, the wavelengths, the resonance, the harmonics, are all quietly, profoundly mathematical. It is comforting, in a way, to think of the world as always singing. Whether it is a blackbird at dawn or the soft hush of wind over the hills, the earth is never truly silent. It is humming, whispering, vibrating with the quiet equations of motion and energy. Not random, not chaotic, but beautifully ordered in a language made not of words, but of waves. And all we have to do is be still and listen. And so, as we draw this quiet journey to its final peaceful close, it is worth pausing for one last gentle breath. Together, we have wandered through the perfect spirals tucked into the heart of a sunflower. We have followed the fractal, branching paths of trees and rivers. We have listened to the hidden mathematics in the song of a bird and the rhythm of a breaking wave. And all along the way, one simple, profound truth has echoed softly beneath the surface. Nature is full of patterns, not rigid, mechanical, unfeeling ones, but living, breathing, elegant rhythms that whisper of structure, of balance, and of a deep and abiding beauty. The mathematics we have explored together tonight is not the kind that demands a calculator or lives only on a chalkboard. It is a math that lives in the delicate, six-sided way a snowflake forms, the way a honeybee builds a perfect, efficient home, the way your own body knows how to rest and how to wake with the slow, steady turning of the earth. It lives in the graceful curves of a seashell, in the patient, searching growth of roots deep beneath our feet, in the swirling collective dance of starlings, and in the ancient stillness of the mountains. What we find again and again is that the most breathtaking complexity does not require a complicated plan. Often, the most intricate and beautiful patterns emerge from the simplest rules, repeated with the patient grace of time, like a fern slowly unfurling, or a river choosing its most effortless path to the sea. In nature, order and chaos do not sit on opposite ends of a scale. They hold hands. They dance together. A murmuration of birds, a brewing thunderstorm, a perfectly timed and restorative nap. They all exist in that beautiful, liminal space where structure and spontaneity meet. Perhaps the greatest gift that the mathematics in nature gives us is the gentle invitation to slow down, to notice, to pay attention not just to the things we see, but to how they all fit together. The way the branches of one tree echo the branches of another, the quiet rhythm of your own footsteps on a forest trail, the soft, steady pulse of your own breath, quietly, faithfully keeping time. There is a deep poetry in it all, not just in the words that we speak, but in the shapes, the sounds, and the movements that nature writes across the entire world. And now, as your eyes grow heavier, or as your thoughts begin to wander gently somewhere else, let this be a soft and peaceful place for you to rest. Whether you are drifting off into a deep and peaceful sleep, or simply resting in this quiet stillness, know that the patterns are all around you and within you, steady, calming, and quietly carrying on. Before you go, if this gentle exploration has brought you a moment of wonder or a moment of rest, I would be so deeply grateful if you would give this video a like and consider subscribing to The Midnight Scientist. It helps others find their way to this quiet corner too, and it truly means the world to me. And I would love to know where in the world you are listening from and what time it is for you right now. It is always so beautiful to see how far these calm little ripples can reach. Until next time, sleep well, Stay curious, and remember, there is a quiet and beautiful poetry in the patterns, if we only take the time to look.